In 1718, Edmund Halley noticed something that should have been impossible. 3 bright stars had drifted from where the ancient Greeks had charted them, not by error, but by actual motion across the heavens. This quiet discovery opened a door that astronomers would walk through for nearly 3 centuries, measuring, cataloguing, refining their understanding of a sky that refused to stay still. The work was painstaking, often solitary, conducted through long nights with instruments of ever-increasing precision, from Halley's careful comparisons with Hipparcos, through the photographic surveys of the 20th century, to the Hipparcos satellite launched in 1989, which mapped over 100,000 stars with an accuracy that earlier generations could scarcely have imagined. If these kinds of slow, quiet journeys through history help the mind settle, subscribing might bring more restful evenings like this one. The stars, it turned out, were never fixed, and so the story begins. In the early decades of the 18th century, as the fields and hedgerows of England lay quiet beneath winter skies, and the great dome of the heavens turned slowly overhead as it had done for countless generations before, a singular discovery was taking shape in the mind of a man who had already contributed so much to our understanding of the cosmos, and who would now, in his 60th year, reveal something that would fundamentally alter humanity's conception of the universe itself. Something so profound and yet so gently announced that its full implications would take decades to be properly absorbed by the scientific community of Europe and beyond. Edmund Halley, whose name we most readily associate with the famous comet that bears it still, was by the year 1718 a figure of considerable standing in the world of natural philosophy, having served as Astronomer Royal and having devoted much of his long career to the patient work of observation and calculation that forms the quiet backbone of astronomical science. And it was in that year that he published a paper in the Philosophical Transactions of the Royal Society, a paper written in the measured and methodical prose typical of such communications, which contained within its carefully worded paragraphs a revelation that would echo through the centuries to come. For Halley had discovered that the stars themselves were moving. To understand why this discovery was so remarkable, and why it had eluded the careful observers who had come before him across so many hundreds and indeed thousands of years, we must first consider what people believed about the stars prior to Halley's announcement, and how deeply ingrained was the notion that the stellar realm represented a sphere of perfect and unchanging constancy, a celestial backdrop against which the planets wandered and the moon traced its monthly path, but which itself remained forever still, forever fixed in the positions that the ancients had recorded with such care in their catalogues and their treatises, positions that were meant to serve as eternal reference points for all the astronomical work that followed. The stars were called fixed stars for precisely this reason, to distinguish them from the wandering stars or planets whose motions across the sky were obvious and predictable. And this terminology was not merely a convenience of language but reflected a genuine cosmological belief that the stellar sphere existed at the outermost boundary of creation, perfect and immutable, turning once each day around the axis of the world but otherwise unchanging in its arrangements. And so when Halley examined the positions of certain bright stars as recorded by the astronomers of antiquity and compared them with the positions measured by the astronomers of his own era, he was not initially looking for motion at all, but was rather engaged in the sort of careful scholarly comparison that occupied many of his contemporaries. What drew Halley's particular attention in this investigation were 3 of the brightest stars visible from the latitudes of Europe, stars that had been known since the earliest days of recorded astronomy and whose positions had been carefully noted by the ancient Greek astronomer Hipparcos, working on the island of Rhodes more than 2,000 years before Halley's time, and these positions had been preserved and transmitted through the centuries by way of the great astronomical compendium known as the Almagest, compiled by Claudius Ptolemy of Alexandria in the 2nd century of the Common Era. And it was against these ancient records that Halley now compared the positions determined by the precise instruments and refined methods of the 17th and early 18th centuries. The 3 stars in question were Arcturus, which gleams with an orange light in the constellation of Boötes and is one of the brightest objects in the northern sky, and Sirius, the brilliant white star that dominates the constellation of Canis Major and is the brightest star visible from Earth, and finally Aldebaran, the ruddy eye of Taurus the Bull. And when Halley examined the recorded latitudes of these 3 notable stars, comparing the ancient values with the modern measurements, he found discrepancies that were far too large to be explained away by the ordinary sources of error that afflict astronomical observations. For Arcturus in particular, Halley calculated that the star had moved from its ancient position by a quantity exceeding half a degree of arc, which may sound like a small amount to those unfamiliar with the precision of astronomical measurement, but which represented an enormous displacement when considered against the stability that was supposed to characterize the fixed stars. And when Halley considered that this change had accumulated over the course of approximately 1800 years, he recognized that he was seeing evidence of genuine motion, a slow but steady drift across the celestial sphere that had carried the star from where Hipparcos had observed it to where it now appeared in the telescopes and quadrants of Halley's contemporaries. The calculation itself was straightforward enough once one accepted the premise that the star might actually be moving, for Halley simply took the difference between the ancient and modern positions and divided it by the elapsed time, arriving at a rate of motion that, while imperceptible on human timescales, was nonetheless real and measurable when accumulated across the vast spans of time that separate us from the astronomers of classical antiquity. And this rate of motion came to be called proper motion, a term that distinguishes the star's own intrinsic movement through space from the various apparent motions caused by the Earth's rotation and orbital motion. And it is a term that remains in use among astronomers to this very day. Halley's background and training had prepared him well for exactly this kind of meticulous historical and observational comparison, for he had devoted himself from an early age to the careful work of mapping the heavens and recording the positions of celestial objects with the greatest accuracy that the instruments of his time would allow. And his first major contribution to astronomy had come when he was still a young man in his early 20s, when he undertook an ambitious expedition to the remote island of St. Helena in the South Atlantic, far from the lights and the comfortable observatories of Europe, in order to compile the first systematic catalogue of the stars visible from southern latitudes. The St. Helena expedition, which occupied Halley from 1676 to 1678, was a formative experience that taught him both the practical challenges of astronomical observation and the importance of extending human knowledge into regions of the sky that had been neglected or unknown to the astronomers of the Northern Hemisphere. And during his time on that isolated volcanic island, working with a small telescope and a sextant under conditions that were often hampered by clouds and the difficulties of establishing precise geographical coordinates, Halley managed to catalogue the positions of over 300 southern stars, a contribution that earned him election to the Royal Society at the remarkably young age of 22 and established his reputation as a careful and dedicated observer. This early work at St. Helena gave Halley a deep appreciation for the value of stellar catalogues and for the painstaking efforts of those who had compiled them across the ages. And it was this appreciation that led him in later years to study carefully the observations preserved in Ptolemy's Almagest, recognizing that these ancient measurements, however crude they might seem by the standards of the 18th century, represented an invaluable baseline against which changes in the heavens might potentially be detected, And it was precisely this line of investigation that ultimately bore fruit in his discovery of stellar proper motion. The Almagest itself is a remarkable document. A comprehensive treatise on mathematical astronomy compiled by Ptolemy around the year 150 of the Common Era. And among its many contents is a catalogue of over 1,000 stars with their positions given in terms of celestial latitude and longitude. And while Ptolemy was certainly a skilled observer in his own right, a significant portion of the data in this catalogue derives from the earlier work of Hipparcos, who had compiled his own stellar catalogue some 3 centuries before Ptolemy's time. And thus the positions recorded in the Almagest carry us back even further into antiquity, to an era when the Mediterranean world was still under the influence of Hellenistic culture, and the great library of Alexandria was a center of learning and scholarship. It was this great antiquity of the observations that made Halley's discovery possible. For the proper motions of stars are so exceedingly small that they can only be detected when one has a very long baseline of time over which to observe them. And while an observer watching a star for a single human lifetime, or even for several generations, would notice no change in its position whatsoever, the accumulation of 18 centuries of motion had produced a displacement large enough to be unmistakable, and Halley had the insight to recognize this displacement for what it was, not an error in the ancient observations, but evidence of genuine stellar motion. When Halley published his findings in 1718, the response from his contemporaries was not universally accepting, for there were many who found it difficult to abandon the long-held belief in the fixity of the stars, and who preferred to attribute the discrepancies that Halley had identified to errors in the ancient observations themselves, arguing that Hipparcos and Ptolemy had simply measured the positions of these stars incorrectly, perhaps due to the limitations of their instruments or to mistakes in their calculations, and that no actual motion needed to be invoked to explain the differences between ancient and modern catalogues. This skepticism was not entirely unreasonable, for the instruments available to ancient astronomers were indeed far less precise than those developed in the centuries following the invention of the telescope. And it was well known that the Almagest contained various errors and inconsistencies that had been identified by careful scholars over the years. And so the suggestion that the discrepancies observed by Halley might be attributed to observational shortcomings rather than to actual stellar motion was a legitimate hypothesis that had to be considered and addressed. And it took some time before the weight of evidence accumulated sufficiently to convince the majority of astronomers that Halley had indeed discovered something genuine and important. One of the strongest arguments in favor of Halley's interpretation was the selective nature of the discrepancies he had found. For if the differences between ancient and modern positions were simply due to random errors in the ancient observations, one would expect these errors to be distributed more or less evenly across all the stars in the catalogue, with some showing positive discrepancies, some showing negative discrepancies, and most showing discrepancies of similar magnitude. But what Halley observed was that only certain stars, notably Arcturus, Sirius, and Aldebaran, showed large discrepancies, while the majority of stars agreed quite well with their ancient positions, and this pattern strongly suggested that something real was happening to these particular stars rather than that the ancient observers had simply made mistakes. It is worth noting that Halley was not entirely alone in suspecting that stars might possess their own motions, for around the same period the French astronomer Jacques Cassini, who was himself a member of the distinguished Cassini family that dominated French astronomy for several generations, had also begun to suspect that some stars might not be entirely fixed in their positions. And while Cassini's work on this question was less conclusive than Halley's, and while he did not publish a definitive announcement of stellar motion as Halley did, The fact that more than one astronomer was beginning to question the traditional doctrine of fixed stars suggests that the time was ripe for this conceptual revolution, and that the accumulating precision of astronomical measurement was inevitably going to reveal the subtle motions that had previously escaped detection. The implications of Halley's discovery extended far beyond the mere cataloguing of stellar positions. For if the stars were not fixed but were instead moving through space, then the entire cosmological framework within which they had been understood required revision, and questions arose naturally about the nature and cause of these motions, about whether all stars possessed them or only some, about whether the motions were random or followed some larger pattern, and ultimately about whether our own Sun, which is after all merely another star, might itself be moving through the cosmos in a similar fashion. This last question, concerning the motion of the Sun, proved to be one of the most fruitful lines of investigation that emerged from Halley's discovery. For once astronomers began to measure the proper motions of many stars with increasing precision over the following decades, patterns began to emerge that suggested the Sun was indeed in motion relative to the surrounding stellar neighborhood. And this solar motion could be detected by observing that stars in one direction of the sky appeared on average to be moving apart from one another, as if we were approaching them, while stars in the opposite direction appeared to be converging, as if we were receding from them. And by analyzing these statistical patterns, astronomers were eventually able to determine both the direction and the approximate speed of the Sun's journey through interstellar space. The work of determining stellar proper motions continued throughout the 18th and 19th centuries, with each generation of astronomers building upon the observations of their predecessors and gradually extending the baseline of time over which motions could be measured. And as telescopes improved and techniques of positional measurement became more refined, astronomers were able to detect the proper motions of fainter and more distant stars, gradually building up a picture of the complex choreography of stellar motion that fills the space around our solar system. Among the stars whose proper motions were eventually measured, some were found to be moving quite rapidly across the sky, while others drifted so slowly that their motion could barely be detected. And this variation in proper motion reflected partly the different actual velocities of the stars through space and partly their different distances from us. For a nearby star moving at a given speed would appear to cross a greater angle of sky each year than a distant star moving at the same speed, just as a bird flying close overhead seems to flash past more quickly than a distant aeroplane. And thus the measurement of proper motions was intimately connected with the challenge of determining stellar distances, a challenge that would occupy astronomers for many decades to come. Halley himself continued to contribute to astronomy in many other ways throughout his long career, and he remained active in scientific work until his death in 1742 at the age of 85. Having served as Astronomer Royal for over 20 years and having witnessed the development of new instruments and methods that would carry the science he loved far beyond what had been possible in his youth. And while he is perhaps best remembered today for his work on the comet that bears his name, his discovery of stellar proper motion stands as one of the most fundamental contributions to our understanding of the universe, revealing as it did that the heavens are not the static and unchanging realm they had long been thought to be, but are instead a dynamic space filled with objects in constant motion. The stars that we see on any clear night, drifting slowly overhead as the Earth turns beneath them, are not the same arrangement that the ancients saw, and they will not be the same arrangement that our distant descendants will see. For each star is pursuing its own course through the galaxy, some moving quickly and some moving slowly, some approaching us and some receding, some destined to grow brighter as they draw near and others destined to fade as they drift away. And all of this ceaseless motion was first glimpsed by Edmund Halley in his quiet comparison of ancient and modern star catalogues. a comparison that revealed the universe to be a far more interesting and dynamic place than anyone had previously supposed. And so we may picture Halley in his study, surrounded by the papers and instruments of his trade, poring over the coordinates recorded by Hipparcos and Ptolemy so many centuries before, comparing them carefully with the measurements of his own era, and gradually coming to the realization that these small discrepancies, these tiny departures from the expected positions, were not errors at all but were instead the signature of motion, the faint traces left by stars pursuing their journeys across the vast and patient canvas of the sky, journeys that had been underway for countless ages before any human eye looked upward in wonder, and that will continue for countless ages more, long after our own brief moment under the stars has passed into the peaceful silence of deep time. In the quiet hours before dawn, when the stars will silently overhead and the world seems to hold its breath, there have always been patient observers who wished to know exactly where each point of light might be found in the sky. For centuries, astronomers gazed upward with instruments that were, by modern standards, rather imprecise, and their measurements of stellar positions contained errors that we would now consider quite large. But gradually, through the careful work of craftsmen and the methodical observations of dedicated astronomers, a new kind of instrument emerged that would transform our understanding of the heavens, allowing positions to be determined with an accuracy that earlier generations could scarcely have imagined. This transformation did not happen all at once, and it did not come about through any single dramatic discovery, but rather through the steady accumulation of small improvements, each one building upon what came before, each one bringing the positions of the stars into slightly sharper focus. The story of this transformation begins in Copenhagen, in the closing years of the 17th century, where a Danish astronomer named Ole Romer was engaged in the painstaking work of observing the heavens. Romer is perhaps best remembered today for his remarkable discovery that light travels at a finite speed, a finding he deduced from careful observations of the moons of Jupiter. But his contributions to the practical art of astronomical observation were equally significant, even if they are less often celebrated. Around the year 1689, Romer devised an instrument that would come to be known as the transit instrument, a telescope mounted in such a way that it could move only in the plane of the meridian, that imaginary great circle passing through the north and south points of the horizon and through the zenith directly overhead. By constraining the telescope to move only along this single arc, Romer eliminated one of the two coordinates needed to specify a star's position, allowing the observer to focus entirely on the moment when a star crossed the meridian, that instant of transit that gave the instrument its name. The principle underlying the transit instrument is wonderfully straightforward, and there is something rather soothing about its simplicity. As the Earth rotates on its axis, the stars appear to drift slowly across the sky from east to west, and each star, in the course of its nightly journey, must eventually cross the meridian. At the moment of transit, the star reaches its highest point in the sky for that particular night, and by noting the precise time at which this crossing occurs, the observer can determine the star's right ascension, one of the two coordinates used to specify positions in the celestial sphere. The transit instrument made it possible to measure these crossing times with far greater precision than had been achieved with earlier instruments, because the observer needed only to watch for the star to pass behind a fine wire or thread stretched across the eyepiece of the telescope, rather than trying to estimate the star's position against the entire backdrop of the sky. Romer's original transit instrument was a significant advance, but like all first attempts at a new design, it was not without its limitations. The instrument needed to be aligned with exquisite care so that it moved exactly in the plane of the meridian, and any small error in this alignment would introduce corresponding errors into the measurements. The telescope itself needed to be mounted on sturdy pivots that allowed it to rotate smoothly without any wobbling or flexing, and the whole apparatus needed to be protected from the effects of temperature changes and other environmental disturbances that might cause the metal parts to expand or contract unevenly. Over the decades that followed, instrument makers in various countries worked to address these challenges, refining the design of the transit instrument and developing techniques for correcting the small errors that inevitably crept into even the most carefully constructed apparatus. One of the most important developments in this gradual refinement was the combination of the transit telescope with a graduated circle, creating what came to be known as the meridian circle or transit circle. Where the simple transit instrument measured only the time at which a star crossed the meridian, the meridian circle added a precisely divided circular scale that allowed the observer to measure the star's altitude or zenith distance at the same moment. This second measurement, when combined with a knowledge of the observer's latitude, made it possible to determine the star's declination, the second of the two coordinates needed to specify its position in the celestial sphere. With a single instrument, an observer could now determine both coordinates of a star's position, and by making repeated observations over many nights, the inevitable small errors could be averaged out, yielding positions of remarkable accuracy. In England, the art of instrument making reached new heights of excellence during the middle of the 18th century, and one of the finest practitioners of this art was John Bird, whose name may not be widely known today but whose work influenced the course of astronomical observation for generations. Bird was a craftsman of extraordinary skill, capable of dividing the graduated circles of astronomical instruments with a precision that few others could match. In the 1750s, he constructed a series of superior instruments for the Royal Observatory at Greenwich, instruments that represented a substantial improvement over what had come before. Bird's circles were divided by hand, using techniques that required immense patience and a steady touch, and the quality of his workmanship was such that astronomers could rely upon his instruments to give measurements that were consistent and trustworthy, night after night and year after year. The graduated circles that formed such an essential part of these instruments were among the most challenging components to manufacture with precision. A circle might be several feet in diameter, made of brass or some other suitable metal, and around its circumference were inscribed tiny marks indicating degrees, minutes, and even smaller subdivisions of arc. The accuracy of any measurement made with the instrument depended critically upon the accuracy of these divisions, and even small errors in the spacing of the marks would translate directly into errors in the observed positions of the stars. For much of the 18th century, these divisions were made by skilled craftsmen working by hand, using dividing compasses and other tools that required great dexterity and patience. The process was slow, and the results, while often very good, varied according to the skill and care of the individual craftsman. A transformative advance in the production of graduated circles came in 1775, when the English instrument maker Jessie Ramsden completed his first dividing engine, a mechanical device that could automatically inscribe the divisions on a circular scale with unprecedented accuracy and consistency. Ramsden's dividing engine was itself a marvel of precision engineering, built with exacting care and incorporating ingenious mechanisms for ensuring that each division was placed exactly where it should be. The engine used a large master screw to rotate the circle through precisely equal angles, and at each position, a diamond-tipped cutter inscribed a fine line on the metal surface. By automating this process, Ramsden was able to produce circles that were divided with an accuracy of just a few seconds of arc, a level of precision that would have been extraordinarily difficult to achieve by hand. The impact of Ramsden's dividing engine on the practice of positional astronomy was profound, though it unfolded gradually over the years and decades that followed. Instruments equipped with circles divided by Ramsden's engine, or by similar engines constructed by other makers who adopted his methods, could measure positions with errors measured in seconds of arc rather than the minutes of arc that had characterized earlier instruments. This improvement might seem modest when expressed in numerical terms, but it represented a refinement of roughly a factor of 60, and it opened up entirely new possibilities for astronomical research. Stars that had previously appeared to be fixed in place could now be seen to have tiny motions of their own, drifting almost imperceptibly against the background of more distant stars over the course of years and centuries. Among the instrument makers who built upon these advances, Edward Troughton stands out as a figure of particular importance. Troughton was active in London during the late 18th and early 19th centuries, and he combined a deep understanding of astronomical requirements with exceptional skill in the workshop. He collaborated closely with other instrument makers and with the astronomers who would use his instruments, seeking always to understand what improvements might be most beneficial and how they might be achieved in practice. The instruments that Troughton produced were characterized by careful attention to every detail, from the quality of the optical components to the smoothness of the pivots and the accuracy of the graduated circles. In 1806, a transit circle constructed by Troughton was installed at Greenwich, and this instrument represented a significant step forward in the capabilities available to astronomers at the Royal Observatory. The Troughton transit circle incorporated numerous refinements over earlier designs, including improvements to the mounting that reduced flexure and vibration, better methods for aligning the instrument with the true meridian, and circles that were divided with the aid of a dividing engine to ensure the highest possible accuracy. With this instrument, the astronomers at Greenwich could determine the positions of stars with errors of just a few seconds of arc, a level of precision that would have astonished their predecessors of just a century earlier. The methodology employed with these transit circles followed a careful and systematic routine that was repeated night after night, season after season, with a patience that is perhaps difficult to appreciate fully in our modern age of instant results. The observer would take up a position at the eyepiece of the telescope as evening twilight faded and the first stars became visible. A clock, regulated with great care to keep accurate time, would tick steadily nearby, and in the eyepiece of the telescope, a series of fine wires or threads would be visible, stretched across the field of view. As a star drifted into the field, carried by the rotation of the Earth, the observer would watch intently, waiting for the moment when the star's image crossed each of the wires in turn. At each crossing, the observer would note the time shown on the clock, either by listening for the ticks and estimating the fraction of a second or, in later years, by using an electrical recording device that could capture the moment with greater precision. From these timings, and from the readings taken from the graduated circles, the position of the star could be calculated. But a single observation was never considered sufficient, because the small errors inherent in any measurement could only be reduced by repetition. The same star would be observed on many different nights, and the results would be averaged together, with the random errors tending to cancel out and the true position emerging from the accumulation of data. The process was slow, and a comprehensive catalogue of stellar positions might take years or even decades to compile, but the results were trustworthy in a way that earlier catalogues had never been. The year 1816 saw the installation of a new transit circle at Greenwich, one that incorporated further refinements and represented the state-of-the-art in astronomical instrumentation. This instrument would serve the observatory for many years, contributing to the great catalogues of stellar positions that were compiled during the 19th century. Similar instruments were installed at other major observatories around the world, as the techniques developed in England spread to the continent and beyond. At the Paris Observatory, French astronomers adopted transit circles for their own programs of stellar observation, contributing to the international effort to map the positions of the stars with ever greater accuracy. The observatory at Pulkovo, near St. Petersburg in Russia, became one of the leading centers of positional astronomy, equipped with instruments that rivaled or even surpassed those at Greenwich in their precision. And at the Cape of Good Hope, astronomers turned their transit circles toward the southern skies, mapping stars that could never be seen from European latitudes. The cumulative effect of all these observations, made with instruments of steadily improving accuracy over the course of more than a century, was a transformation in our knowledge of the positions of the stars. Where earlier catalogues had listed positions with errors of several minutes of arc, the catalogues of the 19th century achieved accuracies of a few seconds of arc, and the best observations could determine positions to a fraction of a second of arc. This improvement made it possible to detect the small proper motions of nearby stars, to measure the tiny shifts caused by stellar parallax, and to place the study of stellar positions on a firm quantitative foundation. The transit instrument revolution was not the work of any single individual, but rather the product of many contributions, each one building upon what came before. Romer conceived the basic idea and demonstrated its potential. Bird and Ramsden developed the techniques for constructing instruments of the highest quality. Troughton brought these various strands together and produced instruments that set new standards of accuracy. And countless observers, working patiently night after night at observatories scattered around the world, transformed the potential of these instruments into actual knowledge, compiling the catalogues of stellar positions that form the foundation of modern astrometry. Their work was not glamorous, and it rarely attracted public attention, but it was essential, and the legacy of their careful observations endures to this day. As you rest now, and as your thoughts perhaps drift towards sleep, you might find it pleasant to imagine those patient observers of centuries past, seated at their telescopes in the quiet hours of the night, watching as the stars drifted slowly across the meridian and recording the moments of transit with unhurried precision. There is something deeply reassuring about the steadiness of their work, the way they returned to the same task night after night, content to make their small contributions to a project that would span generations. The stars that they observed are still there, wheeling overhead in the same slow procession, and the positions they measured remain valid today, a testament to the care and patience with which they carried out their observations. And so, as the night deepens and the stars pursue their ancient courses across the sky, you may let your mind settle into quietness, knowing that the universe continues its steady turning, just as it did when those first transit instruments were trained upon the heavens, and just as it will continue to do for ages yet to come. In the early decades of the 18th century, the question of stellar parallax remained one of the great unsolved problems of observational astronomy, and it drew the attention of some of the most careful observers of the age, including a quiet and remarkably patient English astronomer named James Bradley, who would spend years looking for one thing and find, quite by accident, two entirely different phenomena that would reshape our understanding of how light travels through space and how the Earth moves through the heavens. Discoveries that emerged not from dramatic moments of inspiration but from the slow, Methodical accumulation of measurements taken night after night, season after season, with instruments of unprecedented precision and a dedication to accuracy that bordered on the obsessive, though in the gentlest and most productive way imaginable. Bradley was born in 1693 in Sherborne in Gloucestershire, and he came to astronomy through the influence of his uncle, the Reverend James Pound, who was himself a skilled observer and who recognized in his nephew a particular aptitude for careful measurement and patient analysis, the sort of temperament that finds satisfaction not in grand theorizing but in the quiet accumulation of reliable data. And this temperament would serve Bradley well throughout his long career, though perhaps never more so than during the years he spent at Kew, beginning in 1725. When he embarked on what he hoped would be the definitive measurement of stellar parallax. The search for parallax was, at this time, a matter of considerable scientific importance. For while the heliocentric model of Copernicus had gained wide acceptance among astronomers and natural philosophers, there remained no direct observational proof that the Earth actually moved around the Sun. And the detection of stellar parallax would provide exactly such proof, since it would demonstrate that the apparent positions of stars shifted slightly over the course of a year as the Earth moved from one side of its orbit to the other, and this shift, however small, would be incontrovertible evidence of our planet's motion through space. Bradley's opportunity to pursue this measurement came through his friendship with Samuel Molyneux, a wealthy amateur astronomer who had installed at his residence at Kew House a remarkable instrument designed specifically for the purpose of detecting stellar parallax. And this instrument was a zenith sector of exceptional quality, constructed by the master instrument maker George Graham, whose reputation for precision was unmatched in England. And the sector featured a telescope with a focal length of 24.5 feet. Mounted so that it could observe stars as they passed directly overhead, through the zenith, which was the point in the sky least affected by atmospheric refraction, that troublesome bending of starlight that had plagued astronomical measurements for centuries. The choice to observe stars at or very near the zenith was a deliberate one, driven by the understanding that the atmosphere acts like a lens, bending light rays more severely when they enter at oblique angles, so that stars near the horizon appear higher in the sky than they actually are, and this effect diminishes as one looks more nearly straight up, becoming essentially negligible for stars passing directly overhead. And by eliminating or at least minimizing this source of error, Bradley and Molyneux hoped to achieve the unprecedented accuracy that would be necessary to detect the tiny angular shift of stellar parallax. The star they chose to observe was Gamma Draconis, a moderately bright star in the constellation Draco that had the convenient property of passing almost exactly through the zenith as seen from the latitude of Kew, making it an ideal target for their zenith sector. And they began their systematic observations in December of 1725, carefully recording the precise position of this star each time it crossed their meridian, building up a series of measurements that they hoped would reveal the telltale annual wobble of parallax. What they found, however, was something quite unexpected, for the star did indeed appear to shift its position over the course of the weeks and months of observation. But the shift was in the wrong direction and at the wrong time of year to be explained by parallax, and at first Bradley and Molyneux were puzzled, uncertain whether the displacement was real or whether it represented some undetected error in their instrument or their methods. But as the observations accumulated and the pattern became clearer, Bradley became convinced that they were witnessing a genuine phenomenon, something that required explanation even if it was not the parallax they had been seeking. Samuel Molyneux's attention was soon drawn away from the project by his duties in Parliament and by his appointment as a Lord of the Admiralty, and so Bradley continued the work largely on his own. eventually installing a second zenith sector at the home of his aunt in Wanstead, where he could observe a wider range of stars and gather more comprehensive data. And through these extended observations, he gradually pieced together the pattern of stellar displacement, noting that it followed an annual cycle but that the maximum displacement occurred not when the Earth was at the extremes of its orbit, as parallax would require, but rather when the Earth was moving most directly toward or away from the star in question. This realization was the key to understanding the phenomenon, for Bradley came to see that the displacement was caused not by the Earth's changing position in space but by its changing velocity, by the fact that our planet is constantly in motion around the Sun at a speed of approximately 30 kilometers per second. And this motion affects the apparent direction from which starlight arrives, in much the same way that rain, falling vertically on a still day, appears to come from ahead when one is walking or running forward. And this analogy, which Bradley himself used to explain his discovery, has become one of the most famous in the history of astronomy. Imagine, if you will, that you are standing still on a day when rain is falling perfectly straight down, and if you hold an empty tube or pipe vertically, the raindrops will fall straight through it without touching the sides. But now imagine that you begin to walk forward while holding the same tube, and you will find that the raindrops now strike the front edge of the tube and fail to pass through unless you tilt the tube slightly forward, angling it in the direction of your motion. And the faster you walk, the more you must tilt the tube to allow the rain to pass through. And this tilt represents the angle between the true direction of the rain and its apparent direction as perceived by someone in motion. Bradley recognized that exactly the same principle applies to starlight and to the motion of the Earth, for light from a distant star travels toward us at a finite speed. And while that speed is enormously fast compared to the Earth's orbital velocity, it is not infinite. And so the combination of the light's motion and the Earth's motion produces a small apparent shift in the direction from which the light seems to come. And this shift, which Bradley called the aberration of light, causes every star to trace out a small ellipse in the sky over the course of a year, with the shape and orientation of the ellipse depending on the star's position relative to the plane of the Earth's orbit. Bradley announced his discovery of aberration in 1728, presenting his findings to the Royal Society and providing both the observational evidence and the theoretical explanation for this previously unknown phenomenon. And he was able to calculate the maximum displacement caused by aberration, which he found to be approximately 20.5 arcseconds, a quantity now known as the constant of aberration and currently measured with great precision as approximately 20.5 arcseconds, though modern values have refined this slightly to about 20.49 arcseconds, a number that depends on the ratio of the Earth's orbital velocity to the speed of light. The significance of this discovery extended far beyond the explanation of an unexpected observational result, for the aberration of light provided, for the first time, direct and incontrovertible evidence that the Earth is in motion around the Sun, since the phenomenon could not occur if the Earth were stationary. And so while Bradley had failed to detect parallax, he had nevertheless achieved the larger goal of proving the Copernican hypothesis through observation, and his discovery was immediately recognized as one of the most important contributions to astronomy of the century. Moreover, the constant of aberration provided a new way to estimate the speed of light, for if one knew the Earth's orbital velocity and the angle of aberration, one could calculate how fast light must travel to produce such an angle, and Bradley's measurements were consistent with the estimates of light speed that had been made by Ole Romer some 50 years earlier through observations of Jupiter's moons. And this agreement between two completely independent methods gave astronomers increased confidence in both results. But Bradley was not content to rest on this achievement. for he recognized that his observations of Gamma Draconis and other stars contained additional information that his aberration theory did not fully explain. And so he continued his meticulous measurements year after year, accumulating data with a patience and persistence that few observers have ever matched. And over the course of nearly 2 decades of continuous observation, he gradually became aware of another small periodic variation in stellar positions, one with a much longer period than the annual cycle of aberration. This second phenomenon revealed itself only slowly, emerging from the noise of measurement error through the sheer weight of accumulated observations, and Bradley eventually determined that it had a period of approximately 18.5 years, which corresponded almost exactly to the period of the lunar nodal cycle, the time it takes for the points where the Moon's orbit crosses the plane of the Earth's equator to complete one full circuit around the sky. And this correspondence suggested that the phenomenon was somehow connected to the gravitational influence of the Moon on the Earth. Bradley came to understand that this variation, which he called nutation, was caused by a small wobble in the orientation of the Earth's rotational axis, a wobble induced by the gravitational pull of the Moon on the Earth's equatorial bulge, which is the slight flattening of our planet that results from its daily rotation, and this wobble causes the celestial pole to trace out a small ellipse in the sky, superimposed on the much larger and slower circle of precession that had been known since the time of Hipparcos, and the maximum displacement due to nutation is approximately 9 arcseconds, considerably smaller than the aberration effect but still large enough to matter for precision astronomy. Bradley announced his discovery of nutation in 1748, more than 20 years after he had begun his observations at Kew, and this lengthy interval between the start of his work and the completion of his analysis reflects both the long period of the phenomenon itself and the extraordinary care that Bradley took to ensure that his conclusions were correct, for he recognized that extraordinary claims require extraordinary evidence, and he was unwilling to announce his discovery until he had accumulated enough data to rule out other possible explanations. The zenith sector constructed by George Graham that Bradley used for these observations was a masterpiece of 18th-century instrument making, with its 24.5-foot focal length providing the resolving power necessary to detect angular displacements of just a few arcseconds. And the careful design of the mounting and the division of the arc allowed Bradley to make measurements of unprecedented accuracy. And it is worth pausing for a moment to appreciate the patience required to work with such an instrument night after night, in the cold and damp of English evenings, recording the transit times and zenith distances of stars with a precision that the instrument could only barely deliver. Bradley's dedication to accuracy extended beyond his observations to his methods of analysis, for he developed techniques for identifying and correcting systematic errors in his instruments and his measurements, and he understood that the true value of an observation lies not just in the number recorded but in a careful assessment of the uncertainty associated with that number. And this understanding, which may seem obvious to modern scientists, was by no means universal in Bradley's time, and his insistence on quantifying and minimizing sources of error set a standard for precision astronomy that would influence observers for generations to come. In 1742, Bradley was appointed Astronomer Royal, succeeding Edmund Halley in that prestigious position and taking up residence at the Royal Observatory at Greenwich, where he would continue his work for the remaining 20 years of his life. And in this role he oversaw a comprehensive program of stellar observation that produced a catalogue of positions far more accurate than any that had come before. A catalogue that would serve as the foundation for future work in positional astronomy, and that would reveal still more subtle effects that Bradley himself did not live to fully analyze. The twin discoveries of aberration and nutation transformed the practice of astrometry, for they revealed that the apparent positions of stars are affected by phenomena that had previously been entirely unsuspected. And this meant that any serious program of precision measurement would need to account for these effects, adding new layers of complexity to the reduction of raw observations. And while this might seem to make the astronomer's task more difficult, it also provided new tools for understanding the motions of the Earth and new methods for testing physical theories. Bradley's work also had profound implications for the philosophy of science, for it demonstrated that careful observation could reveal truths about nature that were completely unexpected, truths that emerged not from theoretical speculation but from the patient accumulation of data and the honest confrontation with anomalies. And this lesson, that nature often has surprises in store for those who look carefully enough, remains one of the enduring messages of Bradley's career. The aberration of light, in particular, provided evidence for a finite speed of light that was independent of any astronomical model, for it depended only on the ratio of the Earth's velocity to the speed of light. And this independence made it a particularly powerful piece of evidence, one that could not be explained away by adjustments to other parameters. And the nutation of the Earth's axis similarly provided evidence about the shape and internal structure of our planet that could not have been obtained in any other way. As you lie there listening to this account of Bradley's patient work, you might find it soothing to contemplate the rhythm of his observations, the nightly ritual of preparing the instrument and waiting for the target star to cross the meridian, the careful recording of numbers in the observing log, the accumulation of data point after data point over months and years and decades, all in service of understanding how light travels through space and how our planet moves and wobbles in its eternal dance around the sun. The precision that Bradley achieved with his zenith sector was remarkable for its time, approaching the limits of what was possible with the technology available, and yet he understood that future instruments would surpass his own, that the progress of astronomy depends on each generation building upon the work of those who came before, and this humility before the immensity of the task of understanding the universe is one of the qualities that makes Bradley such an appealing figure in the history of science. The constant of aberration that Bradley measured, approximately 20.5 arcseconds, has been refined over the centuries by observers using increasingly sophisticated instruments, but Bradley's original value was remarkably close to modern measurements, a testament to the quality of his observations and the soundness of his methods. And the same can be said of his measurements of nutation, which have been confirmed and refined but never fundamentally altered. In the quiet of the evening, as you rest and let these words wash over you, you might imagine yourself in Bradley's position, peering through the eyepiece of the zenith sector, watching the slow drift of Gamma Draconis across the field of view, noting the time of transit and the angle from the zenith, and then retiring to the warmth of the house to record the observation and compare it with previous nights, building up, measurement by measurement, the picture of a universe in constant subtle motion, a picture that reveals itself only to those with the patience to look carefully and the honesty to report what they see. Bradley's discoveries, while not the parallax he had originally sought, proved to be even more fundamental. For aberration and nutation are universal phenomena that affect every star in the sky, not just the nearby ones that might show detectable parallax, and understanding these effects was essential before any reliable parallax measurements could be made. And so Bradley's work, while it did not itself detect stellar parallax, laid the groundwork for the successful detection that would come more than a century later. The 18.6-year period of nutation meant that Bradley had to observe for nearly 2 complete cycles to be confident of his results, and this 20-year program of observation represents one of the longest sustained efforts in the history of pre-modern astronomy, a a remarkable demonstration of scientific patience and dedication, and the data he collected during these years remained valuable long after his death, serving as the foundation for later work on the proper motions of stars and other phenomena. As the gentle darkness of sleep begins to gather around you, you can let these thoughts of Bradley's careful work settle into a peaceful background, knowing that the universe he studied continues above us, the stars tracing out their tiny ellipses of aberration as the Earth carries us around the Sun, the celestial pole nodding gently with the rhythm of nutation, all these motions too small to see with the naked eye but revealed through the patient accumulation of precise measurements, a reminder that the cosmos holds wonders within wonders, visible to those who take the time to look with care. The work of mapping the heavens with precision, which had progressed so steadily through the 17th century, reached a remarkable flowering in the decades that followed, as astronomers across Europe turned their attention to the painstaking task of recording the positions of stars with ever greater accuracy, building catalogues that would serve as foundations for all subsequent astronomical work. And it is to these great 18th-century star catalogues that we now turn our attention, settling into the quiet details of their creation, the patient astronomers who compiled them, and the sometimes complicated human circumstances that surrounded their publication and use. We might begin, as seems fitting, with the figure of John Flamsteed, the first Astronomer Royal of England, who spent the better part of his life at the Royal Observatory in Greenwich, observing the heavens night after night with a devotion that bordered on the monastic, and whose life's work would eventually appear in a volume called the Historia Celestis Britannica, published in 1725, 3 years after Flamsteed's death, containing the carefully measured positions of nearly 3,000 stars, recorded with a precision that surpassed anything that had come before it in the English-speaking world, and indeed rivaled or exceeded the best work being done anywhere on the continent at that time. Flamsteed had been appointed to his position in 1675, when King Charles II established the Royal Observatory with the express purpose of improving navigation at sea, a practical concern that would remain intertwined with the history of stellar cartography for centuries to come. And from the very beginning of his tenure, Flamsteed understood that his task was not merely to observe the heavens casually or to pursue whatever celestial phenomena happened to catch his interest, but rather to undertake the systematic measurement of stellar positions with the greatest possible care, building up over time a catalogue that could be trusted absolutely by navigators and astronomers alike. The instruments at Flamsteed's disposal were good ones for their era, including a mural arc of nearly 7 feet in radius, with which he could measure the altitudes of stars as they crossed the meridian. And over the course of more than 40 years of observation, he accumulated an enormous body of data, recording each star's position multiple times on different nights, averaging his results to reduce the inevitable small errors that crept into any single observation, and gradually constructing what he intended to be a definitive reference work for the positions of the fixed stars as seen from northern latitudes. The story of the Historia Celestis Britannica, however, cannot be told without mentioning the unfortunate controversy that arose between Flamsteed and 2 other towering figures of English science, namely Isaac Newton and Edmund Halley, a dispute that caused Flamsteed considerable distress in the final years of his life and which serves as a reminder that even the most abstract and seemingly impersonal scientific work is always, in the end, carried out by human beings with their own concerns, their own pride, and their own sense of how their work ought to be treated. Newton, who was at that time working on the 2nd edition of his Principia Mathematica, had need of accurate lunar observations to verify his theories of the moon's motion, and he grew impatient with what he perceived as Flamsteed's reluctance to share his data, while Flamsteed, for his part, was deeply protective of observations that had cost him decades of labor and which he felt were not yet ready for publication in their final form. And this fundamental disagreement over the timing and manner of publication led to a breach between the two men that was never fully healed. In 1712, without Flamsteed's consent and indeed over his strenuous objections, a preliminary version of his star catalogue was published under the editorship of Edmund Halley, containing many of Flamsteed's observations but in a form that Flamsteed considered incomplete, poorly organized, and in some cases actually erroneous, and the astronomer's fury at this unauthorized publication, which he regarded as a kind of theft of his life's work, was so great that when he eventually obtained copies of the offending edition, he is said to have burned as many of them as he could acquire, a dramatic gesture of protest against what he viewed as a violation of his rights as an observer. The complete and authoritative version of Flamsteed's work, the true Historia Celestis Britannica, was prepared after his death by his assistants Joseph Crosthwaite and Abraham Sharp, working from Flamsteed's original manuscripts and following the plan that he himself had laid out, and this posthumous publication of 1725 presented the positions of 2,935 stars, each one reduced to a common epoch and arranged systematically for easy reference. And it is this version that astronomers of subsequent generations would consult and cite, recognizing it as the authoritative record of Flamsteed's observations. The catalogue was accompanied by an atlas of star charts prepared by Flamsteed himself before his death, showing the constellations with their stars plotted according to his measured positions. And these charts, while perhaps less scientifically essential than the catalogue itself, were nevertheless beautiful and useful objects, combining the practical information of stellar cartography with the traditional iconography of the constellation figures, and they remained in use for many decades as a standard reference for identifying stars and their relative positions in the sky. While Flamsteed was laboring at Greenwich to map the northern heavens, the stars of the southern sky remained largely uncharted, visible only to observers stationed below the equator and therefore inaccessible to the major European observatories, all of which were located in northern latitudes. And it was to remedy this significant gap in astronomical knowledge that the French astronomer Nicolas Louis de Lacaille undertook his remarkable expedition to the Cape of Good Hope, departing from France in 1750 and establishing an observing station near Cape Town, where he would spend 2 years systematically surveying the southern stars with a dedication and efficiency that still commands admiration. Lacaille was a man of extraordinary energy and methodical temperament, qualities that served him well in the demanding work of observational astronomy, and during his time at the Cape, working with relatively modest instruments that he had brought with him from France, he managed to observe and record the positions of 9,766 stars, a number that far exceeded anything that had been achieved before for the southern heavens, and his catalogue, when it was eventually published, more than doubled the number of accurately known stellar positions available to astronomers. The conditions under which Lacaille worked were not always comfortable, as the Cape Colony in the 1750s was a remote outpost with limited resources, and the astronomer had to contend not only with the usual challenges of astronomical observation, such as clouds, atmospheric turbulence, and the limitations of his instruments, but also with the practical difficulties of maintaining a scientific expedition far from the support of European institutions. Yet despite these obstacles, he persevered with remarkable determination, observing on every clear night and reducing his observations during the daylight hours. In addition to his great catalogue of southern stars, Lacaille also introduced a number of new constellation names for regions of the southern sky that had not been formally designated by earlier astronomers, choosing names that reflected the scientific and technological interests of his era, such as the air pump, the microscope, the telescope, and the chemical furnace. And while some of these names may seem prosaic compared to the mythological figures that populate the traditional constellations of the northern sky, they have nevertheless endured and remain in use to this day, a lasting memorial to Locale's work at the Cape. The Paris Observatory, which had been founded in 1667 under the direction of Giovanni Domenico Cassini, continued throughout the 18th century to make important contributions to positional astronomy under the leadership of successive generations of the Cassini family, with Jacques Cassini succeeding his father and being followed in turn by César-François Cassini de Thury and Jean-Dominique Cassini, each of whom maintained the observatory's tradition of careful observation and measurement. And while the Paris Observatory did not produce a single monumental star catalogue comparable to Flamsteed's Historia Celestis, its ongoing program of positional observations contributed steadily to the accumulating body of knowledge about stellar positions and motions. The Cassini family's particular interest lay in geodesy and cartography as much as in astronomy proper, and they undertook the great project of mapping France with unprecedented accuracy, a task that required precise astronomical observations to establish the geographical coordinates of reference points across the country. And in this way, the work of the Paris Observatory remained closely connected to the practical applications of positional astronomy, demonstrating once again the intimate relationship between the measurement of stellar positions and the needs of navigation and surveying. Contemporary with Locale's expedition to the southern hemisphere, the German astronomer Tobias Meyer was working at the observatory in Göttingen to produce a catalogue of exceptional precision, focusing his attention on the stars of the zodiac, that band of constellations through which the sun, moon, and planets appeared to move as seen from Earth, and which was therefore of particular importance for the calculation of planetary positions and the prediction of astronomical events. Meyer's catalogue, completed in 1756, contained the positions of 998 zodiacal stars, a number that might seem modest compared to the thousands of stars in Flamsteed's or Locale's catalogues. But the exceptional accuracy of Meyer's measurements gave his work a value that exceeded what the raw numbers might suggest, as his positions were determined with a precision that approached the theoretical limits of what could be achieved with the instruments of his day, and subsequent astronomers found that they could rely on Meyer's data with unusual confidence. Meyer was also deeply interested in the problem of determining longitude at sea, and he devoted considerable effort to developing accurate lunar tables, which would allow navigators to find their position by observing the moon's location relative to the fixed stars, a method known as the lunar distance technique. And his work in this area was recognized by the British Board of Longitude, which awarded a substantial prize to his widow after his death in recognition of the value of his contributions to navigation. The name of James Bradley, who succeeded Halley as Astronomer Royal in 1742, appears frequently in the history of 18th-century astronomy, for Bradley was responsible not only for the discovery of the aberration of light, which we have mentioned earlier, but also for a program of positional observations that resulted in a catalogue of over 3,000 stars, published posthumously and providing a valuable resource for astronomers of subsequent generations. Bradley's catalogue contained the positions of 3,222 stars, observed primarily with the mural quadrant at Greenwich and reduced with care to a common epoch. And while Bradley himself did not live to see the final publication of this work, his observations were preserved and eventually made available to the astronomical community, where they served as an important reference point for studies of stellar motion. allowing later astronomers to compare positions measured decades apart and thereby detect the slow drift of stars across the sky. As the 18th century gave way to the 19th, the tradition of careful star cataloguing continued with the work of Giuseppe Piazzi at the Observatory in Palermo, Sicily, where the Italian astronomer undertook a comprehensive survey of the heavens using a fine altitude and azimuth circle made by the English instrument maker Jesse Ramsden, one of the most skilled craftsmen of his generation, and the resulting catalogue, published in 2 editions in 1803 and 1814, contained the positions of 7,646 stars, observed with a precision that marked a clear advance over earlier work. Piazzi is perhaps best remembered today for his discovery of Ceres, the first of the asteroids, in 1801, but his star catalogue represented an equally important contribution to astronomy, providing a comprehensive survey of stellar positions that could be compared with earlier catalogues to reveal the proper motions of stars. And his work demonstrated the continued value of patient, systematic observation at a time when some astronomers were becoming more interested in the dramatic discoveries of new celestial objects. The practical value of accurate star catalogues for navigation was demonstrated most clearly by the publication of the Nautical Almanac, which began appearing annually in 1767 under the direction of the Astronomer Royal Neville Maskelyne, and which provided navigators with the astronomical data they needed to determine their position at sea, including the predicted positions of the Sun, Moon, and planets, as well as tables of distances between the Moon and certain bright stars that could be used for longitude determination. Maskelyne understood that the accuracy of the Nautical Almanac depended entirely on the accuracy of the underlying stellar positions, and he therefore paid close attention to the work of cataloguers like Bradley and Meyer, incorporating their data into his calculations and ensuring that British navigators had access to the best available astronomical information, and the success of the Nautical Almanac, which remained in continuous publication and was widely used by sailors of many nations, demonstrated the practical importance of the seemingly abstract work of stellar cartography. The concept of the Durchmusterung, or systematic sweep of the heavens, would be developed more fully in the 19th century by Friedrich Argelander and others, who would extend the work of the 18th century cataloguers to include far greater numbers of stars, observed with improved instruments and reduced with more sophisticated mathematical techniques, but the foundations laid by Flamsteed, Locail, Meyer, Bradley, and Piazzi made this later work possible, providing the reference points against which new observations could be compared and the methodological examples that guided subsequent generations. It is worth pausing to appreciate the sheer patience required for this kind of work, the hundreds of nights spent at the telescope, often in cold and uncomfortable conditions, the careful recording of each observation in logbooks that would later be subjected to lengthy mathematical analysis, the constant attention to the calibration and adjustment of instruments, and the years or even decades required to accumulate enough data for a comprehensive catalogue. And when we consider the relatively modest scientific infrastructure of the 18th century, with its limited instruments, its handwritten records, and its calculations performed entirely by human computers working with pen and paper, the achievements of the great cataloguers seem all the more remarkable. Each star in a catalogue represents not just a point of light in the sky, but a small victory over the difficulties of observation, a measurement carefully made and carefully recorded, one among thousands of such measurements that together build up a picture of the heavens as complete and accurate as human effort can make it. And as you settle more comfortably now, letting your breathing slow and your thoughts drift gently, you might imagine these patient astronomers at their work, night after night, adding one more star to the great accumulating record of the fixed points of light that will overhead, constant and reassuring in their appointed places. The catalogues they produced were not exciting documents in any conventional sense, being essentially long lists of numbers giving the celestial coordinates of each star, its brightness, and perhaps some notes on its color or variability. But within these dry columns of figures lay information of profound importance, the raw material from which later astronomers would deduce the motions of stars, the structure of our galaxy, and ultimately the nature and extent of the universe itself, though the cataloguers themselves could hardly have imagined the uses to which their data would eventually be put. And so the work continued, year after year and decade after decade, as observatories across Europe contributed their share of observations to the growing body of stellar cartography, and as the techniques of observation and calculation were gradually refined, and as the great 18th-century star catalogues took their places on the shelves of astronomical libraries, ready to serve the needs of navigators plotting their courses across unknown seas, and ready too to serve the needs of astronomers yet unborn, who would find in these patient accumulations of data the keys to understanding that the stars themselves are not truly fixed, but move slowly through the depths of space, carrying our own sun and its family of planets along with them on a journey whose destination we are only now beginning to comprehend. And so we come now to one of the quieter triumphs in the history of astronomy, a measurement so delicate and so long sought that when it finally arrived, in the year 1838, it seemed almost impossibly gentle in its announcement, a soft confirmation of something astronomers had suspected and hoped for across more than 2 centuries of patient watching. This is the story of stellar parallax, the tiny apparent shift in a star's position that occurs as our Earth travels around the Sun, and of the 3 astronomers who, working independently at observatories scattered across Europe and the southern tip of Africa, finally captured this elusive quantity within the span of a single remarkable year. To understand why this measurement mattered so deeply, and why it had resisted the efforts of so many brilliant observers for so long, we must first picture the geometry involved, which is really quite straightforward in principle even as it proved extraordinarily difficult in practice. As the Earth orbits the Sun, completing its yearly circuit through space, any nearby star should appear to shift very slightly against the far more distant background of other stars, much as a nearby tree seems to move against distant hills when you shift your head from side to side. The angle of this shift, measured when the Earth stands at opposite ends of its orbit 6 months apart, is what astronomers call the parallax angle, and from this angle, using nothing more complicated than simple trigonometry, one can calculate the actual distance to the star in question. The difficulty, as generations of astronomers discovered to their frustration, is that even the nearest stars are so tremendously far away that these parallax angles are vanishingly small, far smaller than anyone had imagined in the early days of telescopic astronomy. The human eye can just barely distinguish angles of about 1 arcminute, which is 1/60th of a degree, and a skilled observer with a good telescope in the 18th century might hope to measure angles perhaps 100 times smaller than this, down to fractions of an arcsecond. But even the nearest star, as we now know, shows a parallax of less than 1 arcsecond, and most stars visible to the naked eye have parallaxes far tinier still, requiring measurements of almost unimaginable precision. Robert Hooke, that ingenious and sometimes irascible figure of 17th-century English science, made one of the earliest serious attempts to detect stellar parallax in the 1670s, choosing the bright star Gamma Draconis because it passed nearly directly overhead in London, which minimized the troublesome effects of atmospheric refraction. Hooke built a special zenith telescope, pointing straight up through a hole cut in his roof, and watched Gamma Draconis night after night, hoping to detect its tiny wandering. He convinced himself that he had indeed found a parallax, but his measurements were not consistent enough to persuade others, and the star he had chosen, being actually quite distant, showed no parallax that could possibly have been detected with his instruments. James Bradley, the third Astronomer Royal, took up the same challenge in the 1720s, using improved equipment and the same star Gamma Draconis, and while he too failed to find any true parallax, his failure led to a discovery almost as important, the phenomenon called the aberration of starlight, which we discussed in an earlier section of our journey through astrometric history. Bradley's meticulous observations proved that any parallax for Gamma Draconis must be smaller than 1 arcsecond, which already suggested that the stars were far more distant than anyone had comfortably supposed. William Herschel, that tireless observer of the heavens, also searched for parallax in the late 18th century, employing a clever method of comparing the positions of close pairs of stars, reasoning that if one star in a pair happened to be much nearer than the other, it should show a larger parallax shift over the course of a year. Herschel's observations did reveal changes in the relative positions of some double stars, but these changes turned out to result from actual orbital motion of the stars around each other, not from parallax, and so another generation passed without success. By the early 19th century, it had become clear that detecting stellar parallax would require not only the most precise instruments ever constructed, but also a careful choice of target star, one that was likely to be relatively nearby and thus show a measurably larger parallax angle. But how could one know which stars were nearby when the whole point of the exercise was to measure stellar distances for the first time? The answer lay in proper motion, that gradual drift of stars across the sky first detected by Edmund Halley in 1718. Which we explored near the beginning of our story. A star with a large proper motion, moving noticeably against the background stars over years and decades, was likely to be relatively close to us, because a distant star moving at the same actual velocity through space would appear to crawl much more slowly across our field of view, just as a distant aeroplane seems to drift lazily while a nearby bird flashes past. This reasoning led Friedrich Wilhelm Bessel, working at the Königsberg Observatory in what was then Prussia, to focus his attention on a rather faint star in the constellation Cygnus, designated 61 Cygni, which was not particularly remarkable to casual observation but which had been found by Giuseppe Piazzi to have an exceptionally large proper motion of about 5.2 arcseconds per year. This swift movement across the sky, one of the fastest known for any star, suggested strongly that 61 Cygni must be one of our nearer neighbors in space, and Bessel, with the patience and precision for which German astronomy was becoming renowned, set out to capture its parallax once and for all. Bessel was by this time one of the most respected astronomers in Europe, a man who had begun his career as a merchant's apprentice in Bremen before his extraordinary mathematical talents drew him to the study of the heavens. He had already made fundamental contributions to the theory of astronomical instruments and had published meticulous catalogues of star positions, and he understood better than perhaps anyone else alive exactly what precision would be required to succeed where so many had failed. For this task, he acquired a new instrument from the workshop of Joseph von Fraunhofer, the brilliant Bavarian optician whose early death had deprived astronomy of one of its finest craftsmen, and this instrument was a heliometer, a type of telescope specially designed for measuring very small angles with very high precision. The heliometer achieved its remarkable precision through a design feature that may seem counterintuitive at first description, namely a lens that had been carefully cut in half along its diameter, with each half mounted so that it could slide past the other in a precisely controlled manner. When both halves were aligned normally, the telescope functioned as an ordinary refractor, forming a single image of any star at which it was pointed. But when the two half lenses were offset from each other by sliding one past the other, the telescope formed two images of the same field, displaced by an amount proportional to how far the lenses had been moved. By adjusting this offset until the image of one star formed by one half lens exactly coincided with the image of a different star formed by the other half lens, an observer could measure the angular separation between those two stars with extraordinary accuracy, reading the separation directly from the scale that controlled the lens offset. This split-objective design allowed Bessel to measure the position of 61 Cygni relative to nearby background stars night after night over the course of more than a year, building up a careful record of any tiny wobble in the star's position that might reveal the sought-after parallax. The work was painstaking in the extreme, requiring clear skies and steady air, careful calibration of the instrument, and an almost meditative patience as the measurements accumulated slowly through the seasons. Bessel began his systematic observations in the autumn of 1837 and continued through the summer of 1838, always comparing the position of 61 Cygni against the positions of two faint comparison stars in the same telescopic field. By October of 1838, Bessel had gathered enough observations to announce his result with confidence, and in a paper presented to the Berlin Academy of Sciences, he reported a parallax for 61 Cygni of 0.314 arcseconds, with an uncertainty that he estimated as only about 5% of this value. This tiny angle, less than 1/1000th of a degree, was almost too small to visualize, but its implications were staggering, for it meant that even this relatively nearby star was more than 10 light-years from Earth, a distance so vast that light itself, traveling at the fastest speed the universe permits, required more than a decade to make the journey. The modern value for the parallax of 61 Cygni is 0.287 arcseconds, which differs from Bessel's original measurement by less than 10%, a testament to the remarkable quality of his work and the excellence of the Fraunhofer heliometer. But Bessel was not alone in this achievement, and the year 1838 saw not one but 3 independent measurements of stellar parallax announced in quick succession, each from a different observatory and each using somewhat different methods. The story of these parallel efforts, and the gentle priority disputes that followed, adds a human dimension to this technical triumph, reminding us that even in the most rarefied reaches of scientific inquiry, questions of credit and precedence can stir the emotions of those involved. Thomas Henderson, a Scottish astronomer serving as His Majesty's astronomer at the Cape of Good Hope in South Africa, had actually made observations that could have established the parallax of a star several years before Bessel's announcement, but circumstances conspired to delay his analysis and publication until after Bessel's paper had appeared. Henderson had arrived at the Cape Observatory in 1832, at a time when the southern skies were still poorly mapped compared to the northern heavens, and he found himself in a unique position to observe Alpha Centauri, the third brightest star in the night sky and one accessible only from the southern hemisphere. Alpha Centauri, like 61 Cygni in the north, was known to have a large proper motion, nearly 4 arcseconds per year, and Henderson recognized that this made it an excellent candidate for parallax detection. Using the mural circle and transit instrument available at the Cape, he made a series of careful observations during 1832 and 1833, measuring the position of Alpha Centauri at different times of year when the parallax effect should shift it in opposite directions. But Henderson was plagued by doubts about the quality of his instruments, which were older and less refined than he might have wished. And when he returned to Britain in 1833 to take up the position of Astronomer Royal for Scotland, he set his Cape observations aside, uncertain whether they were precise enough to support any definite conclusions. It was only after news of Bessel's successful measurement reached Edinburgh that Henderson was prompted to revisit his old observations, and upon careful analysis he found that they did indeed reveal a parallax for Alpha Centauri, one that was actually larger than Bessel's result for 61 Cygni. Henderson announced his measurement of approximately 1 arcsecond in January of 1839, just a few months after Bessel's publication, and subsequent refinement of his data suggested a value closer to 0.9 arcseconds. The modern parallax of Alpha Centauri is 0.747 arcseconds, making it the nearest bright star to our solar system, and Henderson's measurement, though less precise than Bessel's, was in reasonable agreement with this value. The question of who deserved credit for the first measurement of stellar parallax became a matter of some delicacy in the astronomical community. Henderson's observations had been made earlier than Bessel's, during 1832 and 1833 compared to 1837 and 1838. But Henderson had not analyzed or published his results until after Bessel's announcement had appeared. Bessel, with characteristic generosity, acknowledged Henderson's early work and never sought to diminish his contribution, recognizing that the Scotsman had faced more difficult circumstances and less reliable instruments. The consensus that emerged, and which has generally been maintained by historians of astronomy since, gives Bessel the priority for the first published and fully convincing measurement of stellar parallax, while acknowledging Henderson's independent achievement and the possibility that he might have claimed the prize had he been more confident in his data. A third measurement further complicated the picture of priority, for Friedrich Georg Wilhelm Struve, working at the Dorpat Observatory in what is now Tartu, Estonia, had also been pursuing stellar parallax during these same years and announced his own result in the autumn of 1838, just weeks after Bessel's publication. Struve was a distinguished astronomer from a family that would produce generations of prominent scientists, and he had access to one of the finest refracting telescopes then in existence, a 9-inch Fraunhofer refractor that was the largest in the world at the time of its installation. Struve chose to observe Vega, the fifth brightest star in the sky and the brightest in the northern celestial hemisphere during summer months, partly for its brightness which made precise observation easier, and partly because some earlier measurements had suggested it might show a detectable parallax. His observations extended back to 1835, and by 1837 he had published a preliminary parallax value, though he acknowledged considerable uncertainty in this early result. His refined measurement, announced formally in 1838, gave a parallax of about 0.26 arcseconds for Vega, which is actually somewhat larger than the modern value of 0.13 arcseconds, suggesting that systematic errors affected his observations more than they affected Bessel's. The three measurements together, announced within months of each other after more than a century of failed attempts, represented a watershed moment in human understanding of the cosmos. For the first time, astronomers could point to specific stars and state with confidence how far away they actually were, not in relative terms or theoretical estimates, but in concrete units that could be compared to the known dimensions of the solar system. The distances revealed were almost incomprehensibly vast, dwarfing everything that had come before in human experience of space, and yet they represented only the very nearest stars. the closest neighbors to our Sun in a galaxy containing hundreds of billions of more distant suns. The significance of these measurements extended far beyond mere curiosity about stellar distances, for they provided the first solid rung on what astronomers would come to call the cosmic distance ladder, the chain of overlapping techniques by which we eventually measured the scale of the entire observable universe. Each subsequent method of distance measurement, from the brightness of Cepheid variable stars to the redshifts of distant galaxies, ultimately traces its calibration back to these first parallax measurements of 1838, making Bessel, Henderson, and Struve the foundation upon which all modern cosmological distances rest. The techniques pioneered in this race to measure parallax continued to improve throughout the 19th century and beyond, with larger telescopes and more sensitive instruments pushing the measurable distance ever outward. Photographic plates, introduced to astronomy in the latter half of the 19th century, allowed parallax measurements to be recorded permanently and compared with great precision, and by the early 20th century, astronomers had accumulated parallax values for several thousand nearby stars. Each measurement required at least a year of observations, often more, to capture the full parallactic motion as the Earth completed its orbit, and the process remained laborious and time-consuming throughout the era of ground-based observation. But for tonight, we may let these numbers and names settle gently into the background of our thoughts, knowing that somewhere above us, if the sky is clear, the stars that Bessel and Henderson and Struve observed so carefully are still drifting slowly across their ancient paths, their parallax shifts too small for any unaided eye to perceive, yet real and measurable and profoundly meaningful. The light reaching us from 61 Cygni tonight left that star more than 11 years ago, and the light from Alpha Centauri departed just over 4 years in the past. And in these simple facts of distance and time we find a connection to those patient observers of nearly 2 centuries ago, who first taught us how far away the stars truly are, and in doing so, expanded our conception of the universe beyond anything that previous generations could have imagined. The heliometer stands as one of the most elegant and precise instruments ever devised for the measurement of small angles in the sky. And its story begins in the middle of the 18th century with a French scientist named Pierre Bouguer, who in 1748 conceived of a clever optical arrangement that would allow astronomers to measure the apparent diameter of the Sun with greater accuracy than had previously been possible. Bouguer understood that the human eye, even when aided by a telescope, struggles to judge the exact edges of a bright disk like the Sun, and he proposed that if one could somehow bring 2 images of the solar limb together within the same field of view, the observer might align them with far greater precision than could be achieved by simply watching the Sun drift across a graduated scale. This principle of comparison, of bringing 2 images into a measurable relationship with one another, would prove to be the foundation upon which all subsequent heliometer design would rest. And though Bouguer himself did not live to see his concept fully realized in practical form, his insight planted a seed that would flower over the following decades. It was John Dolland, the English optician who had achieved fame for his development of the achromatic lens, who in 1754 constructed the first practical heliometer based on Bouguer's principle. Dolland's approach was both simple and ingenious, for he took the objective lens of a telescope and divided it into 2 halves along a diameter, mounting each half so that it could slide past the other in a direction perpendicular to the optical axis. When the 2 halves were aligned perfectly, the instrument behaved as an ordinary telescope, but when one half was displaced relative to the other, 2 separate images of whatever object lay in the field would appear, offset from one another by an amount that corresponded precisely to the displacement of the lens halves. by carefully measuring how far the lens halves had been moved when the two images were brought into a particular alignment. The observer could determine angular separations in the sky with remarkable accuracy. The name heliometer, meaning sun measurer, reflected the instrument's original purpose, which was to track the slight variations in the apparent size of the Sun throughout the year as the Earth moved closer to and farther from it in its elliptical orbit. The early heliometers were relatively modest instruments, suitable for solar work but not yet capable of the extreme precision that would later make them famous among stellar astronomers. The optical quality of lenses in the mid-18th century, while improving steadily, still introduced enough aberrations and distortions to limit what could be achieved, and the mechanical systems for measuring the displacement of the lens halves were not yet refined to the necessary degree. Nevertheless, astronomers recognized the potential of the heliometer principle, and throughout the latter decades of the century, various craftsmen and instrument makers experimented with improvements to both the optical and mechanical components. The instrument remained something of a specialty tool, overshadowed by the transit instruments and mural quadrants that dominated positional astronomy in the great observatories of the era. The transformation of the heliometer from a useful but limited device into a precision instrument of the highest order came about through the extraordinary skill of Joseph Fraunhofer, the Bavarian optician whose mastery of lens making has rarely, if ever, been equaled. Fraunhofer, who had begun his career as a poor apprentice in a mirror-making workshop and who taught himself the principles of optics through diligent study, possessed an almost intuitive understanding of how to grind and polish glass to achieve the most perfect surfaces. His telescopes and other optical instruments, produced at the Optical Institute he directed in Benedict Boyen and later in Munich, were recognized throughout Europe as representing the finest work available, and astronomers competed eagerly for the privilege of acquiring his creations. When Friedrich Wilhelm Bessel, the director of the Königsberg Observatory in Prussia, sought an instrument capable of measuring stellar parallax, that elusive quantity that had escaped detection for so many centuries, he turned to Fraunhofer to construct a heliometer of unprecedented quality. The heliometer that Fraunhofer built for Königsberg, completed in 1829, represented the culmination of decades of refinement in both optical and mechanical design. Its objective lens measured 6 2/10 inches in aperture, which may sound modest by the standards of later telescopes but which at the time represented a substantial instrument, and Fraunhofer ground this lens with such perfection that its images were essentially free from the color fringes and distortions that plagued lesser objectives. The lens was divided along a precise diameter, and each half was mounted on a sliding mechanism of such smoothness and accuracy that the observer could adjust the displacement with complete confidence that the measurement would be reproducible. A precision micrometer allowed the position of the lens halves to be read to extraordinarily fine divisions, and the entire instrument was mounted on a stable equatorial stand that could track the apparent motion of the stars across the sky. Fraunhofer, sadly, did not live to see his masterpiece put to its greatest use, for he died in 1826 at the age of only 39, his health likely damaged by the years of exposure to the toxic chemicals used in glass making. Bessel received the Königsberg heliometer and immediately set about learning its capabilities and limitations through a systematic program of careful observations. The optical principle that made the heliometer so powerful for angular measurement was straightforward enough to understand, though putting it into practice required patience and skill. When observing two stars that lay relatively close together in the sky, the astronomer would adjust the displacement of the lens halves until the image of one star produced by the first half of the objective fell precisely upon the image of the other star produced by the second half. At this point, the images would appear to merge into a single point of light, and the displacement recorded on the micrometer would give a direct measurement of the angular separation between the two stars. The beauty of this technique lay in its differential nature. For any slight trembling of the atmosphere, any small guiding errors in the telescope mount would affect both images equally and thus would not corrupt the measurement of their relative position. The heliometer could be rotated about its optical axis to make measurements along different position angles, and this capability proved essential for determining not merely the separation between two stars but also the direction from one to the other. A complete measurement of the relative position of two stars required observations at multiple position angles, typically 4 or more, with the instrument rotated by 90 degrees between each set. The observer would record the micrometer readings at each orientation, and later, in the warmth of the computing room, these readings would be combined through a process of reduction that accounted for various instrumental effects and yielded the true angular separation and position angle. This procedure was laborious and time-consuming, and a single night's work might yield only a handful of complete position measurements, but the results achieved a precision that no other instrument of the era could match. In the hands of a skilled observer working with a fine heliometer, angular measurements could achieve a precision of approximately 1/100th of an arcsecond, which is to say 1/3600th of a degree, a quantity so small that it defies easy comprehension. To place this figure in some perspective, one might note that the full moon spans about half a degree in the sky, or roughly 1800 arcseconds, and thus the heliometer could detect shifts 180,000 times smaller than the lunar disk. Such precision demanded perfect attention from the observer, who had to judge the exact moment when the two stellar images merged most completely, and it required atmospheric conditions that were steady enough to produce sharp, well-defined points of light. On nights when the air was turbulent, causing the stars to dance and shimmer, meaningful heliometer work was simply impossible, and the astronomer would close the dome and wait for better conditions. The original purpose of the heliometer, the measurement of the solar diameter, continued to be served by instruments of this type, and the data they gathered contributed to our understanding of whether the Sun varies in size over time. Heliometers also proved valuable for tracking the positions of asteroids, those small bodies that had been discovered in increasing numbers since the beginning of the 19th century and whose orbits required careful determination. But it was for the measurement of stellar parallax that the heliometer achieved its greatest fame, and it was Bessel, working with Fraunhofer's Königsberg instrument, who in 1838 announced the first reliable detection of this long-sought quantity for the star 61 Cygni. That achievement opened a new chapter in astronomy, and the heliometer was recognized as the instrument that had made it possible. Following Bessel's success, other observatories acquired heliometers with the intention of extending parallax measurements to additional stars, and the decades that followed saw a steady accumulation of distance determinations using this technique. The work was slow, for each parallax required observations spanning at least a full year to capture the entire cycle of the Earth's orbital motion, and careful attention to all the sources of systematic error that might corrupt the results. The number of parallaxes measured by heliometer methods grew from a handful in the 1840s to several dozen by the 1870s, representing the foundation upon which our knowledge of stellar distances was built. Each measurement was the product of many nights of patient observation, many hours of computation, and a deep familiarity with the instrument's behavior under varying conditions. Among the most productive heliometer programs of the later 19th century was that conducted at the Royal Observatory at the Cape of Good Hope under the direction of David Gill. Gill, a Scottish astronomer who had previously used heliometer observations of Mars to refine the solar parallax, was appointed Her Majesty's astronomer at the Cape in 1879 and immediately recognized the potential for Southern Hemisphere parallax work using the fine heliometer that the observatory possessed. The Cape heliometer was an excellent instrument, and Gill brought to its use a combination of observational skill and organizational energy that produced results far exceeding what had previously been achieved. Working through the 1880s, Gill and his assistants measured parallaxes for numerous southern stars, many of which had never been studied in this way owing to their invisibility from northern observatories. The observing technique that Gill employed was refined through years of experience until every unnecessary motion was eliminated and every measurement was made with maximum efficiency. The observer would settle into position at the eyepiece, adjust the instrument to the first position angle, and make a series of settings of the micrometer while an assistant recorded the readings. Then the heliometer would be rotated to the next position angle, and the process repeated. On a good night, with steady air and clear skies, a skilled observer might complete measurements for several star pairs, but more often the work proceeded slowly, interrupted by passing clouds, by moments of poor seeing, or by the simple fatigue that attended hours of concentrated visual effort. Gill's dedication to this program, and his ability to inspire similar dedication in his staff, made the Cape Observatory a leading center for parallax research during this period. Another notable heliometer was that installed at the Yale Observatory Station in Johannesburg, South Africa, where the clear skies and stable atmosphere provided excellent conditions for precision astrometry. The Yale heliometer contributed additional parallax measurements for southern stars, extending the reach of this technique to regions of the sky that complemented the work being done at the Cape and at northern observatories. The accumulated body of heliometer parallaxes, though never large by later standards, represented the most reliable distance information available for nearby stars and served as the calibration against which other, less direct methods could be tested. The dominance of the heliometer in parallax work persisted through the latter decades of the 19th century. But by the 1890s and into the early 20th century, photographic methods began to offer a serious alternative. Photography possessed the great advantage of recording the positions of many stars simultaneously on a single plate, allowing the observer to measure the target star's position relative to a whole field of reference objects rather than just one or two comparison stars. Photographic plates also provided a permanent record that could be measured and remeasured at leisure, without the pressure of real-time observing, and the measurements could be made in daylight by technicians who need not possess the exceptional visual acuity required for heliometer work. These advantages, combined with steady improvements in photographic emulsions and measuring machines, gradually shifted the balance of preference away from the heliometer. Yet the heliometer did not disappear overnight, for astronomers recognized that it offered certain capabilities that photography could not easily match. The precision achievable with a fine heliometer in good conditions remained competitive with photographic methods well into the 20th century, and for certain specialized applications, such as the measurement of double star separations or the determination of asteroid positions relative to nearby stars, the heliometer continued to find use. The instrument represented a perfected form of visual measurement, the culmination of 2 centuries of refinement in telescope optics and mechanical design, and those who had mastered its use were understandably reluctant to abandon it entirely. The heliometer also played an important role in observations of transits and occultations, events in which one celestial body passes in front of another as seen from Earth. The ability to measure small angular separations with great precision made the heliometer valuable for determining the exact moments when such events began and ended, and these timings contributed to the refinement of orbital parameters for planets and satellites. The instrument's versatility, combined with its established record of reliability, ensured that it remained part of the astronomer's toolkit even as photographic methods came increasingly to dominate routine positional work. In reflecting upon the heliometer and its contribution to astronomy, one is struck by the intimate relationship between observer and instrument that this technique required. Unlike later methods that interposed layers of technology between the astronomer and the sky, heliometer observation placed the human eye and the human judgment at the very center of the measurement process. The observer had to learn the instrument's personality, its small quirks and idiosyncrasies, the way it behaved on warm nights versus cold ones, the slight flexures that occurred as it was pointed to different parts of the sky. This knowledge came only through long experience, and the best heliometer observers were those who had devoted years of their careers to mastering the technique. The precision of 1/100th of an arcsecond that skilled observers achieved with fine heliometers represented the practical limit of what human vision could accomplish when aided by the best optical technology of the age. This limit arose from the fundamental nature of light itself, from the turbulence of the atmosphere, and from the physiological capabilities of the eye, and no amount of refinement in instrument design could push beyond it by any large factor. To achieve still greater precision, astronomers would eventually need to find ways of averaging over the atmospheric disturbances, of recording positions in forms that could be measured with mechanical rather than visual methods, and of observing from locations where the air itself was thinner and steadier. These developments lay in the future, and when they came, they would transform astrometry in ways that the heliometer astronomers could scarcely have imagined. But for nearly a century, from Bessel's first parallax in 1838 to the widespread adoption of photographic methods in the early 20th century, the heliometer stood as the instrument of choice for the most demanding angular measurements in stellar astronomy. Its elegant optical principle, its mechanical precision, and its proven capability in skilled hands made it the natural choice for any observation where accuracy was paramount. The distances to nearby stars, those fundamental quantities upon which so much else depends, were first established through the patient work of heliometer observers, and their measurements provided the foundation upon which later generations would build. And so we come now to a particularly gentle topic, one that concerns itself with the quiet work of establishing where exactly the stars are, not in any casual or approximate sense, but in a manner so careful and so precise that astronomers across the world, working in different cities and under different skies, could agree with one another about the positions of celestial objects to within tiny fractions of a degree. This is the story of fundamental reference frames, and of the patient efforts of many individuals over many decades to create catalogues of stars whose positions could serve as the foundation for all other measurements in the sky. It is, in many ways, a story about coordination and cooperation, about the slow accumulation of data, and about the meticulous correction of errors that crept into observations from sources both known and unknown. To understand why such work was necessary, we might first consider what it means to specify where a star is located. When we say that a star lies at a certain position in the sky, we are describing its location relative to an imaginary framework, a kind of celestial grid that astronomers have agreed to use. This framework is defined by two fundamental reference points: the celestial equator and the vernal equinox. The celestial equator is simply the projection of Earth's own equator onto the sky, an imaginary great circle that divides the northern celestial hemisphere from the southern one. The vernal equinox, meanwhile, is the point where the Sun appears to cross the celestial equator moving northward in the spring, and this point serves as the origin from which positions are measured along the equator. Together, these two elements define a coordinate system, much like latitude and longitude on Earth, but applied instead to the sphere of the heavens. The difficulty, of course, is that neither the equator nor the equinox is marked by any visible object. They must be determined through observation, by watching the motions of the Sun and planets against the background of stars, and by carefully measuring the positions of stars themselves as Earth rotates and orbits. This determination is not straightforward, because the equator and equinox are themselves in slow but constant motion, drifting gradually due to the wobble of Earth's axis known as precession, and subject as well to smaller perturbations called nutation. To establish an accurate reference frame, astronomers needed to observe certain stars with great care, measuring their positions in an absolute sense rather than merely relative to other stars, and then to track how those positions changed over time. These special stars, observed with the utmost precision and used to anchor the entire system of celestial coordinates, came to be known as fundamental stars. The catalogues that listed the positions of fundamental stars were called fundamental catalogues, and they occupied a special place in the hierarchy of astronomical data. Unlike ordinary star catalogues, which might list positions measured relative to other stars or derived from photographic plates, fundamental catalogues aimed to provide absolute positions, tied directly to the equator and equinox through observations of the Sun, Moon, and planets. The positions of these fundamental stars then served as reference points for all other astronomical work, allowing observers to calibrate their instruments and to place newly discovered objects on the same coordinate grid. One might think of fundamental stars as the fixed points on a map, the cities and landmarks from which all other distances are measured. In the latter decades of the 19th century, two figures emerged as central to the development of fundamental catalogues, and their work would shape astrometry for generations to come. The first of these was Simon Newcomb, a Canadian-American astronomer who spent most of his career at the United States Naval Observatory in Washington. Newcomb was a man of remarkable mathematical ability and tireless industry, and he devoted much of his professional life to the improvement of astronomical constants and reference systems. Beginning in the 1870s and continuing into the 1890s, Newcomb undertook a comprehensive revision of the fundamental data underlying the American Ephemeris and Nautical Almanac, the official publication that provided astronomers and navigators with the predicted positions of celestial bodies. Newcomb's work involved not only the recalculation of the orbits of the Sun, Moon, and planets, but also the establishment of a new system of star positions that would serve as the foundation for these calculations. He gathered observations from multiple sources, carefully analyzed the systematic errors present in different datasets, and produced a catalogue of fundamental star positions and proper motions that represented the best available knowledge of the time. His system of astronomical constants, including the precise values of precession and other quantities needed to transform positions from one epoch to another, was adopted internationally and remained the standard for much of the 20th century. Newcomb's approach was characterized by a deep concern for consistency and accuracy, and by a willingness to undertake laborious calculations that would have deterred less determined individuals. Across the Atlantic, in Germany, a parallel effort was underway, led by the astronomer Arthur Auwers. Ours had made his reputation through careful work on star positions and proper motions, and he was keenly aware of the need for an authoritative catalogue that could serve as the basis for all positional astronomy. In 1879, Ours published what he called the Fundamental Catalogue, a collection of precisely determined positions for a selected set of stars. This catalogue, sometimes referred to as the FC to distinguish it from later versions, represented the first in what would become a long series of fundamental catalogues produced under German auspices. Ours understood that the creation of a fundamental catalogue was not a task that could be completed once and then forgotten. The positions of stars change over time due to proper motion, the slow apparent drift of each star across the sky resulting from its actual motion through space. Moreover, the reference frame itself, defined by the equator and equinox, shifts gradually due to precession, and the observations used to establish star positions are always subject to systematic errors that may only become apparent when new data are gathered. For these reasons, fundamental catalogues needed to be revised periodically, incorporating new observations and correcting for newly discovered sources of error. The fundamental catalogue that Ours initiated in 1879 was thus the beginning of an ongoing project, one that would be taken up by successive generations of astronomers. The Berlin Academy der Wissenschaften, the Prussian Academy of Sciences, played an important role in coordinating these efforts and in fostering international cooperation. Astrometry, perhaps more than any other branch of astronomy, depended on the combination of observations from many different observatories, each contributing data that could be compared and merged to produce results more accurate than any single institution could achieve alone. The Berlin Academy provided institutional support for the Fundamental Catalogue project and helped to establish standards that observatories in different countries could follow. This coordination was essential, because one of the greatest challenges in creating a fundamental catalogue was the presence of systematic errors that varied from one observatory to another. Systematic errors are those that affect all observations made with a particular instrument or at a particular location in a consistent way, shifting them in a particular direction rather than scattering them randomly. Such errors might arise from imperfect knowledge of the instrument's alignment, from atmospheric refraction that bent starlight by slightly different amounts than expected, from errors in the clock used to time observations, or from any number of other sources. Because these errors were consistent within a given observatory's data, they were difficult to detect and remove. Only by comparing observations from multiple observatories, each with its own set of systematic errors, could astronomers hope to identify and correct these biases. The Fundamental Catalogue project thus required not only careful observation but also careful analysis, sifting through data to separate the true positions of stars from the artifacts introduced by instruments and circumstances. As the 20th century began, the work of maintaining and improving fundamental catalogues continued. The original fundamental catalogue of Ours was revised and updated, leading to successive versions known as the FK2 and eventually the FK3. The FK3, completed in 1937, was the work of August Kopf, a German astronomer who carried on the tradition established by Ours. Kopf's catalogue contained positions and proper motions for 1,535 stars, each of which had been observed with great care and whose positions had been determined in the fundamental system. These stars were distributed across the sky in such a way that observers anywhere on Earth could find suitable reference points for their work. The distinction between fundamental stars and the stars listed in secondary catalogues is worth pausing to consider, as it helps to clarify the structure of positional astronomy in this era. Fundamental stars were those whose positions had been determined absolutely, through direct observations tied to the equator and equinox. Their positions anchored the reference frame and provided the standard against which all other measurements could be compared. Secondary catalogues, by contrast, contained stars whose positions had been measured relative to the fundamental stars or derived from photographic observations calibrated against them. These secondary catalogues could include many more stars, sometimes hundreds of thousands, but their accuracy depended ultimately on the accuracy of the fundamental stars used as reference points. One important series of secondary catalogues was the Astronomische Gesellschaft catalogue, often abbreviated as the AGK. The Astronomische Gesellschaft, or Astronomical Society, was a German organization that coordinated large-scale observing programs, dividing the sky into zones and assigning each zone to a particular observatory for systematic observation. The resulting catalogues, of which there were several versions produced over the decades, provided positions for large numbers of stars and served as a valuable resource for astronomers studying stellar motions and distributions. The AGK catalogues were tied to the fundamental system through the positions of the fundamental stars they contained, ensuring that their data could be placed on the same reference frame as other positional work. Proper motions became an increasingly important component of fundamental catalogues as the 20th century progressed. Because stars move slowly but steadily across the sky, a position that is accurate at one moment will become slightly inaccurate as time passes. To predict where a star will be at some future date, or to trace where it was at some past date, astronomers need to know not only its current position but also the rate and direction of its motion. Fundamental catalogues therefore included proper motions alongside positions, specifying how each star's coordinates changed over time. The determination of accurate proper motions required observations spanning many years or even decades, and the accumulation of such long baseline data was one of the ongoing tasks of positional astronomy. The equator and equinox, as we have mentioned, are not fixed points but rather move slowly due to the precession of Earth's axis. This motion, discovered by Hipparcos in ancient times and refined by subsequent generations of astronomers, amounts to a slow circular wobble that causes the celestial poles and equator to trace out large circles on the sky over a period of about 26,000 years. In addition to this main precession, there are smaller oscillations called nutation, caused by the gravitational influence of the Moon and Sun on Earth's equatorial bulge. To specify positions accurately, astronomers must account for these motions, transforming positions from the equator and equinox of one date to those of another. The fundamental catalogues provided positions referred to a particular epoch, a specific date for which the equator and equinox were defined, and included the information needed to transform those positions to other epochs. The determination of the equator and equinox from observations was itself a matter of considerable complexity. Astronomers observed the Sun's apparent path across the sky, tracking its position day by day and noting where it crossed the celestial equator at the spring and autumn equinoxes. They observed the planets, whose motions were governed by the same gravitational laws that determined Earth's orbit, and used these observations to refine their knowledge of Earth's orientation in space. They observed stars with great precision, using the resulting data to define the direction of the celestial pole and the plane of the celestial equator. All of these observations were combined, weighted according to their estimated accuracy, and used to establish the reference frame that would underlie all positional astronomy for years to come. The work of Newcomb, Auwers, Kopf, and their many colleagues was characterized by patience and by a willingness to pursue accuracy through incremental improvement. No single observation, however careful, could establish a position with certainty. Only by combining many observations, made over long periods of time and from multiple locations, could the systematic errors be identified and reduced. The fundamental catalogues that resulted from this work were monuments to collective effort, representing the best knowledge that the astronomical community could achieve through cooperation and persistence. As you rest now and let your thoughts drift, you might hold in your mind an image of these astronomers at their telescopes, night after night, year after year, recording the positions of stars with meticulous care. You might imagine the long tables of numbers, the careful comparisons between observatories, the slow refinement of values as new data were added and old errors were corrected. There is something deeply reassuring about this work, this patient accumulation of knowledge, this steady progress toward greater accuracy. The stars themselves move through space on their own courses, indifferent to our efforts. But the framework we have built to describe their positions is a testament to human curiosity and human cooperation, a gentle structure of numbers and measurements that allows us to speak with one another about the heavens. And so the fundamental catalogues continued to evolve, each new version incorporating the latest observations and the most refined techniques. The FK3 of 1937 was followed in later decades by the FK4 and eventually the FK5, each bringing improvements in accuracy and extending the number of stars included. The tradition that ours began and Kopf continued was carried forward by new generations of astronomers, working with new instruments but guided by the same principles of care and precision. The reference frame that these catalogues defined became the foundation for astronomy worldwide, a common language of position and motion that allowed observers in different countries and different centuries to share their knowledge and build upon one another's work. For now, let us simply appreciate the quiet achievement of these fundamental catalogues, the countless hours of observation and calculation that went into their creation, and the way in which they brought order to our understanding of the sky. The stars are very far away, and their positions change only slowly, but the effort to measure those positions with ever greater accuracy has been one of the enduring projects of astronomy. It is a project that continues today, though the methods have changed and the instruments have grown more sophisticated. The spirit of careful measurement and international cooperation that Newcomb and Hours embodied remains at the heart of astrometry, guiding the work of those who still look up at the stars and ask, with gentle persistence, exactly where they are. In the quiet of an observatory on a clear March night in the year 1840, a physician and chemist named John William Draper turned his attention upward toward the moon, that familiar companion to our evenings, and with patience and care he allowed its soft reflected light to fall upon a small plate coated with silver iodide, a substance that would slowly, gradually, over the course of 20 minutes, record what no human hand had ever drawn with such faithful precision. This was New York City, and the moon hung above the young university where Draper worked. And though the city below was growing and changing with each passing season, the moon itself remained as it had always been, pocked and cratered and ancient beyond measure. And now, for the first time in all of human history, its image was being captured not by the interpretive eye of an artist but by the impartial action of light itself upon chemistry. The daguerreotype process was still quite new in those days, having been announced to the world only the previous year by Louis Daguerre in Paris, and already Draper understood that this invention might serve purposes far beyond portraiture and the recording of earthly scenes. The resulting image was small, perhaps 3 inches across, and it showed the lunar surface with its maria and highlands rendered in delicate gradations of tone. And while it may seem modest by the standards of later generations, it represented something profound, a fundamental shift in how humanity might come to know the heavens. The moon, of course, is exceedingly bright compared to the stars, and so it made a natural first subject for these early experiments in celestial photography. The stars themselves, those distant suns scattered across the darkness, presented far greater challenges, for their light is so very faint that the photographic materials of the time struggled to detect them at all. Draper continued his experiments over the years that followed, attempting to capture starlight on his sensitized plates, and though his success with stellar subjects was limited, his work with the moon and later with the solar spectrum established principles that others would build upon in the decades to come. He passed away in 1882, but by then the field he had helped to pioneer was beginning to flourish in observatories across both Europe and America, as improvements in photographic chemistry and telescope design gradually made the photography of stars not merely possible but practical. Across the Atlantic Ocean, in the gentle English countryside not far from London, there stood a modest scientific institution known as Kew Observatory, and it was here during the 1850s that a man named Warren de la Rue undertook pioneering work that would advance the art of celestial photography considerably. De la Rue was a businessman by profession, having made his fortune in the manufacture of stationery and fine papers, but his true passion lay in the sciences, particularly in chemistry and astronomy, and he brought to these pursuits both financial resources and a remarkable ingenuity of mind. At Kew Observatory, de la Rue constructed a reflecting telescope specifically designed for photographic purposes, taking great care to ensure that the optical system would produce sharp images across the entire field of view, and he developed methods for driving the telescope smoothly to follow the apparent motion of celestial objects as the Earth rotated beneath them. This tracking was essential, you see, because photographic exposures of the faint stars required many minutes, sometimes even hours, and during all that time the telescope had to follow its target with the utmost precision, lest the resulting image be smeared and blurred beyond usefulness. De la Rue achieved particular success in photographing the sun and moon, producing images of exceptional clarity and detail, and his work demonstrated that photography could reveal features too fine or too subtle for the human eye to perceive directly through the eyepiece. He also photographed solar eclipses, capturing the delicate structures of the corona and prominences, and through these efforts he helped establish photography as a legitimate tool of astronomical research rather than merely a curiosity or novelty. Meanwhile, in the city of New York, a lawyer and amateur astronomer named Lewis Morris Rutherford was pursuing similar investigations with considerable skill and determination. Rutherford had constructed a private observatory near his home, equipping it with fine instruments that he often modified or improved according to his own careful designs. And beginning around 1858, he turned his attention to the photography of celestial objects with remarkable dedication. Unlike many early experimenters, Rutherford recognized that telescopes designed for visual observation were not necessarily optimal for photography, because the photographic plates of that era were most sensitive to blue and violet light rather than to the yellow and green light to which the human eye responds most strongly. This difference meant that a telescope carefully focused for visual use might produce blurred photographs, and so Rutherford set about constructing telescopes with lenses specifically corrected for the photographic wavelengths, an innovation that significantly improved the quality of his stellar images. Over the course of nearly 2 decades, from 1858 to 1877, he produced photographs of the moon, the Sun, star clusters, and individual stars, and he developed methods for measuring the positions of stars directly from the photographic plates with considerable accuracy. His work represented an important step toward the use of photography as a tool for astrometry, that patient science concerned with determining where exactly the stars reside in the celestial sphere. Now we must turn our attention to Paris, that beautiful city where so much astronomical history has unfolded, and to the observatory that stands on its southern edge, where two brothers named Paul and Prosper Henry labored with quiet diligence through the 1880s on a task that would ultimately transform the practice of star mapping. The Henry brothers had been assigned the demanding work of extending the great star charts that formed the basis of positional astronomy, and their particular responsibility was to map a region of the sky along the ecliptic, that imaginary line marking the apparent path of the Sun through the constellations over the course of a year. The ecliptic zone presented peculiar difficulties, for it passes through regions of the Milky Way where stars cluster so densely that the eye struggles to distinguish individual points of light amid the general glow, and even the most careful visual observer finds it challenging to record their positions accurately. Night after night, the brothers peered through their telescopes, sketching what they saw and noting the locations of stars on their charts. But the work was slow and exhausting, and the results were never quite as complete or as certain as they wished them to be. There were always more stars, fainter stars hovering just at the edge of visibility, and the brothers recognized that human patience and human perception had inherent limits that no amount of dedication could entirely overcome. It was this frustration, this honest acknowledgement of the limitations of visual observation, that led Paul and Prosper Henry to consider whether photography might offer a solution to their difficulties. If a photographic plate could be exposed at the focus of a telescope for a sufficient length of time, they reasoned, it would accumulate light from even the faintest stars, recording their positions with a precision and completeness that no human eye could match. And so the brothers set about designing and constructing a specialized instrument for this purpose, a telescope known as an astrograph, with an aperture of 33 centimeters and optical properties carefully optimized for photographic work. The design required considerable thought and experimentation, for the objective lens had to bring light of the photographic wavelengths to a sharp focus across a flat field of view large enough to capture a useful area of sky, and the mounting had to track the stars with such steadiness that long exposures would yield pinpoint stellar images rather than trails or smears. By 1885, the brothers had achieved success with their instrument, producing photographs of the ecliptic zone that revealed thousands upon thousands of stars, far more than any visual observer could hope to chart in a lifetime of patient work. The advantages were immediately apparent, for not only did the photographs show more stars than the eye could see, but they also provided a permanent record that could be measured and remeasured at leisure, compared with photographs taken at other times, and stored safely for future generations to consult. While the Henry brothers pursued their work in Paris, another development was unfolding in the southern hemisphere that would prove equally consequential for the future of star mapping. In Cape Town, at the Royal Observatory established to survey the southern skies, an astronomer named David Gill had been observing a great comet that appeared in the heavens during September of 1882. This comet was a spectacular object, easily visible to the unaided eye, and Gill arranged to have it photographed against the background of stars, an undertaking that required placing a camera alongside the observatory telescope and tracking the comet as it moved slowly against the fixed stars. The resulting photographs were striking, showing not only the bright head and sweeping tail of the comet but also, unexpectedly, thousands of stars scattered across the background of the image. Gill had not anticipated that so many stars would be recorded, and he recognized at once the implications of this accidental discovery. Here was evidence that photography could capture stellar images far more efficiently than anyone had supposed. That a single photographic exposure of relatively modest duration could reveal stars in such profusion that years of visual observation would be required to match it. The photograph of the 1882 comet became, in a sense, a revelation, demonstrating possibilities that would reshape astronomical practice in the decades to come. Inspired by this success, David Gill began to envision a great international project, a collaborative effort among observatories around the world to photograph the entire sky and thereby create a permanent photographic record of the positions and brightnesses of millions of stars. This vision, which came to be known as the Carte du Ciel, would become one of the most ambitious undertakings in the history of astronomy, drawing together institutions from many nations in a shared endeavor lasting decades. But the Carte du Ciel belongs to a later portion of our story, and for now it is enough to note that Gill's photograph of the comet served as a kind of spark, igniting interest in astrophotography as a tool for systematic star mapping among astronomers who had previously regarded it with skepticism or indifference. The advantages that photography offered to the practice of astrometry were substantial and manifold, and it is worth pausing to consider them in some detail. First, and perhaps most importantly, a photograph is objective in a way that no human observation can be. When an astronomer peers through a telescope and notes the position of a star, that observation is filtered through the peculiarities of human perception, through fatigue and distraction and the subtle biases that affect even the most careful observer. Different astronomers might record slightly different positions for the same star, and the same astronomer might record different positions on different nights depending on conditions and state of mind. A photographic plate, by contrast, records exactly what the light does, without interpretation or variation, and while the plate itself may have imperfections, these imperfections are consistent and can be characterized and corrected. Second, a photograph provides a permanent record that can be examined and re-examined indefinitely. A visual observation exists only in the notes of the observer, but a photographic plate can be stored in an archive and consulted years or even centuries later, allowing future astronomers to check the work of their predecessors or to discover new phenomena that were recorded but not noticed at the time. Third, and of great practical importance, a photograph captures an entire field of view simultaneously, recording the positions of hundreds or thousands of stars in a single exposure. A visual observer can examine only one star at a time, moving the telescope from point to point and noting each position individually, a laborious process that limits how many stars can be catalogued in a given span of time. Photography transformed this arithmetic dramatically, making it feasible to map the sky with a completeness that would have been utterly impossible by visual means alone. Yet for all these advantages, the early practitioners of astrophotography faced challenges that were sometimes vexing and always demanded careful attention. The photographic emulsions of the 19th century were imperfect materials, subject to irregularities in their thickness and sensitivity that could introduce errors into the measurements derived from the plates. A region of the emulsion that was slightly thicker or more sensitive than its neighbors might record a star as slightly brighter or larger than it truly appeared, and these variations had to be understood and accounted for if the resulting positions were to be trusted. Furthermore, the atmosphere through which astronomers must always observe is not uniform but varies in density and temperature from place to place and moment to moment, bending the paths of light rays in ways that shift the apparent positions of stars. This phenomenon, known as atmospheric refraction, affects all astronomical observations, but it posed particular challenges for photography because long exposures were susceptible to changes in atmospheric conditions over the course of the exposure. A star might drift slightly during the many minutes of an exposure, not because it had truly moved but because the atmosphere had shifted and wavered, smearing its image across a tiny region of the plate. The telescopes themselves introduced additional complications, for no lens or mirror is entirely perfect in its construction, and even small imperfections can produce distortions that vary across the field of view. A star near the center of a photograph might be rendered accurately while a star near the edge might be slightly displaced from its true position, stretched or shifted by the optical properties of the instrument. These distortions had to be measured and characterized for each telescope and each photographic plate, a painstaking process that required careful analysis and extensive calibration against stars whose positions were already known with precision. The development of mathematical techniques for correcting these distortions became an important part of the astrographic enterprise, as astronomers sought to extract the maximum accuracy from their photographic records. Despite these challenges, the fundamental promise of photography was clear, and by the late 1880s, the astronomical community had begun to embrace it with increasing enthusiasm. The old methods of visual observation would not disappear overnight, for many observatories lacked the resources or expertise to adopt the new techniques, and there remained certain kinds of work for which the trained human eye still held advantages. But the direction of progress was unmistakable. Photography offered a path to catalogues of unprecedented size and precision, to systematic surveys of the entire sky that would reveal the true distribution of stars in the heavens, and to a kind of astronomical archive that would preserve the state of the sky for all future generations to study. The brothers Henry in Paris, David Gill in Cape Town, Louis Rutherford in New York, and Warren de la Rue at Kew had all contributed to this transformation in their various ways, and though each worked in relative isolation, focused on particular problems and particular instruments, their collective efforts marked a turning point in the long history of humanity's attempts to understand our place among the stars. The sky above, that patient vault of darkness and light, had always been there, waiting to be known, and now at last there existed tools capable of knowing it with a thoroughness and permanence that earlier generations could only have imagined. And so the work continued, year after year, plate after plate, as the great project of mapping the heavens entered a new and more powerful phase. In the spring of 1887, as the chestnut trees along the boulevards of Paris were beginning to unfurl their pale green leaves, a gathering of astronomers from across the world made their way to the French capital for what would become one of the most ambitious scientific undertakings of the 19th century. The Astrographic Congress, convened in the month of April at the Paris Observatory, brought together 56 delegates representing 19 different nations, each of them united by a common purpose that seemed, at the time, both thrillingly modern and entirely achievable. They had come to discuss the possibility of photographing the entire sky, every star visible to the new photographic plates, and recording their positions with a precision that would serve astronomers for generations to come. The air in Paris that April was mild, and the delegates who strolled through the observatory grounds between sessions could not have known that they were setting in motion a project that would outlast most of their lifetimes, stretching forward across decades, through wars and revolutions, through the rise and fall of empires, until some portions of the work would only reach completion in the 1960s, nearly 80 years after that hopeful spring gathering. The driving force behind this Congress, and indeed behind the entire conception of the project that would come to be known as the Carte du Ciel, was Admiral Ernest Amédée Barthélemy Mouchez, who served as the director of the Paris Observatory from 1878 until his death in 1892. Mouchez was an unusual figure in the world of astronomy, having spent much of his earlier career not peering through telescopes but rather navigating the oceans as a naval officer, surveying coastlines and producing detailed maritime charts that earned him considerable respect among hydrographers and cartographers alike. This background in precise surveying, in the methodical documentation of geographical features across vast expanses of water and land, shaped his vision of what astronomy might accomplish if only it could be organized with similar systematic thoroughness. When Mouchez turned his attention to the heavens, he brought with him the surveyor's conviction that the universe could be mapped, measured, and catalogued, if only sufficient resources and coordination could be brought to bear upon the task. He had become deeply interested in the potential of photography as a tool for astronomical observation, recognizing that photographic plates could record the positions of stars with a consistency and objectivity that the human eye, peering through an eyepiece and estimating positions against a reticle, could never quite achieve. The congress that Mouchez convened in Paris was not a spontaneous affair but rather the culmination of several years of discussion and preliminary work. Astronomers across Europe had been experimenting with astrophotography since the middle of the century, and by the 1880s it had become clear that photographic techniques had advanced to the point where systematic stellar photography was genuinely feasible. The brothers Paul and Prosper Henry, working at the Paris Observatory under Mouchez's direction, had produced remarkable photographs of star fields that demonstrated just how many faint stars could be captured on a single plate, far more than any visual observer could hope to record in a comparable span of time. These images had circulated among the astronomical community and had generated considerable excitement about the possibilities that lay ahead. Mouchez, with his talent for organization and his diplomatic connections from his naval career, seized upon this momentum and issued invitations to observatories around the world, proposing that they come together to discuss a coordinated international effort that would divide the sky into zones and share the enormous labor of photographing and measuring the positions of millions of stars. The delegates who arrived in Paris that April came from observatories scattered across the globe, representing a remarkable cross-section of the astronomical world of the late 19th century. From Greenwich came representatives of the Royal Observatory, that venerable institution perched on its hill above the Thames, where the prime meridian begins its journey around the Earth. The Paris Observatory itself, of course, was well represented, along with the observatories at Bordeaux and Toulouse, giving France a strong presence in the project that would bear such a distinctly French name. From the Iberian Peninsula came delegates representing the observatory at San Fernando in Spain, while from North Africa came those affiliated with the observatory at Algiers, then under French administration. The observatory at Tacubaya in Mexico sent representatives across the Atlantic, as did the observatories at Santiago in Chile, La Plata in Argentina, and Rio de Janeiro in Brazil, ensuring that the southern skies of the Americas would be included in the Great Survey. The Cape Observatory in South Africa, perched at the southern tip of that vast continent, was represented as well, along with the observatories at Melbourne, Sydney, and Perth in Australia, institutions that would prove essential for covering the deep southern reaches of the celestial sphere that could never be observed from European latitudes. From the northern regions came delegates from Helsinki in Finland and Potsdam in Germany, while from the Mediterranean came representatives of the observatory at Catania in Sicily, ensuring that the project would have truly global participation spanning both hemispheres and multiple continents. One of the most distinctive aspects of the Carte du Ciel project, and one that reflected both the organizational genius of its founders and the practical requirements of international cooperation, was the decision to standardize the equipment that would be used by all participating observatories. The delegates at the Paris Congress agreed that each observatory would construct or acquire an identical telescope, designed according to precise specifications that would ensure the plates produced at Greenwich would be directly comparable to those produced at Melbourne or Santiago or any other participating institution. This standardized instrument, known as the astrograph, was a refracting telescope with an aperture of 33 centimeters and a focal length of 3 meters and 43 centimeters. Dimensions chosen to produce images of a particular scale that would facilitate the measurement of stellar positions. Each photograph taken with this instrument would cover a field of view measuring 2 degrees by 2 degrees, a modest patch of sky that nonetheless contained, in most regions, hundreds or thousands of stars whose positions could be extracted from the photographic emulsion with patient measurement. The decision to use identical instruments was not merely a matter of scientific convenience but also a statement of principle, an assertion that the great work of mapping the heavens would be a truly collaborative effort in which no single observatory would hold a privileged position, and in which the contributions of all participants would be equally valued and directly comparable. The project as conceived at the Paris Congress had 2 distinct but related aims, each requiring its own set of observations and measurements. The first aim was the creation of the Carte du Ciel itself, a comprehensive photographic atlas of the entire sky that would record all stars down to approximately the 14th magnitude, a level of faintness that pushes well beyond what the unaided human eye can perceive, even under the darkest and most favorable conditions. These atlas plates would serve as a permanent visual record of the sky as it appeared in the late 19th century, a kind of celestial snapshot that future generations could consult to identify stars, to trace changes in stellar positions over time, and to discover objects that might have been overlooked in earlier surveys. The second aim was the creation of the astrographic catalogue, a systematic listing of the positions of all stars down to approximately the 11th magnitude, with each position measured from the photographic plates and recorded in numerical form so that astronomers could look up the precise coordinates of any catalogued star without needing to examine the original photographs. The catalogue would be the more immediately useful product for astronomers engaged in positional work, while the atlas would serve as an archival resource and as a tool for identification and discovery. Both products required the same basic observations, the same careful exposures on the standardized astrograph plates, but they differed in the depth to which the stars would be measured and in the form in which the results would be published. The vastness of the task that the Congress had undertaken becomes apparent when one considers how the sky was to be divided among the participating observatories. The celestial sphere was parceled out into zones defined by declination, which is the astronomical coordinate analogous to latitude on the Earth's surface, measuring the angular distance of a celestial object north or south of the celestial equator. Each participating observatory was assigned responsibility for a particular band of declinations, a strip of sky that wrapped entirely around the celestial sphere from east to west but occupied only a limited range of north-south positions. The assignment of zones took into account both the geographical latitude of each observatory, which determined which portions of the sky were accessible from that location, and the resources and capabilities of each institution, which influenced how much of the workload each could reasonably be expected to bear. Observatories in the Northern Hemisphere naturally took responsibility for the northern zones of declination, while those in the southern hemisphere assumed the task of photographing and cataloguing the southern zones. And observatories situated near the equator could contribute to the regions near the celestial equator, where their position offered no particular advantage or disadvantage. The Vatican Observatory, that small but historically significant institution nestled within the ancient walls of Vatican City, joined the Carte du Ciel project in 1891, a few years after the initial Congress but still early enough to take on a meaningful share of the enormous workload. The participation of the Vatican Observatory reflected the universal nature of the project and the willingness of the Catholic Church, under Pope Leo XIII, to engage with modern scientific endeavors and to contribute to the advancement of human knowledge about the cosmos. The zone assigned to the Vatican was a strip of northern sky, and the observatory set about acquiring the necessary equipment and training the personnel who would carry out the painstaking work of photography and measurement. The presence of the Vatican among the list of participating institutions added a certain symbolic weight to the project, suggesting that the mapping of the heavens was an endeavor that transcended national boundaries and religious divisions, uniting all of humanity in the contemplation of the stars that shine down upon every nation and every people. The work itself, once it began in earnest, proved to be far more demanding than even the most cautious estimates had suggested. Each plate had to be exposed with great care, the telescope tracking the apparent motion of the stars across the sky so that their images would remain sharp and undistorted on the photographic emulsion. Multiple exposures were often required to ensure that plates of sufficient quality were obtained, and the vagaries of weather meant that many nights of potential observation were lost to clouds, to humidity, to atmospheric turbulence that blurred the stellar images beyond acceptable limits. Once the plates were obtained, the even more laborious task of measurement began, as technicians and astronomers peered through measuring machines, recording the positions of individual stellar images one by one, converting the positions on the photographic plate to celestial coordinates through a series of mathematical transformations that accounted for the optical characteristics of the telescope, the orientation of the plate, and the effects of atmospheric refraction. The sheer number of stars to be measured was staggering, running into the millions for the complete catalogue, and each measurement had to be performed with care and verified against independent observations to catch the inevitable errors that crept into such repetitive work. As the years passed and the 19th century gave way to the 20th, the Carte du Ciel project continued, though progress was uneven and the initial enthusiasm of the founding Congress gave way to a more sober recognition of the difficulties involved. Some observatories made steady progress through their assigned zones, photographing and measuring with commendable diligence, publishing their results in thick volumes that accumulated on library shelves around the world. Other observatories encountered difficulties, whether through lack of funding, through the departure of key personnel, through the interruptions of war and political upheaval, or through the simple exhaustion that comes from decades of demanding and often tedious work. The First World War disrupted observations at many European institutions, and the economic hardships of the interwar period made it difficult for some observatories to maintain the level of effort that the project required. The Second World War brought further interruptions, and by the time peace returned in 1945, the Carte du Ciel had been underway for nearly 60 years, with significant portions of the sky still unfinished. The outcome of the project, when viewed from the perspective of the present day, must be characterized as incomplete, though this incompleteness should not obscure the genuine accomplishments that were achieved. The Astrographic catalogue, which aimed to record positions for stars down to the 11th magnitude, was largely completed over the course of the project's long history, with the final zones being finished in the 1960s, more than 3/4 of a century after the Paris Congress. This catalogue, comprising millions of stellar positions measured from the standardized astrograph plates, represents an invaluable resource for astronomers studying the motions of stars. For the positions recorded in the late 19th and early 20th centuries can be compared with modern observations to reveal the slow drift of stars across the celestial sphere. The proper motions that accumulate over decades and centuries to shift the familiar patterns of the constellations by imperceptible degrees. The Carte du Ciel itself, the photographic atlas intended to reach down to the 14th magnitude, fared less well, with many zones never completed and the original vision of a comprehensive all-sky photographic survey remaining unrealized. The plates that were produced, and the zones that were completed, nonetheless constitute a precious archive, a record of the sky as it appeared to the astronomers of a century ago, and scholars continue to consult these materials when historical records of stellar positions and brightnesses are required. The legacy of the Carte du Ciel extends beyond the catalogues and atlas plates that it produced, for the project represented a pioneering experiment in international scientific cooperation on a scale that had never before been attempted in astronomy. The concept of dividing a vast scientific task among multiple institutions scattered around the globe, coordinating their efforts through agreed-upon standards and shared methodologies, would become a model for later collaborative projects in astronomy and in other fields of science. The difficulties encountered by the Carte du Ciel, the decades of delay, the zones left incomplete, the challenges of maintaining momentum across generations of scientists, also provided valuable lessons for those who would later organize international scientific endeavors, demonstrating both the possibilities and the pitfalls of such ambitious undertakings. When astronomers in the late 20th century began planning projects like the Hipparcos satellite mission, which would measure stellar positions from above the distorting atmosphere of the Earth, they did so with an awareness of the long history of astrometric surveys, including the hard-won experience of the Carte du Ciel. The observatories that participated in the project, from Greenwich to Melbourne, from Paris to the Cape, from the Vatican to Tacubaya, formed a network of institutions that shared not only a common scientific goal but also a common set of instruments and methods, creating connections across national boundaries that would persist long after the project itself had wound down. The astronomers who devoted years of their careers to the patient work of photography and measurement became part of a community defined by their shared commitment to the Great Survey. And the publications they produced, the thick volumes of coordinates and magnitudes, stand as monuments to their dedication. Many of these astronomers are now forgotten, their names preserved only in the acknowledgements of the catalogues they helped to compile, but their work endures in the data they so carefully gathered. Data that continues to be used by researchers pursuing questions that the original participants could never have imagined. As you settle deeper into the quietness of this moment, you might find it pleasant to imagine one of those observers at their telescope, perhaps at the Melbourne Observatory on a clear winter night in the southern hemisphere. The astrograph pointed toward a zone of the Milky Way dense with stars, the photographic plate gathering light while the clockwork drive keeps pace with the turning Earth. The observer waits patiently, checking the guiding eyepiece from time to time to ensure that the stars remain precisely centered, while the sounds of the night, the rustle of wind in the eucalyptus trees, the distant call of a night bird, fade into the background of consciousness. The exposure complete, the plate is carefully removed and carried to the darkroom for development, where the images of thousands of stars will gradually emerge from the chemical bath. each tiny point of light a record of photons that traveled across the void for years or centuries before falling upon the emulsion. In such quiet moments, repeated countless times at observatories around the world over the span of decades, the Carte du Ciel slowly took shape, one small patch of sky at a time, building toward a vision of completeness that would never quite be achieved but that nonetheless left behind a legacy of enduring value. The zones that were completed in the 1960s, bringing the astrographic catalogue at last to its intended conclusion, were the work of astronomers who had not yet been born when the Paris Congress first conceived the project, demonstrating how scientific endeavors can span the generations, passing from the hands of the founders to those of their successors and eventually to researchers who inherit the work as part of the long tradition of their discipline. The astronomers who completed those final zones did so not out of obligation to the original vision, necessarily, but because the work remained scientifically valuable, because the positions of stars in those neglected zones were still needed for the ongoing study of stellar motions and galactic structure. In this way, the Carte du Ciel, despite its incompleteness, achieved a kind of quiet success, contributing to the accumulating body of astronomical knowledge that each generation builds upon the work of those who came before. And so the Great Survey, conceived in the spring of 1887 by 56 delegates gathered in Paris under the leadership of Admiral Mouchez, unfolded across the better part of a century, touching the lives of astronomers on every continent, filling libraries with catalogues and atlas plates, and demonstrating both the possibilities and the limits of human ambition when turned toward the patient mapping of the heavens. The stars themselves, of course, continued on their ancient courses, indifferent to the efforts of the observers who recorded their positions, drifting imperceptibly across the celestial sphere in accordance with the gravitational forces that govern all motion in the universe. But the record of those positions, captured on photographic plates and published in volumes that now yellow with age, remains as a testament to a remarkable chapter in the history of astrometry, a chapter that began with hope and international cooperation and ended, many decades later, with the quiet satisfaction of work completed, even if that completion came later and in a more modest form than the founders had originally envisioned. As the 19th century progressed, the careful study of stellar positions grew far beyond what any single observatory could accomplish, and astronomers began to understand that mapping the heavens with true completeness would require a cooperative effort spanning continents and hemispheres, with telescopes positioned at locations both north and south of the equator, each contributing its own portion of the celestial sphere to a gradually accumulating whole. The establishment of major observatories during this period represents one of the quieter but more consequential developments in the history of science, as nations invested considerable resources in buildings and instruments and the training of observers, all in service of the patient work of recording where the stars appeared on any given night, and how those positions might change, ever so slightly, over the passage of years and decades. We might begin our gentle survey of these institutions with the founding of Pulkovo Observatory, which came into being in the year 1839 on a modest hill some 19 kilometers south of St. Petersburg in Russia, where the astronomer Wilhelm Struve had been tasked by Tsar Nicholas I with creating what would become one of the finest astronomical facilities in the world. Struve, who had already distinguished himself through decades of careful work at the Dorpat Observatory in what is now Estonia, brought to this new endeavor both his considerable expertise and his exacting standards for instrumental precision, and the result was an observatory equipped with what was then the largest refracting telescope ever constructed, a magnificent instrument with an objective lens measuring 15 inches in diameter, crafted by the renowned Munich firm of Merz and Mahler. This great refractor, mounted beneath the central dome of the observatory's elegant neoclassical building, became the primary tool for Struve's continuing investigations into double stars and stellar positions, and the observations made with it contributed substantially to the growing body of astrometric data that astronomers across Europe were slowly compiling. The location of Pulkovo was chosen with considerable care, for the hill upon which it stands, though not particularly high, offered relatively steady atmospheric conditions and a clear view of the horizon in all directions, qualities that matter greatly when one is attempting to measure stellar positions with the utmost accuracy. Struve organized the work of the observatory according to systematic principles, establishing programs of observation that would continue for many years under consistent methods, and this attention to long-term consistency proved invaluable for detecting the subtle motions of stars that reveal themselves only through the comparison of measurements made decades apart. The observatory also served as an important training ground for the next generation of Russian astronomers, and its influence extended throughout the scientific community of the Russian Empire and beyond, as visitors came to study its methods and instruments, and as its published catalogues found their way into the libraries of observatories around the world. Across the Atlantic Ocean, the United States was developing its own capabilities for astronomical observation, and the United States Naval Observatory in Washington gradually emerged as a significant contributor to the international effort of mapping the heavens. The growth of this institution owed much to the efforts of Matthew Fontaine Maury, who served as superintendent from 1844 to 1861 and who, despite being remembered primarily for his work in oceanography and the study of winds and currents, also oversaw important expansions of the observatory's astronomical programs. Maury recognized that accurate knowledge of stellar positions was essential for the practical work of navigation, which remained the primary justification for naval investment in astronomy, and under his direction the observatory acquired improved instruments and began systematic programs of observation that would yield useful catalogues of star positions. The work of the Naval Observatory continued and expanded in the decades following Maury's tenure, and among the astronomers who made significant contributions there was Asaph Hall, whose patient observations with the observatory's 26-inch refractor led to one of the more notable discoveries of the era, though we mention it here not for any dramatic quality but simply as an illustration of what careful telescopic work could reveal. In August of 1877, Hall detected two small moons orbiting the planet Mars, objects so faint and so close to the bright disk of the planet that they had escaped notice by all previous observers, and he named them Phobos and Deimos after the mythological attendants of the god of war. This discovery, while not strictly a matter of stellar astrometry, demonstrated the quality of the instruments and the skill of the observers at the Naval Observatory, and Hall went on to make many other contributions to positional astronomy, including careful measurements of double stars and determinations of stellar parallax that added to the slowly growing knowledge of stellar distances. While Northern Hemisphere observatories could map the stars visible from their latitudes with ever-increasing precision, a fundamental limitation remained in that roughly half of the celestial sphere lay forever below their horizons, visible only from locations south of the equator. The importance of establishing capable observatories in the southern hemisphere was recognized early, and among the most significant of these institutions was the Royal Observatory at the Cape of Good Hope, situated near Cape Town in what was then a British colony at the southern tip of Africa. This observatory had been founded in 1820, but it was under the directorship of Thomas MacLear, who arrived in 1834 and served until 1870, that it began to make its most substantial contributions to astrometry, as MacLear brought both energy and methodical precision to the task of cataloguing southern stars. MacLear's work included a verification and extension of the measurements made by Nicolas Louis de L'Ocaille during his famous expedition to the Cape in the 1750s, and he also undertook extensive geodetic surveys of the surrounding region, work that required the same sort of careful angular measurements that characterized stellar astrometry. The observatory under his direction produced catalogues of star positions that filled in portions of the sky that northern observers simply could not reach, and this data proved essential for creating a complete picture of the stellar heavens. Following MacLear, the directorship passed to David Gill, who arrived in 1879 and who would prove to be one of the most influential figures in late 19th-century astrometry, bringing new methods and new levels of precision to the work of the Cape Observatory and forging international collaborations that advanced the field considerably. Gill was particularly interested in the determination of stellar parallax and the measurement of solar system distances, and his work on the parallax of Mars and on the distances to nearby stars earned him widespread recognition. He also championed the use of photography in astrometry, recognizing that photographic plates could record the positions of many stars simultaneously and could be measured at leisure after the observation was complete, offering advantages over the traditional method of observing stars one at a time through the eyepiece of a transit instrument. Under Gill's direction, the Cape Observatory became a leader in the emerging field of photographic astrometry, and his enthusiasm for this technique helped inspire the ambitious international project known as the Carte du Ciel, which we will have occasion to discuss in due course. In the Northern Hemisphere, the Royal Observatory at Greenwich continued to hold a position of considerable importance throughout this period, serving not only as a working astronomical facility but also as the keeper of the prime meridian and the arbiter of timekeeping for much of the world. Under the long directorship of George Biddell Airy, who served as Astronomer Royal from 1835 until 1881, the observatory maintained its traditional programs of positional astronomy while also adapting to new developments in instrumentation and methodology. Airy was a meticulous administrator who insisted on systematic procedures and careful record-keeping, and under his guidance the observatory produced regular catalogues of star positions derived from observations made with transit instruments and mural circles of the highest quality. The transit circle that Airy had installed at Greenwich in 1851 defined the exact position of the prime meridian, the line of zero longitude from which positions east and west are reckoned, and this instrument remained in use for fundamental observations for many decades. Airy's approach to observatory management emphasized the reduction and publication of observations, ensuring that the data gathered at Greenwich would be available to astronomers elsewhere, and the annual volumes of Greenwich observations became standard references consulted by researchers around the world. While Airy was sometimes criticized for being overly conservative in adopting new techniques, his insistence on consistency and accuracy ensured that the observations made during his tenure formed a reliable foundation for later work, and the institutional practices he established continued to shape the character of the Royal Observatory long after his retirement. The latter part of the 19th century saw the construction of several large refracting telescopes that expanded the capabilities of observational astronomy considerably, and among these instruments the 36-inch refractor installed at Lick Observatory in California in 1888 represented a significant achievement. Lick Observatory was built on the summit of Mount Hamilton, at an elevation of more than 4,000 feet, a location chosen specifically for its clear skies and steady atmospheric conditions, and the funding for its construction came from a bequest by James Lick, a wealthy California landowner who wished to create a lasting monument to scientific investigation. The Great Refractor, with its lens crafted by the firm of Alvan Clark and Sons, was for a time the largest telescope in the world, and it proved capable of revealing details in celestial objects that smaller instruments could not discern. The astronomers who worked at Lick Observatory used this magnificent telescope for a variety of purposes, including the measurement of double stars, the observation of planetary surfaces, and the spectroscopic analysis of stellar light, and its contributions to astrometry, while perhaps less prominent than its other work, nonetheless added to the store of precise positional measurements upon which the understanding of stellar motions depended. The success of Lick Observatory demonstrated the advantages of situating telescopes at high-altitude sites with favorable atmospheric conditions, a lesson that would influence the choice of locations for many subsequent observatories, and it established California as an important center for astronomical research, a status that the state has retained to the present day. Even larger than the Lick refractor was the great telescope installed at Yaquis Observatory in Wisconsin in 1897, an instrument whose objective lens measured 40 inches in diameter and which remains to this day the largest refracting telescope ever constructed. The funding for Yaquis Observatory came from Charles Yaquis, a Chicago businessman, and the observatory was affiliated with the University of Chicago, representing a model of academic and private partnership in scientific research that would become increasingly common in the 20th century. The 40-inch refractor was the work of Alvan Graham Clark, the son of the founder of the Clark firm, and its immense lens required years of careful grinding and polishing to achieve the optical quality necessary for serious astronomical work. The size of refracting telescopes had effectively reached its practical limit with the Yaquis instrument, for lenses much larger than 40 inches would sag under their own weight and distort the images they produced, and the future of large telescope construction would lie with reflecting instruments whose mirrors could be supported from behind. Nevertheless, the Yaquis refractor served admirably for many decades, contributing to studies of stellar spectra, double stars, and planetary surfaces, and the observatory itself became an important training ground for astronomers who would go on to make significant contributions at institutions across the country. The precision of its mounting and drive systems made it well suited for the sort of careful positional measurements that astrometry required, and observations made with it added to the growing understanding of stellar positions and motions. Beyond the major observatories of Europe and North America, smaller institutions in various parts of the world made contributions to the global effort of mapping the heavens, filling in gaps in coverage and providing observations from locations that offered unique advantages. In Argentina, the Córdoba Observatory was established in 1871 under the direction of Benjamin Apthorpe Gould, an American astronomer who had trained in Germany and who brought both rigor and ambition to this new endeavor in the Southern Hemisphere. Gould recognized that the southern skies had been far less thoroughly mapped than the northern heavens, and he set about systematically cataloguing the stars visible from Córdoba's latitude with the same care and precision that characterized the best European work. The result of Gould's labors, and those of the assistants who worked alongside him, was the Uranometria Argentina, published in 1879, a comprehensive catalogue and atlas of the southern stars that filled a significant gap in astronomical knowledge. Gould observed with the naked eye and with modest telescopes, but his methods were systematic and his standards were high, and the catalogue he produced remained a standard reference for Southern Hemisphere astronomy for many years. The establishment of the Córdoba Observatory represented an important step in extending the global network of astronomical institutions to include South America, and the work done there demonstrated that significant contributions could come from locations far removed from the traditional centers of European science. Colonial observatories established by European powers in their overseas territories also played a role in extending the coverage of astronomical observation, even if their contributions are less well remembered today. The Madras Observatory in India, founded in 1792, was among the earliest of these institutions, and while its primary purposes were practical, relating to surveying and navigation, it also contributed observations of celestial objects visible from its tropical latitude. The observatory at Hong Kong, established in 1883, served similar purposes for the British presence in East Asia, and observatories in Sydney and other Australian cities gradually developed capabilities for serious astronomical work as the 19th century progressed. These colonial institutions often operated with limited resources and small staffs, and their contributions to astrometry were correspondingly modest compared to those of the great European observatories, but they nonetheless added to the global picture of the heavens and provided coverage of portions of the sky that more northerly observatories could not reach. The observers who worked at these distant outposts of science often faced challenges unknown to their colleagues in Europe, including tropical heat, humidity that affected instruments, and the isolation of working far from the centers of scientific communication. Yet they persevered in their careful work of recording where the stars appeared, night after patient night. By the close of the 19th century, this global network of observatories, spanning both hemispheres and including institutions large and small, had accumulated a vast store of positional measurements that documented the locations of hundreds of thousands of stars with ever-increasing precision. The coordination among these institutions remained somewhat informal, with observatories publishing their results independently and astronomers elsewhere incorporating this data into their own analyses as they saw fit. But the foundations had been laid for more systematic international cooperation in the century to come. The patient work of generations of observers, peering through eyepieces or later examining photographic plates, had produced catalogues and charts that mapped the heavens with a thoroughness that earlier astronomers could scarcely have imagined, and this accumulated knowledge formed the basis upon which all subsequent advances in astrometry would build. The story of these observatories is in many ways a quiet one, lacking the dramatic discoveries that capture public attention, consisting instead of the steady accumulation of measurements made night after night, year after year, each observation a small contribution to a larger whole. Yet this patient work, carried out by astronomers whose names are largely forgotten today, created the foundation upon which our understanding of stellar positions and motions rests, and the institutions they built and maintained represent a significant investment by human societies in the careful study of the natural world. As we turn now to consider the collaborative projects that sought to coordinate this global effort more systematically, we carry with us an appreciation for the dedicated observers at Pulkovo and Greenwich, at the Cape and Cordoba, at Lick and Yekes and a dozen other institutions, whose careful measurements made the mapping of the heavens possible. The stars, when we first learn of them, seem to be fixed in their places, unchanging points of light arranged in patterns that our ancestors named and recognized across countless generations. And yet, as we have come to understand through patient observation spanning many human lifetimes, the stars are not truly fixed at all, but are moving through space, each one tracing its own unhurried path across the vast distances of the galaxy. The measurement of these motions, these slow drifts that reveal themselves only through the careful comparison of observations separated by years or decades, became one of the great undertakings of 19th and 20th century astronomy, a task requiring dedication that stretched across individual careers and indeed across generations of astronomers working together in a quiet continuity of purpose. To measure how a star moves across the sky, one must first know with great precision where that star appears at a given moment, and this knowledge requires the patient cataloguing of stellar positions, the creation of reference frameworks against which future observers might detect the subtle shifts that time reveals. It was this understanding that motivated Friedrich Wilhelm August Argelander, a German astronomer working at the Bonn Observatory, to undertake what would become one of the most ambitious cataloguing projects in the history of astronomy, a systematic survey of the northern sky that would record the positions and brightnesses of hundreds of thousands of stars, creating a foundation upon which future generations might build their understanding of stellar motions. Argelander began his great survey in 1859, working with his assistants Eduard Schonfeld and Adalbert Kruger, using a telescope of modest size but employed with extraordinary care and patience. Night after night, weather permitting, they would observe and record, building slowly toward a comprehensive map of the northern heavens. The method they employed was one of visual observation, with one astronomer looking through the eyepiece and calling out positions and estimated brightnesses while another recorded these observations in careful ledgers. This was exacting work, requiring concentration and stamina, yet it proceeded steadily over the course of 3 years until, in 1862, the observations were complete, though the work of reducing and publishing these observations would continue for some time thereafter. The result of this labor was the Bonner Durchmusterung, which translates roughly as the Bonn Survey, a catalogue containing the positions and magnitudes of 324,198 stars visible from the Northern Hemisphere. This number is worth pausing over, for it represents not merely a collection of data points but the fruit of countless hours of careful observation, each star examined and recorded by human eyes, each position determined through the patient reading of graduated circles and the steady tracking of stellar transits across the field of view. The catalogue covered the sky from the north celestial pole down to a declination of 2 degrees south of the celestial equator, providing coverage of the entire sky visible from Bonn and indeed from most Northern Hemisphere observatories. The significance of the Bonner Durchmusterung extended far beyond its immediate utility as a finding chart for astronomers seeking to locate particular stars. Because Argelander and his colleagues had recorded positions with considerable precision for such a vast number of stars, their catalogue provided a baseline against which future observations might be compared, enabling the detection of proper motions for stars whose positions had shifted measurably in the intervening years. This was, in a sense, a gift to the future, a careful record made in the present that would gain value with the passage of time, as subsequent generations of astronomers could measure the same stars and detect shifts too small to have been noticed in any single lifetime of observation. Yet the Bonner Durchmusterung covered only the northern sky, leaving the southern heavens largely unmapped with comparable thoroughness. This gap in coverage was addressed through an international collaboration that would extend over more than 2 decades, producing a complementary catalogue known as the Córdoba Durchmusterung. This southern survey was carried out at the Argentine National Observatory in Córdoba, under the direction of John Macon Tomey, an American astronomer who had come to Argentina to help establish and operate this new observatory situated beneath the southern stars. The Córdoba Durchmusterung began in 1892 and continued until 1914, a span of 22 years during which observers at the Argentine station systematically recorded the positions and brightnesses of stars in the southern sky. The completed catalogue extended coverage from 10 degrees south of the celestial equator all the way to the south celestial pole, providing for the southern hemisphere what Argelander had provided for the north. When combined, the two Deutsche Musterung catalogues offered astronomers a comprehensive inventory of the stars visible to the naked eye and many fainter ones besides, a foundation for proper motion studies that now spanned the entire celestial sphere. While these great catalogues provided the positional baseline necessary for detecting stellar motions, the actual measurement of proper motions required sustained effort over many years, comparing stellar positions determined at different epochs and carefully accounting for the many sources of error that might masquerade as genuine stellar motion. It was to this task that Louis Boss, an American astronomer, dedicated much of his career, eventually producing a catalogue that would remain a standard reference for decades. Boss began his proper motion work at the Dudley Observatory in Albany, New York, and continued it throughout his life with a patience and thoroughness that the work demanded. His method involved gathering all available position measurements for each star from various catalogues and observational records, spanning as many years as possible, and then deriving from these data a best estimate of the star's motion across the sky. This was painstaking work, requiring not only mathematical skill but also careful judgment about the reliability of different observations and the proper weighting to give each measurement in the final analysis. The result of this lifetime of labor was published in 1937 as the General Catalogue of 33,342 stars for the epoch 1950, often known simply as the Boss General Catalogue or by the abbreviation GC. This catalogue provided positions and proper motions for its 33,000 stars, giving astronomers a carefully vetted reference list of stellar motions against which they might calibrate their own observations or upon which they might base their studies of galactic structure and dynamics. The number of stars was smaller than in the Deutsche Musterung catalogues, but the precision of the proper motions was considerably higher, reflecting the careful analysis that had gone into deriving each value. Alongside these cataloguing efforts, new observational techniques were emerging that would transform the field of astrometry and enable the measurement of stellar positions and motions with previously unattainable precision. Chief among these was the application of photography to positional astronomy, a development that would eventually make visual observation largely obsolete for precise astrometric work. One of the pioneers of this photographic revolution in proper motion studies was Frank Schlesinger, an American astronomer whose work at Yankees Observatory and later at Yale established methods that would be used throughout the 20th century. Schlesinger recognized that photographic plates, when measured with sufficient care, could yield stellar positions more precise than those obtainable through visual observation, and moreover that plates taken years or decades apart could be compared directly to reveal proper motions with an accuracy that visual methods could not match. At Yankees Observatory in Wisconsin, and later at the Yale University Observatory, he developed systematic programs of photographic observation aimed at determining both parallaxes and proper motions for large numbers of stars. These two quantities, parallax and proper motion, are in some ways complementary, for parallax gives the distance to a star while proper motion gives its apparent angular velocity across the sky, and together they allow astronomers to calculate the actual velocity of the star through space. The techniques that Schlesinger developed required extraordinary attention to detail, for the measurement of stellar positions on a photographic plate involves many sources of error that must be carefully controlled or corrected. The plate must be measured using a specialized instrument called a measuring engine, a precision device equipped with microscopes and graduated scales that allows the position of each stellar image to be determined to within a few micrometers. The optical properties of the telescope that produced the plate must be well understood, for any distortions in the optical system will affect the apparent positions of the stars. Atmospheric refraction, the bending of light as it passes through the Earth's atmosphere, must be accounted for, as must the proper motion of the reference stars themselves. These photographic techniques spread rapidly through the astronomical community, and by the middle of the 20th century, the comparison of photographic plates taken at different epochs had become the standard method for measuring stellar proper motions. The plates themselves became valuable archives, collections of celestial photographs spanning decades that could be compared and re-measured as techniques improved, yielding ever more precise determinations of stellar positions and motions. One astronomer who made particularly extensive use of photographic methods was Willem Jacob Luton, a Dutch-American astronomer whose career spanned much of the 20th century and who became renowned for his dedication to finding and cataloguing stars with large proper motions. Luton understood that stars with large proper motions are, on average, relatively nearby, for a given velocity through space produces a larger angular motion when the star is closer to us. By systematically searching for high proper motion stars, Luton was therefore compiling a census of the solar neighborhood, identifying stars that are our relatively near neighbors in the galaxy. Luton examined hundreds of thousands of photographic plates over the course of his long career, using a device called a blink comparator that allowed him to rapidly alternate between two photographs of the same star field taken years apart. Stars that had moved appreciably between the two photographs would appear to jump back and forth as the images were alternated, catching the attention of the observer. Through this painstaking work, Luton discovered thousands of high proper motion stars, many of them faint red dwarf stars that had previously escaped notice. Among his discoveries was a star now known as Luton's star, a red dwarf located about 12 light-years from the Sun, close enough to be among our nearest stellar neighbors yet so faint that it requires a telescope to be seen at all. Similar surveys were conducted at other observatories, each contributing to the growing catalogue of stellar motions. At the Lowell Observatory in Arizona, founded by Percival Lowell for the study of the planets, astronomers undertook their own proper motion survey, using the observatory's telescopes to photograph the sky and search for stars that moved measurably between exposures. These various surveys, conducted independently at different observatories around the world, gradually built up a comprehensive picture of stellar motions across the sky, revealing patterns that would inform our understanding of the structure and dynamics of the Milky Way galaxy. An important conceptual contribution to these efforts came from the Dutch astronomer Jacobus Cornelius Kapteyn, who introduced the idea of selected areas as a way to make systematic sky surveys more tractable. Kapteyn recognized that it would be impractical to study every star in the sky with equal attention, and he therefore proposed that astronomers should concentrate their efforts on a carefully chosen set of regions, or selected areas, distributed across the sky in a pattern designed to give a representative sample of the stellar population as a whole. By studying these selected areas intensively, determining positions, motions, brightnesses, and spectral types for all stars within them, astronomers could build up a statistical picture of the galaxy without attempting the impossible task of studying every star individually. Kapteyn's selected areas concept proved influential, and observatories around the world participated in coordinated programs to observe these designated regions, sharing their results and gradually assembling the data needed to understand the structure of the stellar system. This cooperative approach, with different observatories contributing observations according to their capabilities and resources, exemplified the international character that astrometric work often assumed, recognizing that the sky belongs to no single nation and that understanding it requires the combined efforts of observers stationed across the globe. Among all the proper motion measurements made during this era, one star stands out as possessing the largest known motion across the sky of any star visible from Earth. This distinction belongs to a faint red dwarf star discovered in 1916 by Edward Emerson Barnard, an American astronomer renowned for his visual acuity and his meticulous observation of the heavens. Barnard detected this star while comparing photographs taken several years apart, noticing that one faint star had shifted its position by an amount that was immediately striking even by the standards of high proper motion stars. Barnard's star, as it came to be known, moves across the sky at a rate of 10.3 arcseconds per year, a figure that may seem small in everyday terms but is remarkably large by astronomical standards. To put this in perspective, the full moon spans about 1800 arcseconds in diameter, so Barnard's star moves by roughly 0.5% of the moon's diameter each year. Over a human lifetime of 70 or 80 years, this motion would amount to several hundred arcseconds, enough to noticeably shift the star's position relative to its neighbors in the sky. Over longer spans of time, the motion is even more dramatic, and astronomers have calculated that in about 10,000 years, Barnard's star will reach its closest approach to the Sun, passing within about 4 light-years of our solar system. The large proper motion of Barnard's star is a consequence of two factors: its relative proximity to the Sun, being located only about 6 light-years away, and its considerable velocity through space, about 90 kilometers per second relative to our solar system. The combination of nearness and high velocity produces the apparent rapid motion across the sky that first caught Barnard's attention and that has made this star a subject of continued interest to astronomers. The study of proper motions, pursued so patiently through these decades of cataloguing and plate measurement, yielded insights that extended far beyond the motions of individual stars. By analyzing the patterns of proper motions across the sky, astronomers could detect the rotation of our galaxy, could identify streams of stars moving together through space as remnants of disrupted star clusters, and could trace the general drift of stars in the solar neighborhood. These investigations laid the groundwork for our modern understanding of galactic dynamics, revealing the Milky Way to be a vast rotating system in which each star traces its own orbit around the distant galactic center. The techniques developed during this era, the careful comparison of photographs, the precise measurement of plates, the statistical analysis of proper motion data, remained the standard methods of astrometric work until the advent of space-based observations in the latter part of the 20th century. Yet even with the arrival of new technologies, the historical records compiled by Argelander, Boss, Schlesinger, Luton, and their many colleagues retained their value, for proper motion determination still requires the comparison of positions separated by time, and the longer the time baseline, the more precise the resulting motion estimate. The photographic plates carefully preserved in observatory archives, some of them now more than a century old, continue to serve as a record of where the stars were located in earlier times, a gift from past generations of astronomers to those who continue the work of mapping the slow dance of the stars across the sky. And so the catalogues grew, the measurements accumulated, and our knowledge of stellar motions gradually became more complete and more precise. This was work that proceeded not through sudden breakthroughs or dramatic discoveries, but through the steady accumulation of careful observations, each one adding its small contribution to the great edifice of astronomical knowledge. It is perhaps fitting that such work should have this character, for the motions it sought to measure are themselves gradual and unhurried, revealing themselves only to those who have the patience to watch and wait and measure with care, year after year, decade after decade, as the stars drift slowly onward through the endless night. And so we come now to the quiet, painstaking work of extracting meaning from the photographic plates themselves, for it was never enough simply to expose the glass to starlight and develop the image. The plates, once fixed and dried and stored in their careful archives, contained within their emulsion layers a kind of frozen sky, a representation of the heavens at one particular moment. But the positions of the stars upon that glass were not yet positions in the sky. They were merely distances from edges, measurements in millimeters across a physical surface, and the transformation of those earthly measurements into celestial coordinates required machines of considerable precision and mathematical procedures of equally considerable complexity. This work, the measuring and the reducing of photographic plates, occupied generations of astronomers and their assistants, and it proceeded with a slowness and a steadiness that we might find almost meditative to consider now, here in the quietness of this evening. The instruments developed for this purpose were called measuring engines, or sometimes measuring machines, and their fundamental task was beautifully simple in principle while being extraordinarily demanding in execution. One needed to determine, for each star image upon the plate, the precise location of that image relative to some reference point, typically the center of the plate or a set of fiducial marks etched into the glass during manufacture. The measurements were made in two perpendicular directions, which we might call X and Y, and from these rectangular coordinates on the plate one could eventually derive the right ascension and declination of the star in the sky, though many corrections and transformations lay between the raw measurement and the final catalogue position. Among the most influential and widely used of these measuring engines were those produced by the firm of Repsold, based in Hamburg, whose workshops had supplied telescopes and instruments to observatories across Europe for much of the 19th century. The Repsold measuring machine became something of a standard in the field, and its design embodied principles that would persist in various forms for many decades. The plate was mounted upon a carriage that could move in one direction, while a second carriage, carrying the measuring microscope, moved perpendicular to the first. Long precision screws drove these carriages, and the rotation of the screws was measured by circular scales divided with the finest graduations that the technology of the time permitted. The measurer would peer through the microscope, centering a crosshair or a set of parallel wires upon the star image, and then read the positions from the scales, recording the numbers by hand in a logbook. The precision required was formidable. A single arcsecond of angle in the sky corresponded to only a few micrometers on a typical photographic plate, and the measuring engines were designed to achieve repeatability at this level or better. The screws had to be manufactured with extraordinary accuracy, and even then their errors were mapped and tabulated so that corrections could be applied. The microscopes were fitted with illumination systems to render the star images visible, and the mountings were designed to minimize vibration and thermal expansion, for even small changes in temperature could cause the metal framework to shift by amounts that were significant at the micrometer scale. The Royal Greenwich Observatory, which played such a central role in the International Astrographic Catalogue project, developed its own specialized equipment over the years, including the measuring engine known as Galaxy, which represented a later generation of such machines. Galaxy was designed to handle the particular requirements of measuring the Carte du Ciel and Astrographic catalogue plates, and it incorporated refinements that reflected the accumulated experience of decades of photographic astrometry. The machine allowed for the systematic measurement of large numbers of stars on each plate, with the operator working through the plate methodically, star by star, recording coordinates that would later be processed through the reduction procedures. Another significant instrument was the Mann two-coordinate measuring engine, produced by the firm of Mann in England, which found use in various observatories. The two-coordinate designation indicated that the machine was designed specifically for the simultaneous measurement of both X and Y positions, as distinct from earlier machines that might measure one coordinate and then require the plate to be rotated for measurement of the second. The Mann machine, like its contemporaries, relied upon precision screws and scales, and upon the careful eye of a skilled operator to center the measuring mark upon each star image. These machines were substantial pieces of apparatus, often weighing hundreds of kilograms and occupying dedicated rooms within the observatory where temperature and humidity could be controlled. Once the measurements were obtained, the process of reduction began, and this mathematical transformation was itself a considerable undertaking. The raw measurements were coordinates upon the plate, given in millimeters from some arbitrary origin, but the desired end product was positions upon the celestial sphere, given in right ascension and declination for a specified epoch. The connection between these two coordinate systems was not direct, for numerous effects intervened to complicate the relationship, and each of these effects had to be accounted for with appropriate corrections. Atmospheric refraction was one such effect, arising because the light from a star is bent as it passes through the Earth's atmosphere, causing the star to appear higher in the sky than its true geometrical position. The amount of refraction depends upon the altitude of the star above the horizon, being greatest for stars near the horizon and negligible for stars at the zenith. The correction for refraction required knowledge of the atmospheric conditions at the time of observation, including temperature and pressure, and the application of tables or formulae that had been developed from theoretical principles and refined by centuries of practical experience. Aberration was another effect requiring correction, this one arising from the finite speed of light combined with the motion of the Earth through space. Because the Earth moves in its orbit around the Sun, and simultaneously rotates upon its axis, the apparent direction to a star is slightly displaced from its true direction, in a manner that depends upon the velocity of the observer relative to the incoming light. The annual aberration, caused by orbital motion, can amount to some 20 arcseconds, while the diurnal aberration, caused by the Earth's rotation, is much smaller but still measurable with precision instruments. Precession entered the reduction process because the orientation of the Earth's axis changes gradually over time, describing a slow cone in space with a period of approximately 26,000 years. This means that the coordinate system defined by the celestial equator and the vernal equinox is itself in motion, and positions measured at one epoch must be transformed to the standard epoch of the catalogue being compiled. The transformation involves both the precession of the equinoxes, which shifts the 0 point of right ascension, and the changing obliquity of the ecliptic, and the formulae for these corrections had been refined over many centuries of theoretical and observational work. Beyond these effects, which arose from the geometry of observation and the motion of the Earth, there were systematic errors specific to the plate and the telescope. Plate tilt was one such error, occurring when the photographic plate was not perfectly perpendicular to the optical axis of the telescope at the moment of exposure. Even a small tilt introduced a linear distortion into the positions, causing stars on one side of the plate to appear displaced relative to stars on the other side. This effect could be detected and corrected by examining the pattern of residuals after a preliminary reduction. Optical distortion was another source of systematic error, arising from the inherent limitations of the telescope's lens or mirror system. No optical system is perfect, and particularly toward the edges of the field of view, stars may appear slightly displaced from their true positions due to aberrations in the optical design. This distortion could be characterized by measuring plates of star fields with well-known positions, and by applying polynomial corrections that modeled the pattern of displacement as a function of position on the plate. The standard mathematical approach to the reduction process was known as the plate constants method, or sometimes the six-constant plate model. In this approach, the relationship between plate coordinates and celestial coordinates was assumed to be describable by a linear transformation involving 6 parameters. These parameters accounted for the scale of the plate in both coordinates, the orientation of the plate relative to the celestial coordinate system, and the position of the plate center upon the sky. The 6 constants were determined by measuring stars of known position, called reference stars, which appeared upon the plate along with the stars whose positions were to be determined. The mathematics of this determination involved setting up equations relating the measured plate positions of the reference stars to their catalog positions, and then solving for the 6 unknown constants using the method of least squares. Once the constants were found, they could be applied to transform the plate coordinates of any star on the plate into celestial coordinates. The accuracy of the resulting positions depended upon the number and distribution of reference stars, upon the accuracy of their catalog positions, and upon how well the linear model represented the true relationship between plate and sky. For many purposes, the 6-constant model was adequate, but for work of the highest precision, or for plates with significant optical distortion, it became necessary to extend the model by including higher-order terms. Polynomial extensions allowed for the inclusion of quadratic, cubic, or even higher powers of the plate coordinates, capturing distortion patterns that the linear model could not represent. These extended models required more reference stars for their determination, and the solutions became more complex, but the resulting positions were correspondingly more accurate. The entire process, from measurement to reduction to final catalogue, was extraordinarily labor-intensive. A single photographic plate might contain images of hundreds or thousands of stars, and each star required individual measurement. The measurer would sit at the measuring engine for hours at a time, eyes pressed to the microscope, hands adjusting the fine screws, voice calling out numbers to a recorder or pencil scratching entries into a logbook. Days would pass in the measurement of a single plate, and the Astrographic Catalogue project, with its thousands of plates, required the efforts of dozens of measurers working over decades to complete. Skilled measurers became valuable assets to their observatories, and the quality of their work directly affected the accuracy of the final catalogues. The ability to center consistently upon star images, to read scales accurately, to maintain concentration through long hours of repetitive work. These were talents that developed through practice and that varied from one individual to another. Observatories invested considerable effort in training their measurers, and in developing procedures that would ensure consistency and accuracy. Yet despite all efforts at consistency, a troubling source of error persisted, known as the personal equation. Different measurers, it was found, would obtain systematically different positions for the same stars. One measurer might consistently place the crosshair slightly to one side of where another measurer placed it, or might estimate the center of a large diffuse image differently than a colleague. These differences were often small, amounting to fractions of a micrometer on the plate and fractions of an arcsecond in the sky, but they were systematic and persistent. Reducing their effect required careful calibration, with different measurers observing the same plates and their results being compared and adjusted. Another systematic error, equally troublesome, was known as the magnitude equation. This was a systematic difference in the measured positions of bright stars compared to faint stars, and it arose from the nature of the photographic image itself. Bright stars produced larger, more saturated images on the plate, while faint stars produced smaller, more compact images. The measurer, attempting to estimate the center of these differently sized images, might introduce a systematic bias, placing the estimated center of large images slightly differently than the estimated center of small images. Furthermore, the optical system of the telescope might introduce different amounts of distortion for images of different sizes, compounding the effect. The magnitude equation was a persistent problem in photographic astrometry, and various techniques were developed to detect and correct it, including the observation of star fields at different exposure times and the intercomparison of catalogues compiled from plates of different limiting magnitudes. As the decades of the 20th century progressed, the burden of manual measurement became increasingly unsustainable. The amount of observational material was growing. The demands for more complete and more accurate catalogues were increasing, and the pool of skilled measurers was limited. The solution, when it came, was automation, the development of machines that could measure photographic plates without continuous human intervention. The Cosmos machine at the Royal Observatory, Edinburgh, which became operational in 1972, was one of the pioneering automatic measuring machines. Its name stood for coordinates, sizes, magnitudes, orientations, and shapes, reflecting the comprehensive nature of the data it could extract from each stellar image. Cosmos used a scanning approach, with the plate being moved past a detector that recorded the light transmitted through the plate at each position. The resulting data were processed by computer to identify stellar images and determine their positions, magnitudes, and other characteristics. The machine could measure a plate far faster than any human measurer, and with a consistency that was unaffected by fatigue or personal equation. At Cambridge, a similar machine was developed under the name APM, the Automatic Plate Measuring Facility. Like Cosmos, APM used automated scanning and computer processing to extract positions and magnitudes from photographic plates. These machines represented a new era in astrometry, one in which the role of the human measurer shifted from the direct work of measurement to the design and oversight of automated systems. The machines had their own sources of systematic error, of course, and considerable effort went into their calibration and characterization, but they made possible the measurement of quantities of data that would have been utterly impractical by manual methods. The reduction procedures evolved as well, with computer programs taking over the calculations that had previously been performed by hand or with the aid of mechanical calculators. The fitting of plate constants, the application of corrections for refraction and aberration and precession, the transformation from plate coordinates to celestial coordinates, all of these became automated, and the resulting catalogues could be produced more quickly and with fewer opportunities for clerical error. Yet the fundamental principles of the reduction process remained the same as they had been in the era of manual measurement, for the relationship between the plate and the sky was governed by geometry and optics and the motion of the Earth, and these did not change with the advent of computers. And so the quiet work of plate measurement and reduction continued through the final decades of the photographic era, producing catalogues of increasing completeness and accuracy. The machines hummed in their climate-controlled rooms. The computers processed their data, and the positions of stars were extracted from the frozen images upon the glass plates, one by one, in an endeavor that stretched back to the first faltering attempts to record starlight upon sensitized surfaces and forward to the moment when new technologies would render the photographic plate itself obsolete. But that transition still lay some years ahead, and for now the plates remained central to the work, each one a small rectangle of glass bearing the imprints of countless stars, waiting to yield its secrets to the patient inquiry of measurement and mathematics. The night sky, when we look upon it with patient eyes, seems to present a canvas of fixed and eternal points, each star holding its appointed place as though pinned there by some careful hand. And yet, as astronomers of the 18th and 19th centuries began to measure and record and compare with ever greater precision, it became apparent that nothing in the heavens is truly still, that everything moves, and that even our own sun, which we might naturally assume to be the stable center of our experience, is itself drifting through the vast spaces between the stars, carrying the Earth and all its companion planets along with it on a journey whose destination lies somewhere among the distant constellations, a journey that had been occurring since long before there were human eyes to wonder at the stars, and which continues still as you settle into the comfortable quiet of this moment. It was William Herschel, the German-born musician who became one of the greatest observational astronomers in history, who first demonstrated this solar motion in a paper presented to the Royal Society in the year 1783, and his method, though based upon what we might now consider a remarkably small sample of observations, was both elegant in its conception and sound in its reasoning, revealing the kind of careful geometric thinking that would characterize the best work in astrometry for generations to come. Herschel understood that if the sun were moving through space in a particular direction, then the stars around us would appear to shift in a systematic way, much as the trees along a country road seem to part before a traveler and close together behind them, and this effect, which astronomers call secular parallax, would cause stars in the direction of the sun's motion to appear to spread apart from one another over time, while stars in the opposite direction would seem to converge, and stars to either side would show a general drift away from the point toward which the sun is traveling. Working with the proper motions of just 13 stars, which was a small number even by the standards of his day but represented those stars for which reasonably reliable measurements of apparent movement were available, Herschel applied this geometric principle with considerable care, examining the directions in which each star appeared to be moving across the sky and asking himself whether there existed some point in the heavens from which the stars could be said to be receding, on average, and some opposite point toward which they might be converging. The mathematics involved were not trivially simple, for each star's proper motion is the combination of its own true movement through space and the apparent movement caused by the sun's journey, and separating these two components required assumptions about the random nature of individual stellar motions. But Herschel proceeded with the quiet confidence of a mind well suited to such problems, and after his calculations were complete, he announced that the sun appeared to be moving toward a point in the constellation Hercules, near the star Lambda Herculis, a point that astronomers would come to call the solar apex, while the opposite point, the solar antapex, lay in the southern constellation Columba. This discovery was remarkable not only for what it revealed about the sun's motion, but also for what it implied about the nature of the universe itself. For if the sun could be shown to move, then it was no longer possible to regard it as the fixed and central point around which all other things revolved, and the old notions of a stationary sun at the heart of creation began to give way to a more dynamic and humbling picture in which our star was but one of many, drifting among its neighbors through depths of space that suddenly seemed less like a dome overhead and more like an ocean of unimaginable extent. Herschel himself recognized that his determination of the solar apex was approximate, being based as it was on so few stars, and he expressed hope that future astronomers with access to more and better proper motion data would be able to refine his result. And in this expectation he was entirely correct, for the work of mapping the Sun's journey through the galaxy would occupy some of the finest astrometric minds of the following century. Among those who took up this task was Friedrich Wilhelm August Argelander, a Prussian astronomer whose name appears repeatedly in any account of 19th-century positional astronomy, and whose meticulous approach to observation and data analysis represented the very best practices of his era. In the year 1837, more than half a century after Herschel's initial work, Argelander published a refined determination of the solar apex based upon a substantially larger sample of stellar proper motions, applying more sophisticated mathematical techniques to the problem and benefiting from the accumulated improvements in the measurement of star positions that had occurred in the intervening decades. Where Herschel had worked with 13 stars, Argelander employed the proper motions of several hundred, and where Herschel had relied upon relatively crude measurements from various sources, Argelander could draw upon more consistent and precise catalogues compiled by the great meridian observers of the early 19th century. The result of Argelander's analysis confirmed Herschel's essential finding, placing the solar apex in the same general region of Hercules, though with greater precision regarding its exact location, and providing a more reliable estimate of the speed at which the Sun appeared to be traveling, which Argelander calculated to be something on the order of several kilometers per second relative to the nearby stars, though the exact figure would continue to be refined as observations improved. The direction Argelander found differed somewhat from Herschel's original value, which was entirely expected given the improved data, and his work established a methodology that would be followed by many subsequent investigators, each adding their own refinements and extensions as the body of known proper motions grew ever larger and more precise throughout the remainder of the century. As more proper motions became available through the great photographic surveys and the patient work of meridian astronomers, it became possible to examine not just the average motion of the Sun, but also the patterns of movement among the stars themselves. And it was here that a Dutch astronomer named Jacobus Cornelius Kapteyn made a discovery that would prove to be of fundamental importance for understanding the structure of our galaxy, though the full implications of his findings would not become clear until other astronomers had built upon his work in ways he could not have anticipated. Kapteyn was a man of extraordinary dedication to the laborious tasks of positional astronomy, and he had established at Groningen a laboratory devoted to the measurement and analysis of photographic plates, where he and his assistants would spend years extracting positional data from images of star fields, and it was this painstaking work that led him, in 1904, to announce a remarkable discovery concerning the systematic motions of the stars. What Kapteyn found was that the proper motions of stars in the solar neighborhood were not randomly distributed, as one might expect if each star were simply wandering independently through space, but instead showed a pronounced tendency to cluster around two preferred directions, as though the stars could be divided into two great streams or currents flowing past one another through interstellar space. This phenomenon, which Kapteyn called star streaming, suggested that the stellar population of our region of space was not a simple homogeneous collection of independently moving objects, but rather consisted of at least two distinct groups with different characteristic motions. And this was a finding that demanded explanation, For what could cause such a systematic pattern in the movements of so many stars spread across such vast distances? Kapteyn himself proposed various explanations for the star streams, considering the possibility that they might represent two interpenetrating clouds of stars with different origins or different dynamical histories. And while his specific interpretations would later be superseded by more complete theories of galactic structure, his fundamental observation was sound and would prove to be a crucial piece of the puzzle that astronomers were slowly assembling regarding the nature of our stellar system. The star streaming effect, it would eventually be understood, arises naturally from the rotation of the galaxy, combined with the Sun's position within it and the particular way in which stellar orbits are distributed. But reaching this understanding would require additional decades of observation and analysis, and would depend upon the contributions of several other remarkable individuals whose stories interweave with that of Kapteyn himself. One of the models that Kapteyn developed from his extensive studies of stellar distributions and motions was an attempt to map the overall structure of the stellar system, to determine its shape and extent, and to locate the position of the Sun within it. This effort, which culminated in what became known as the Kapteyn universe, represented one of the most ambitious attempts yet made to describe the galaxy as a whole based upon systematic observational data rather than speculation. And while its conclusions would ultimately prove to be significantly in error, the methods Kapteyn employed and the data he assembled represented an important advance in the scientific study of galactic structure. According to Kapteyn's model, which he developed over many years and refined repeatedly as new data became available, the stellar system was a flattened, roughly lens-shaped collection of stars, extending perhaps 30,000 light-years along its longest dimension and perhaps 6,000 light-years in thickness, with the Sun located reasonably close to the center of this structure. The picture Kapteyn painted was one in which the density of stars decreased smoothly outward from the center in all directions, with the Sun occupying a position of modest importance, not quite at the central point but not far from it either, in a location that seemed to accord with the apparent uniformity of the Milky Way's brightness as it encircled the sky. This model was based upon careful counts of stars in different regions of the sky and at different apparent brightnesses, combined with the proper motion data that Kapteyn had spent so many years collecting and analyzing, and it represented a genuine scientific achievement even though later investigations would reveal that it significantly underestimated the true size of the galaxy and significantly overestimated the centrality of the Sun's position within it. The errors in Kapteyn's model arose primarily from a phenomenon he could not have accounted for adequately given the state of astronomical knowledge at the time, namely the absorption and scattering of starlight by interstellar dust, which makes distant stars appear fainter and redder than they would if space were perfectly transparent, and which effectively hides large portions of the galaxy from view, particularly in the directions where the dust is most concentrated. Because Kapteyn did not fully account for this interstellar absorption, he believed that the galaxy extended only as far as his star counts could reach, not realizing that the apparent thinning of stars in certain directions was due not to the actual edge of the stellar system, but rather to obscuring material that blocked the light of more distant stars. This limitation was shared by nearly all galactic models of the era and would only be overcome when astronomers developed methods of probing the galaxy's structure that did not depend solely upon counting visible stars in optical light. The crucial breakthrough came from an American astronomer named Harlow Shapley, who in the years around 1918 published a series of papers that would fundamentally transform our understanding of the galaxy's size and the Sun's place within it. Shapley's method relied not upon counting ordinary stars or measuring their proper motions, but rather upon studying a particular type of variable star known as Cepheid variables. which are stars that pulsate in brightness over regular periods ranging from days to weeks, and which possess a remarkable property that makes them extraordinarily useful as distance indicators, namely a tight relationship between the period of their light variations and their intrinsic luminosity, such that a Cepheid with a longer period is genuinely more luminous than one with a shorter period. This period luminosity relationship, which had been discovered by Henrietta Swan-Leavitt in 1912 through her study of Cepheid variables in the Small Magellanic Cloud, meant that by observing the period of a Cepheid's variation, astronomers could determine how intrinsically bright it was, and by comparing this intrinsic brightness with its apparent brightness as seen from Earth, they could calculate its distance, even when that distance was far too great to be measured by parallax or any other geometric method. Shapley applied this technique to Cepheid variables found in globular clusters, those dense spherical collections of hundreds of thousands of ancient stars that orbit around the galactic center, and by determining the distances to many such clusters, he was able to map out their three-dimensional distribution in space and thus to infer the location and extent of the galaxy itself. What Shapley found was startling and at first met with considerable skepticism from other astronomers, for his distances implied that the galaxy was far larger than Kapteyn's model suggested, perhaps 10 times larger or more, and that the Sun was not located anywhere near the center but rather out toward the periphery, in a position that we might describe as quite undistinguished within the vast system of stars that comprises the Milky Way. The globular clusters, Shapley showed, were distributed roughly symmetrically around a point that lay in the direction of the constellation Sagittarius, at a distance of some 50,000 light-years from the Sun. And this point, he argued, must represent the true center of the galaxy, with the Sun located far off to one side. Seeing the great bulk of the stellar system spread across the sky in the band of the Milky Way, but mistaking its structure due to the confusing effects of interstellar absorption. Shapley's determination of the galaxy's size was itself somewhat in error, being larger than the values accepted today due to an incomplete calibration of the Cepheid period luminosity relationship at that time. But his essential finding regarding the Sun's peripheral position was correct and represented a profound shift in our cosmic perspective, one that might be compared to the earlier Copernican revolution in its philosophical implications. For just as Copernicus had displaced the Earth from the center of the solar system, Shapley now displaced the Sun from the center of the galaxy, leaving humanity in a position that seemed ever more modest and unremarkable with each new astronomical discovery. The final piece of the puzzle regarding galactic structure that we shall consider in this gentle survey of astrometric history came from another Dutch astronomer, Jan Hendrik Oort, who in 1927 provided the definitive proof that our galaxy rotates and worked out the mathematical description of this rotation in terms that could be tested and confirmed by observation. Oort's analysis combined two types of stellar motion data: the proper motions that had been the bread and butter of astrometry for 2 centuries, and the radial velocities that could be measured spectroscopically by observing the Doppler shifts in stellar spectra, and by examining how these two components of motion varied systematically with direction in the sky and with distance from the Sun. He was able to demonstrate that the observed patterns could only be explained if the entire galaxy were rotating, with stars closer to the center completing their orbits more quickly than stars farther out, much as the inner planets of our solar system orbit the Sun more rapidly than the outer ones. This differential rotation, as it is called, explained naturally the star streaming that Kapteyn had discovered 2 decades earlier, for in a differentially rotating galaxy, stars at different distances from the center would have different orbital velocities, and from the vantage point of the Sun, this would create the appearance of systematic flows of stars moving in preferred directions, exactly as Captain had observed. Oort's analysis also allowed him to estimate various parameters of the galactic rotation, including the distance to the galactic center and the period of the Sun's orbit around it. And while these early estimates have been refined considerably by subsequent observations, the basic picture that Oort established of a vast rotating disk of stars, with the Sun participating in this rotation from a position well out from the center, has remained the foundation of our understanding of galactic structure ever since. And so we see how the patient accumulation of positional measurements, begun in earnest in the 18th century and continued with ever greater precision through the 19th and into the 20th, led gradually but inexorably to a picture of our place in the universe that would have astonished the astronomers of earlier ages. A picture in which the Sun moves through space at considerable speed, heading toward a point in the constellation Hercules, while at the same time participating in the grand rotation of a galaxy far larger than anyone had imagined, from a position that is neither central nor special but simply one among billions, a perspective that might seem diminishing but which perhaps can also be understood as connecting us to something vast and magnificent, a cosmic structure revealed through the quiet work of measuring and recording, night after night, year after year, the positions of the stars. And so we come now to a rather significant period in the long and patient history of measuring stellar distances, a time when the photographic plate, that simple sheet of glass coated with light-sensitive emulsion, became the primary tool for determining just how far away the stars truly are. This era, spanning roughly from the very early 1900s through to the final decades of the 20th century, saw the gradual accumulation of thousands upon thousands of parallax measurements, each one representing countless hours of careful observation, meticulous plate measurement, and painstaking calculation. It is a story of quiet dedication, of astronomers who spent entire careers refining techniques that would inch humanity's knowledge of cosmic distances ever forward, one tiny angular shift at a time. The transformation of parallax measurement from a challenging art practiced by a handful of visual observers into a systematic, reproducible science owes a great deal to the work of Frank Schlesinger, an American astronomer whose contributions beginning in 1903 would fundamentally alter how such measurements were made. Schlesinger was working at the Yerkes Observatory in Williams Bay, Wisconsin, where the great 40-inch refractor, the largest refracting telescope ever constructed, dominated the landscape. But it was not this magnificent instrument that Schlesinger would use for his parallax work, for he understood that what mattered most for such measurements was not sheer light gathering power but rather the ability to record stellar positions with the utmost precision and consistency over extended periods of time. What Schlesinger recognized, and this recognition proved crucial to the development of the entire field, was that the photographic plate offered distinct advantages over the human eye when it came to measuring the tiny angular displacements that constitute stellar parallax. The eye, for all its remarkable capabilities, introduces variability into observations, as different observers may perceive stellar positions slightly differently, and even the same observer may not be perfectly consistent from one night to the next. The photographic plate, by contrast, provides a permanent, objective record of the star field at a particular moment, a record that can be measured and remeasured, studied and compared with other plates taken months or years apart, all without the uncertainties inherent in visual estimation. Schlesinger began his systematic development of photographic parallax techniques at Yerkes in 1903, and over the following years he refined an approach that would become the standard method for parallax determination throughout the photographic era. The key to his technique lay in the use of long-focus refractors. telescopes with considerable focal lengths that would spread the star images across a larger area of the photographic plate, thereby allowing more precise measurement of the tiny shifts in position that parallax produces. A longer focal length means that any given angular displacement on the sky corresponds to a larger linear displacement on the plate, and this magnification of the parallax signal made measurement considerably more tractable. The procedure that Schlesinger developed, and which would be followed with minor variations by parallax observers for the better part of a century, involved taking multiple photographic exposures of a star field containing the target star whose parallax was sought, along with a number of reference stars that served as a backdrop against which the target's motion could be measured. These reference stars were assumed, at least initially, to be sufficiently distant that their own parallaxes were negligible, so that any apparent shift in the position of the target star relative to these references could be attributed primarily to the parallactic effect caused by Earth's orbital motion around the Sun. The timing of these observations was of considerable importance, for the apparent parallactic shift of a star varies throughout the year as Earth moves from one side of its orbit to the other. Schlesinger and those who followed his methods adopted a standard observing strategy that called for obtaining photographs when the parallax factor was at its maximum, which is to say, when Earth's position in its orbit placed the Sun, Earth, and the target star in an arrangement that maximized the apparent angular displacement. For any given star, this condition occurs twice yearly, approximately 6 months apart, and so the systematic parallax programs of this era were characterized by observations taken at these optimal times, with the 6-month separation between plates providing the baseline against which the parallax could most readily be discerned. Each plate would be exposed for a carefully determined length of time, sufficient to record good images of both the target star and the reference stars, and then the plate would be processed using the chemical techniques standard to astronomical photography of the period. Once dried and hardened, the plate became a permanent record, and the real work of measurement could begin. This measurement was performed using specialized instruments called measuring machines or comparators, devices that allowed the astronomer to determine the precise position of each stellar image on the plate with respect to a coordinate system defined by the machine itself or by markings on the plate. The positions of the target star relative to the reference stars would be measured on many plates taken over several years, and these measurements would then be subjected to mathematical analysis designed to separate the various components of stellar motion. For a star exhibits not only parallax but also proper motion, that gradual drift across the sky that reflects the star's actual movement through space, and the analysis must account for both effects simultaneously if an accurate parallax is to be derived. Schlesinger developed and refined the mathematical techniques necessary for this separation, establishing procedures that would remain in use, with various improvements, throughout the decades of photographic parallax work that followed. In 1920, Schlesinger moved from Yerkes to the Allegheny Observatory, which is associated with the University of Pittsburgh, and there he continued his parallax program with even greater vigor. The Allegheny Observatory possessed a 30-inch refractor that proved well suited to parallax work, and under Schlesinger's direction the observatory became one of the premier centers for such research. When Schlesinger eventually departed Allegheny, his successor continued the program, maintaining the steady accumulation of parallax measurements that characterized this methodical approach to understanding stellar distances. The Allegheny program would continue for many years, contributing hundreds of carefully determined parallaxes to the growing body of knowledge about our stellar neighborhood. Meanwhile, other observatories were establishing their own systematic parallax programs, each contributing to what would eventually become a substantial catalogue of stellar distances. The Sproul Observatory, located at Swarthmore College in Pennsylvania, operated a 24-inch refractor that was dedicated to astrometric work, including an extensive parallax program that would ultimately measure the parallaxes of thousands of stars. The Sproul refractor, with its long focal length and stable mounting, was well suited to the precise positional measurements that parallax determination requires, and the observatory's astronomers applied themselves to this work with characteristic diligence over many decades. The McCormick Observatory, associated with the University of Virginia, also made significant contributions to the parallax enterprise through its program utilizing a 26-inch refractor. This instrument, like those at Allegheny and Sproul, was employed in the patient collection of photographic plates from which parallaxes could be derived, and the McCormick program added many valuable measurements to the accumulating store of stellar distance data. Each of these observatories developed its own particular expertise and refinements to the basic techniques, and taken together they formed a network of institutions devoted to the systematic determination of stellar parallaxes through photographic means. Yale University, too, maintained an active parallax program that contributed significantly to the field. The Yale parallax work was characterized by careful attention to the sources of error that could compromise parallax measurements, and the Yale astronomers worked to understand and minimize these errors through improved observing and reduction techniques. The program at Yale, like those at the other major parallax observatories, represented a long-term commitment to the gradual accumulation of reliable distance measurements, a commitment that required patience and persistence in equal measure. As the decades passed and the number of measured parallaxes grew, it became increasingly important to gather all of this scattered data into a single comprehensive resource that astronomers could consult. This task of compilation fell to Louise Jenkins, an astronomer who would devote much of her career to the creation and maintenance of the General Catalogue of Trigonometric Stellar Parallaxes. The first edition of this catalogue appeared in 1952, and it represented a remarkable effort to collect, evaluate, and present in systematic form all of the reliable parallax measurements that had been made up to that time. Jenkins assessed each measurement for quality and reliability, and where multiple determinations existed for the same star, she combined them to derive a best estimate of the parallax. The General Catalogue became an essential reference for astronomers interested in stellar distances, providing a single authoritative source for parallax data that would otherwise have been scattered across hundreds of individual publications. Jenkins continued to update and expand the catalogue as new measurements became available, and successive editions incorporated the steady stream of parallax determinations flowing from the various observing programs. The fourth edition of the General Catalogue, published in 1995, contained parallaxes for 8,112 stars, representing the accumulated work of nearly a century of photographic parallax observation. This catalogue stands as a monument to the patient efforts of the many astronomers who contributed to its contents, each measurement representing hours of telescope time, careful plate measurement, and mathematical analysis. Yet for all the care and dedication that went into these photographic parallax programs, the measurements were not without their challenges and limitations. The quest for ever more precise parallaxes led astronomers to grapple with subtle sources of error that had not been fully appreciated in the early days of the photographic technique. One significant issue was the problem of color-dependent refraction, which arises because the atmosphere bends light of different wavelengths by slightly different amounts. A red star and a blue star, even if they are at exactly the same position on the sky, will have their images displaced by slightly different amounts as their light passes through the atmosphere. And this differential displacement can introduce systematic errors into parallax measurements if not properly accounted for. The difficulty with color-dependent refraction is particularly acute when the target star and the reference stars differ significantly in color, as will often be the case. Red dwarf stars, which were of considerable interest because of their abundance and their relatively large parallaxes, typically appeared quite red on photographic plates, while the reference stars against which their positions were measured might include stars of various colors, some quite blue. The differential atmospheric refraction between these stars of different colors could mimic or mask the true parallactic shift, leading to systematic errors in the derived parallaxes if the effect were not carefully modeled and removed. Related to this was the phenomenon of atmospheric dispersion, which causes the light from a star to be spread out into a tiny spectrum by the atmosphere, with the blue end of this spectrum displaced from the red end. The image of a star on a photographic plate is therefore not a simple point but rather a slightly elongated smear whose centroid position depends on the color sensitivity of the photographic emulsion and on the color of the star itself. This atmospheric dispersion varies with the altitude of the star above the horizon, being most pronounced when the star is low in the sky and the light must traverse a greater thickness of atmosphere. Parallax observers learned to account for these effects, either by restricting observations to times when the star was high in the sky, or by applying corrections based on theoretical models of atmospheric dispersion. Another source of difficulty lay in the reference stars themselves, for these stars were not in fact infinitely distant as the simple parallax model assumed. Each reference star has its own parallax, even if small, and if this parallax is not accounted for, it can introduce errors into the determination of the target star's parallax. The correction for finite reference star distances requires some knowledge of how far away the reference stars are, which presents something of a circular problem since the distances to these stars are themselves uncertain. Parallax observers developed statistical methods for estimating and correcting this effect, but it remained a source of systematic uncertainty that was difficult to eliminate entirely. The photographic emulsion itself introduced additional complications, for the properties of the emulsion could vary slightly from plate to plate, and the development process introduced its own variabilities. The images of stars on a photographic plate are not perfect points but rather small disks whose size and shape depend on a variety of factors including the brightness of the star, the focus of the telescope, the seeing conditions during the exposure, and the characteristics of the emulsion. Measuring the precise center of such an image is not a trivial matter, and different measuring techniques could yield slightly different results. Observers developed standardized procedures for measuring plates and applied various corrections to account for known systematic effects, but some residual uncertainty inevitably remained. The long time baseline required for good parallax measurements introduced yet another challenge, for telescopes and their mountings do not remain perfectly stable over years and decades. Small changes in the telescope optics, gradual shifts in the mounting, and alterations to the building housing the instrument could all introduce subtle systematic effects that might be mistaken for true stellar motion. The most careful parallax programs included regular observations of standard fields and other checks designed to monitor and correct for such instrumental drifts, but maintaining the necessary long-term stability was a constant concern. Despite these many challenges, the photographic parallax programs of the 20th century succeeded in establishing reliable distances to thousands of nearby stars, providing the foundation upon which much of our understanding of stellar properties was built. Each parallax measurement, however modest it might seem in isolation, contributed to the larger picture of the solar neighborhood and its stellar inhabitants. The distances derived from these parallaxes allowed astronomers to convert the apparent brightnesses of stars into true luminosities, to estimate stellar sizes and masses, and to begin constructing a three-dimensional map of the stars surrounding our Sun. The work was slow, it was methodical, and it demanded a kind of patience that may seem foreign to our modern world of instant results and rapid discovery. A single reliable parallax might require observations spanning 5 years or more, and the measurement of thousands of such parallaxes was the work not of individual astronomers but of institutions committed to programs extending across generations. The astronomers who devoted their careers to this work understood that they were contributing to an edifice that would be completed, if it were ever completed at all, long after their own tenures had ended. Louise Jenkins, in compiling her general catalogue, was gathering together the fruits of all these labors, creating a resource that made the accumulated knowledge accessible to the broader astronomical community. Her catalogue went through 4 editions over more than 4 decades, each edition incorporating the new measurements that had appeared since the last, each edition slightly expanding humanity's surveyed knowledge of stellar distances. The 4th edition, with its 8,112 stars, represented the culmination of the photographic era, capturing in a single volume nearly everything that could be achieved through the patient accumulation of ground-based photographic parallax measurements. By the time that 4th edition appeared in 1995, a new era was already dawning, an era in which satellites orbiting above Earth's blurring atmosphere would transform parallax measurement once again, just as photography had transformed it nearly a century before. But the work of the photographic era was not thereby rendered obsolete or unimportant, for the techniques developed and the measurements accumulated during those decades provided the essential foundation upon which subsequent advances would build. The great parallax catalogues of the space age would be calibrated against and compared with the ground-based measurements, and the understanding of systematic errors gained through decades of photographic work would inform the analysis of satellite data. And so the photographic parallax programs take their place in the long history of attempts to measure the distances to the stars, representing a period of steady, incremental progress achieved through dedication, patience, and careful attention to detail. The names of the observatories, Yerkes and Allegheny, Sproul and McCormick and Yale, serve as reminders of the institutions that made this work possible, while the general catalogue of trigonometric stellar parallaxes stands as a lasting tribute to the efforts of all those who contributed to our knowledge of where the stars actually are in the vast three-dimensional space that surrounds us. It is a gentle story, perhaps, lacking in drama but rich in the quiet satisfaction of work well done, of problems carefully considered and patiently solved, of knowledge accumulated one small measurement at a time across the long and peaceful decades of the photographic era. And so we come now to a particularly gentle chapter in the history of astrometry, one that concerns itself with the subtle wobbles of stars, those tiny deviations from straight paths across the sky that reveal the presence of things we cannot see directly. This is a story about patience and precision, about the careful work of astronomers who noticed that certain stars did not move quite as expected, and who concluded, correctly as it turned out, that invisible companions must be tugging at them, pulling them this way and that as they journeyed together through space. It is a story that spans more than a century, from the first theoretical predictions in the 1840s to the sophisticated measurements of the late 20th century, and it teaches us that sometimes the most important things in the universe make themselves known not by their light, but by their gravitational influence upon their neighbors. To understand this work, we must first recall what we learned earlier about proper motion, that slow drift of stars across the celestial sphere that results from their actual movement through space relative to our Sun. When astronomers carefully measured the proper motions of stars over many years, they expected to find that each star traced a straight line against the more distant background, moving steadily in one direction year after year, decade after decade. And indeed, most stars do behave this way, proceeding along their paths with admirable consistency, their positions changing by tiny but predictable amounts as the centuries pass. But some stars, it was discovered, do not move in straight lines at all. Instead, they follow wavy paths, oscillating back and forth around an average trajectory, as though something unseen were periodically pulling them off course. This is the phenomenon we call astrometric wobble, and it became one of the most powerful tools available to astronomers for detecting objects that emit little or no light of their own. The first person to recognize the significance of these wobbling paths was the German astronomer Friedrich Wilhelm Bessel, whom we have encountered before in connection with his measurement of stellar parallax. Bessel was perhaps the most careful observer of his generation, a man who understood better than anyone the importance of accounting for every possible source of error in astronomical measurements. In 1844, Bessel published a remarkable paper in which he announced that two of the brightest stars in the sky, Sirius and Procyon, were not moving in straight lines. Instead, their proper motions showed distinct waviness, a periodic oscillation that could not be explained by any known effect. Bessel had been studying these stars for many years, comparing his own observations with historical records stretching back decades, and he had become convinced that the deviations were real, not merely the result of measurement errors or instrumental problems. The explanation Bessel proposed was elegantly simple. He suggested that both Sirius and Procyon must have invisible companion stars orbiting around them, and that what we observe as the proper motion of these bright stars is actually the motion of the center of mass of each system, combined with the orbital motion of the visible star around that center of mass. In other words, Sirius and Procyon were not single stars at all, but binary systems in which one component happened to be too faint to see directly. The wobble in their paths was the visible signature of this hidden companionship, a gravitational dance revealed through careful positional astronomy. This was a bold prediction, for Bessel was claiming the existence of objects that no one had ever seen, based entirely on the analysis of tiny positional discrepancies accumulated over many years of observation. The wobble he detected in the motion of Sirius amounted to only a few arcseconds over the course of its roughly 50-year orbital period, and detecting such a small systematic variation against the background of random measurement errors required extraordinary skill and patience. But Bessel was confident in his analysis, and he calculated approximate orbital periods and other properties for these unseen companions, leaving it to future astronomers with better telescopes to confirm or refute his predictions. The confirmation came 18 years later, in circumstances that were themselves rather lovely in their unexpectedness. In January of 1862, an American telescope maker named Alvin Graham Clark was testing a new 18.5-inch refracting telescope that his family's firm had constructed for the University of Mississippi. Testing a large telescope lens requires pointing it at bright stars and examining the images carefully for any defects or distortions, and Clark naturally chose Sirius, the brightest star in the night sky, as one of his test objects. As he examined the image of Sirius through the eyepiece, adjusting the focus and checking the quality of the optics, Clarke noticed a tiny point of light very close to the brilliant primary star, almost lost in its glare. At first he thought it might be a flaw in the lens, a ghost image produced by some imperfection in the glass, but further examination showed that it was a real celestial object, a faint companion star exactly where Bessel had predicted one should exist. This was Sirius B, the first white dwarf star ever discovered, though its true nature would not be understood for many decades. Clarke had found Bessel's invisible companion purely by accident, while engaged in the mundane task of testing optical equipment, and his discovery vindicated the astrometric method in the most satisfying way possible. The wobble in the proper motion of Sirius was not an artifact or an error. It was the genuine signature of a gravitationally bound companion, and Bessel's careful analysis had correctly predicted its existence nearly 2 decades before anyone could see it directly. The search for the companion of Procyon proved considerably more difficult, and it would take another 34 years before that object was finally observed. The problem was partly one of brightness difference and partly one of orbital geometry. Procyon's companion, like that of Sirius, turned out to be a white dwarf star, intrinsically very faint and easily overwhelmed by the light of its much brighter primary. But whereas Sirius B orbits at a relatively comfortable distance from Sirius A, allowing it to be glimpsed when conditions are favorable, Procyon B stays much closer to its primary throughout its orbit, making it exceptionally difficult to separate visually from the glare of the main star. Many astronomers attempted to find Procyon B in the decades following Bessel's prediction, but the companion eluded all searches until 1896, when the American astronomer John Martin Scheibel finally succeeded in detecting it using the 36-inch refractor at Lick Observatory in California. Scheibel caught the faint companion at a particularly favorable moment in its orbit, when it had reached its maximum angular separation from the primary star, and even then it was an extraordinarily difficult observation, requiring perfect atmospheric conditions and the utmost care in distinguishing the true companion from optical artifacts. But the detection was genuine, and Procyon B took its place alongside Sirius B as a confirmed astrometric prediction, a world whose existence had been inferred from wobbles in starlight long before any human eye could see it directly. The success of Bessel's method inspired generations of astronomers to search for other unseen companions using the same technique, and this brings us to a distinction that became increasingly important as the work progressed. When we speak of the proper motion of a single star, we mean the straightforward drift of that star across the sky, a linear motion that can be described by a direction and a speed. But when we speak of the proper motion of a binary system, we must distinguish between 2 different components of the observed movement. There is the motion of the center of mass of the system, which proceeds in a straight line just as a single star would, and there is the orbital motion of the visible component around that center of mass, which produces the periodic wobble we have been discussing. The observed path of the star is the combination of these 2 motions, a wavy line that oscillates around the straight trajectory of the center of mass. The amplitude of this wobble depends on several factors, including the mass of the unseen companion, its orbital distance from the visible star, and the distance of the entire system from our Sun. A more massive companion produces a larger wobble, as does a companion in a wider orbit, while more distant systems show smaller angular wobbles simply because the same physical displacement subtends a smaller angle when viewed from farther away. These relationships allow astronomers to deduce the properties of unseen companions from careful measurements of the wobble, though the calculations involve various assumptions and can be complicated by factors such as orbital inclination and eccentricity. As telescopes and measurement techniques improved through the 20th century, astronomers began to search for ever smaller wobbles, hoping to detect companions of lower and lower mass. The ultimate goal for many was the detection of planets around other stars, objects so small that their gravitational influence on their parent stars would be almost imperceptibly tiny. This was an enormously ambitious undertaking, requiring the measurement of stellar positions with a precision of hundredths or even thousandths of an arcsecond, far beyond what had been achieved in Bessel's day. But some astronomers believed it could be done, and one of the most persistent was Pieter van der Kamp, a Dutch-American astronomer who devoted much of his career to the search for extrasolar planets using the astrometric method. Van der Kamp worked at the Sproul Observatory in Pennsylvania, where he had access to a 24-inch refracting telescope that he used to make thousands of photographic observations of nearby stars over many decades. His primary target was Barnard's star, a faint red dwarf that holds the distinction of having the largest known proper motion of any star, moving across the sky at a rate of more than 10 arcseconds per year. This large proper motion made Barnard's star an ideal candidate for astrometric planet searches, because any wobble caused by orbiting planets would be easier to detect against such a rapid background movement, and because the star's proximity to our Sun, only about 6 light-years away, meant that even small physical wobbles would produce measurable angular displacements. In 1963, Van der Kamp announced that his observations revealed a wobble in the proper motion of Barnard's star consistent with the presence of a planet roughly 1.5 times the mass of Jupiter, orbiting with a period of about 24 years. This was extraordinary news, the first claimed detection of a planet around another star, and it attracted considerable attention from both astronomers and the general public. Van der Kamp continued his observations over the following years, refining his analysis and eventually proposing in 1969 that the wobble was better explained by 2 planets, one roughly equal to Jupiter's mass and another slightly smaller, orbiting with periods of 12 and 26 years respectively. The astronomical community received these claims with a mixture of excitement and skepticism. The reported wobble was extremely small, only about 1/100th of an arcsecond or so, right at the edge of what could be reliably measured with the available technology. Other observatories attempted to confirm the detection using their own instruments, but the results were inconclusive, with some finding hints of a wobble and others finding nothing at all. And then, gradually, a troubling pattern emerged. It was discovered that the Sproul refractor had undergone several modifications over the years, including adjustments to its objective lens in 1949 and again in 1957. When other astronomers examined Van der Kamp's data more closely, they found that the apparent wobble in Barnard's star correlated suspiciously with these instrumental changes. The star appeared to shift its position slightly each time the telescope was modified, suggesting that the wobble was not a real astronomical effect at all, but rather a systematic error introduced by changes in the optical system. This was a disappointing conclusion, both for Van der Kamp personally and for the broader astronomical community that had hoped to see the first confirmed detection of an extrasolar planet. Van der Kamp himself never fully accepted the systematic error explanation, and he continued to defend his results until his death in 1995. But the consensus among other astronomers gradually shifted against him, and Barnard's star is no longer considered to host the planetary companions he claimed to have detected. The episode serves as a sobering reminder of how difficult astrometric planet detection really is, and how easily systematic errors can masquerade as genuine signals when one is searching for effects at the very limits of instrumental precision. Despite this setback, The astrometric method did achieve genuine successes in detecting low-mass companions, particularly in cases where the companion was massive enough to produce a wobble larger than the systematic errors inherent in the observations. One notable example is the companion to Van Biesbroek's star, also known as VB8, a very faint red dwarf star discovered by the Belgian-American astronomer Georges van Biesbroek in 1944. This star, located about 21 light-years from the Sun, was found through astrometric observations to have an extremely low-mass companion, an object near the boundary between the smallest stars and the largest brown dwarfs. The astrometric orbit of this companion was carefully determined through decades of observations, revealing an orbital period of several years and a companion mass estimated at roughly 8% of the Sun's mass, making it one of the lowest mass stellar companions known at the time. The detection of such low-mass companions represented a significant achievement for the astrometric method, demonstrating that patience and precision could reveal objects that were simply too faint to see directly with the telescopes of the day. The technique was particularly valuable for detecting companions to nearby red dwarf stars, which are themselves quite faint and which might harbor companions of comparably low luminosity. Many of these systems were discovered through programs of systematic astrometric monitoring, in which selected stars were observed repeatedly over periods of years or decades, with their positions measured to the highest achievable accuracy and any deviations from linear proper motion carefully analyzed. The precision required for this work is worth contemplating for a moment, as it gives some sense of the extraordinary demands placed on the instruments and observers. To detect a wobble of 1/100th of an arcsecond, as Van de Camp attempted to do for Barnard's star, one must measure stellar positions to an accuracy better than this amount, which corresponds to an angle so small that it defies easy visualization. Imagine a coin placed at a distance of about 400 kilometers, and suppose you wished to detect whether that coin had shifted by the width of a human hair. That is roughly the level of angular precision we are discussing, and achieving it consistently over many years, while accounting for all possible sources of systematic error, is one of the most demanding tasks in observational astronomy. The challenges include not only the obvious ones of atmospheric turbulence and instrumental stability, but also more subtle effects such as the differential refraction of starlight by the Earth's atmosphere, the gradual settling and flexure of telescope mountings, changes in the optical properties of lenses and mirrors as they age, and the proper calibration of the reference stars against which the target star's position is measured. Each of these effects must be understood and corrected if the final measurements are to be meaningful, and the history of astrometric companion searches is littered with cases where unrecognized systematic errors led to false detections or missed discoveries. And yet, despite all these difficulties, the astrometric method remains a powerful tool for detecting unseen companions, and it laid the groundwork for much of what we now know about binary stars, brown dwarfs, and eventually planets around other stars. The wobble that Bessel first noticed in Sirius and Procyon was the beginning of a long tradition of inferring the presence of invisible objects from the gravitational perturbations they produce, a tradition that would eventually extend far beyond the capabilities of ground-based optical astrometry and into the realm of space-based instruments capable of measuring positions with precisions measured in millionths of an arcsecond. But all of that lay in the future, beyond the scope of our present story. For now, as you rest and perhaps begin to feel the gentle pull of sleep, it is enough to appreciate the quiet elegance of this method, the way that patient observation of tiny wobbles in starlight can reveal the presence of worlds and suns that would otherwise remain forever hidden from our view. The stars do not move in perfect straight lines, and in their subtle deviations we find evidence of companionship across the vast distances of space, a reminder that even in the apparent emptiness between the stars, matter gathers and orbits and dances to the ancient music of gravity. The mathematics of celestial reference frames begins with a question that seems almost philosophical in its nature, which is to ask where exactly we might place the origin of our measurements when we look outward into the depths of space, and how we can describe the positions of stars with such precision that astronomers working decades or even centuries apart might understand one another perfectly, comparing their observations as though they had stood side by side at the same telescope on the same evening. This is not a simple matter, for the sky is not a fixed canvas upon which the stars have been painted in permanent positions, but rather a slowly shifting arrangement of luminous points, each moving according to its own trajectory through the galaxy, while the very platform from which we observe, our own Earth, wobbles and precesses and nutates in ways that cause the coordinate grid we project upon the heavens to drift and rotate over the course of years and centuries. To establish order in this constantly shifting scene, astronomers developed what they call celestial reference frames, which are mathematical constructions that allow us to assign coordinates to any point on the sky in a manner that can be precisely communicated and reproduced. The fundamental elements of such a frame are not arbitrary, but arise naturally from the geometry of our situation as observers standing on a spinning planet that orbits the Sun along a particular path through space. The celestial equator is the great circle formed by projecting the plane of Earth's equator outward onto the sky, an imaginary line that divides the heavens into northern and southern hemispheres just as the terrestrial equator divides our globe. The ecliptic is another great circle, this one representing the apparent path of the Sun against the background stars over the course of a year, which is to say the plane of Earth's orbit projected outward to infinity. These two circles, the celestial equator and the ecliptic, are inclined to one another by approximately 23.5 degrees, a tilt that gives rise to our seasons and that plays a central role in the mathematics of celestial coordinates. Where these two great circles intersect, there are 2 points, and one of these intersections is called the vernal equinox, which is the point where the Sun appears to cross from the southern celestial hemisphere into the northern, an event that occurs around the 20th or 21st of March each year and marks the beginning of spring in the northern hemisphere. This point, the vernal equinox, serves as the origin of right ascension, which is the celestial equivalent of longitude, measured eastward along the celestial equator from the vernal equinox in units of hours, minutes, and seconds. Declination, the celestial equivalent of latitude, is measured in degrees north or south of the celestial equator, ranging from 90 degrees at the north celestial pole down through 0 at the equator and continuing to -90 degrees at the south celestial pole. Together, right ascension and declination allow us to specify any position on the sky with perfect precision, assuming we have agreed upon exactly where the celestial equator and the vernal equinox are located at any given moment. And here we encounter the great difficulty that occupied the minds of mathematical astronomers for centuries, for the vernal equinox does not stay in one place. The gravitational attraction of the Sun and Moon upon the slightly flattened figure of the Earth causes our planet's axis to describe a slow circle in space, like a spinning top that wobbles as it slows, completing one full cycle in approximately 26,000 years. This motion is called precession, and its effect is to cause the vernal equinox to drift westward along the ecliptic at a rate of roughly 50 seconds of arc per year, which may seem like a tiny amount but accumulates to nearly 1.5 degrees per century, a shift large enough to move stars noticeably from one constellation into another over the course of a few thousand years. The phenomenon was discovered by Hipparcos in ancient times, but measuring its rate with precision required centuries of careful observation and mathematical analysis. Simon Newcomb, the American-Canadian astronomer who worked at the United States Naval Observatory in Washington during the latter half of the 19th century, devoted much of his career to establishing the most accurate possible values for the fundamental constants of astronomy, including the rate of precession and its various components. Newcomb was a methodical and exacting scientist who approached his work with an almost mechanical patience, compiling and analyzing vast quantities of observational data to extract the underlying constants of nature with unprecedented accuracy. His system of astronomical constants, published in 1896, represented the culmination of decades of effort and became the foundation upon which all subsequent positional astronomy would build for nearly a century. The values he determined for precession, for the obliquity of the ecliptic, and for the various other parameters that describe the orientation and motion of Earth's axis were so carefully derived that they remained in official use until the 1980s. When improved observations and computational methods finally allowed for modest refinements. Newcomb's work on precession required him to disentangle several different effects that had previously been conflated or imprecisely separated. The dominant component, called lunisolar precession, arises from the gravitational torque exerted by the Sun and Moon on Earth's equatorial bulge, and this is the effect that causes the slow westward drift of the equinoxes. But there is also a smaller effect called planetary precession, which arises from the gravitational influence of the other planets on the plane of Earth's orbit, causing the ecliptic itself to shift slowly in space. The combination of these two effects, which partially cancel one another, gives the general precession in longitude, the net rate at which the vernal equinox moves westward along the ecliptic. Newcomb's refined values for these quantities superseded earlier determinations by Bessel and others, establishing a new standard that would serve as the basis for astronomical ephemerides and star catalogues well into the 20th century. But precession is not the only motion that complicates the reference frame. There is also nutation, a small nodding motion superimposed on the steady precessional drift, caused by variations in the gravitational forces exerted by the Sun and Moon as the geometry of the Earth-Moon-Sun system changes over time. The dominant term in nutation has a period of about 18.5 years, corresponding to the regression of the lunar nodes, and causes the celestial pole to describe a small ellipse superimposed on its precessional circle. Newcomb and his contemporaries worked out detailed mathematical expressions for nutation, allowing observers to correct their measured positions to account for this periodic wobble and thereby obtain coordinates that could be compared across different epochs. The concept of the fundamental catalogue emerged as a practical solution to the problem of establishing and maintaining a consistent reference frame over time. A fundamental catalogue is not merely a list of star positions measured at a single moment, but rather a carefully constructed system that provides both positions and proper motions for a selected set of reference stars, allowing astronomers to calculate where those stars should appear at any desired epoch. The proper motion of a star is its apparent angular velocity across the sky, measured in seconds of arc per year, and arises from the actual motion of the star through space combined with the Sun's own motion relative to the stellar background. By knowing both the position of a star at a reference epoch and its proper motion, one can extrapolate forward or backward in time to predict where the star should appear at any other epoch, a calculation that is essential for planning observations and for comparing data taken at different times. The German astronomers of the 19th and 20th centuries played a particularly important role in developing and maintaining fundamental catalogues, beginning with Friedrich Wilhelm August Argelander and continuing through a succession of workers at the observatories of Bonn, Berlin, and Heidelberg. The designation FK, standing for Fundamental Catalogue in German, came to denote the series of fundamental catalogues produced by this tradition, each successive version incorporating improved observations and refined methods. The FK3, completed in 1937, served for many years as the primary reference for positional astronomy, establishing the coordinate system to which other catalogues were referred. It was followed by the FK4, published in 1963, which represented a significant improvement in both the number of stars included and the accuracy of their positions and proper motions. The FK4 system, as it came to be known, defined the celestial reference frame for a generation of astronomers, providing the positions and proper motions of some 1,500 stars distributed across the sky. These fundamental stars served as anchor points to which all other positional measurements were ultimately referred, whether made photographically, visually, or by the new electronic methods that were beginning to emerge. The coordinate system of FK4 was defined by the adopted values for precession and other constants, values that traced their lineage back through Newcomb's work to the careful observations of earlier centuries. But as observations improved and as the years passed, systematic errors in FK4 became apparent. Discrepancies between the catalogue positions and the true positions of stars as revealed by increasingly precise measurements. Walter Frick, who directed the Astronomisches Röntgen Institute in Heidelberg from 1955 until his retirement, dedicated much of his career to the development of an improved fundamental catalogue that would address the limitations of FK4 and establish a more accurate reference frame for the coming decades. Frick was a quiet and meticulous worker who understood that the construction of a fundamental catalogue required not only excellent observations but also a deep understanding of the systematic errors that could creep into astronomical measurements. Under his leadership, the Heidelberg Institute accumulated and analyzed a vast body of observational data from around the world, comparing measurements from different observatories and instruments to identify and correct for systematic effects. The systematic differences between star catalogues are a fascinating study in the subtle sources of error that can affect astronomical measurements. Regional errors are variations in the accuracy of positions across different parts of the sky, arising perhaps from irregularities in the graduation of measuring circles or from atmospheric refraction that varies with zenith distance. The magnitude equation is a systematic error that depends on the brightness of the star being observed, often arising from the way in which the eye or the photographic plate responds differently to bright and faint images. The color equation is a similar effect that depends on the color of the star, caused by chromatic aberration in optical systems or by the varying sensitivity of detectors to different wavelengths of light. Identifying and correcting these systematic errors required careful comparison of multiple catalogues and the development of statistical methods to separate random from systematic effects. The FK5, published in 1988 under Frick's guidance, represented the culmination of these efforts, incorporating not only improved observations but also new theoretical developments in the treatment of precession and other fundamental constants. The FK5 adopted slightly revised values for the rate of precession, correcting small errors that had been identified in Newcomb's original determinations. It also included improved proper motions for the fundamental stars, derived from the comparison of positions measured over longer time baselines and with more accurate instruments. The result was a reference frame that was significantly more accurate than its predecessor, though still subject to the fundamental limitation that no truly fixed points exist in the heavens against which to anchor the coordinate system. This limitation, the absence of truly fixed reference points, is worth contemplating for a moment in the quiet of the evening. Every star in our galaxy is in motion, following its own orbit around the galactic center, so that the proper motions we measure are always relative to some adopted frame that is itself slowly drifting. The fundamental catalogues attempted to define an inertial reference frame, one that is not rotating with respect to the distant matter of the universe, but achieving this in practice required careful attention to the collective motion of the reference stars. If the proper motions of the fundamental stars were systematically in error, the entire coordinate system would slowly rotate, introducing spurious motions into the positions of all other celestial objects. Frick and his colleagues worked diligently to minimize such rotations, using observations of external galaxies and other distant objects to tie the FK5 frame as closely as possible to an inertial system. The designation of epochs, the moments in time to which catalogue positions are referred, has its own quiet history. For many years, astronomers used the Besselian year, named after Friedrich Bessel, which was defined in terms of the position of the Sun along the ecliptic and began at the instant when the mean longitude of the Sun reached a particular value. Besselian epochs were designated by the prefix B, as in B 1950.0, which was a commonly used reference epoch for mid-20th century catalogues. But the Besselian year had certain inconveniences, including the fact that it did not correspond exactly to the calendar year and varied slightly in length from one year to the next. The transition to the Julian year, a year of exactly 365 1/4 days, simplified certain calculations and was adopted along with the introduction of the FK5 system. Julian epochs are designated by the prefix J, as in J 2000.0, which has become the standard reference epoch for modern astrometry and is the epoch to which the FK5 positions were ultimately referred. The mathematics of transforming positions between different epochs involves the application of precession, proper motion, and other corrections in a carefully prescribed order. To bring a position from one epoch to another, the astronomer must first remove the effects of precession and nutation that were applied at the original epoch, then apply the star's proper motion to shift its position forward or backward in time, and finally apply the precession and nutation appropriate to the new epoch. These transformations can be expressed as matrix multiplications in which rotation matrices representing the various angular shifts are applied in sequence to the position vector of the star. The mathematics is not particularly difficult, but it requires meticulous attention to signs and conventions, and errors in these calculations can introduce systematic distortions into the resulting positions. The concept of the fundamental plane, the celestial equator projected from Earth's equator, provides the basic reference for declination measurements, while the intersection of this plane with the ecliptic plane defines the 0 point of right ascension. But because both planes are subject to slow variations, the definition of the reference frame must be tied to a specific moment in time, the adopted epoch, and the positions of stars at other epochs must be calculated by applying the appropriate corrections for the intervening interval. This is the mathematical machinery that underlies all positional astronomy, a framework of rotating coordinate systems and time-varying transformations that allows observers separated by centuries to compare their measurements and to understand the motions of the stars. The FK5, with its improved proper motions and its refined constants, served as the primary reference frame for the final decade before the revolution in astrometry brought about by space-based observations. Its positions were accurate to within a few hundredths of a second of arc, and its proper motions to within a few thousandths of a second of arc per year, representing the pinnacle of what could be achieved with ground-based optical observations. Yet even this remarkable accuracy would soon be surpassed by measurements from above the atmosphere, where the blurring effects of turbulent air could be eliminated and where the entire sky could be observed with a single, precisely calibrated instrument. The mathematics of celestial reference frames remains fundamental to all of astrometry, providing the conceptual and computational framework within which positions are expressed and compared. The equator, the ecliptic, and the equinox continue to serve as the basic elements of celestial coordinates, even as the definition of the reference frame has shifted from the positions of bright stars to the directions of distant radio sources billions of light-years away. The work of Newcomb and Frick and their many colleagues around the world established a tradition of precision and care that persists to this day, a quiet dedication to getting the numbers right that has enabled all the discoveries that depend upon knowing exactly where in the sky one is looking. And so, as we contemplate the mathematics of these reference frames, we may appreciate the patience and diligence of those who devoted their careers to determining the precise values of precession and proper motion, who compared catalogue against catalogue to identify systematic errors measured in fractions of a second of arc, and who worked steadily through the years to provide astronomers everywhere with a reliable and consistent system for describing the positions of the stars. It is work that proceeds largely unnoticed by the wider world, this careful maintenance of the celestial coordinate system, but it is essential to everything else that astronomy accomplishes, a foundation of measurement upon which all else is built. The stars will slowly overhead. The equinoxes drift westward along the ecliptic, and the reference frames that we construct to describe these motions are themselves the product of generations of patient observation and mathematical analysis, a quiet testament to the human desire to understand and to measure the cosmos in which we find ourselves. The story of how we came to measure the positions of stars with extraordinary precision takes a rather unexpected turn in the middle of the 20th century, when astronomers began to listen to the sky rather than simply looking at it. Radio waves, those gentle ripples of electromagnetic radiation with wavelengths far longer than visible light, had been discovered coming from space almost by accident in the early 1930s, and in the decades that followed, a small community of patient researchers worked to understand what the radio sky might tell us about the universe. What they could not have known at first was that their work would eventually provide the most stable and precise reference frame for measuring positions that humanity has ever constructed, a framework anchored not to nearby stars with their subtle drifts and wobbles, but to objects so impossibly distant that they appear to hang motionless against the fabric of space itself. The fundamental challenge that faced early radio astronomers was one of resolution, which is to say the ability to distinguish fine details and pinpoint exactly where a radio signal was coming from. The resolution of any telescope, whether it gathers light or radio waves, depends upon the ratio of the wavelength being observed to the diameter of the collecting aperture, and since radio waves are roughly 1,000,000 times longer than visible light, a radio telescope would need to be roughly 1,000,000 times larger than an optical telescope to achieve the same sharpness of vision. A single radio dish, even one as magnificently large as the 250-foot instrument at Jodrell Bank in England or the great dish nestled in the limestone hills of Arecibo, could only see the radio sky as a rather blurry impression, unable to pinpoint the precise locations of the sources it detected. It was this problem that occupied the mind of Martin Ryle at the Cavendish Laboratory in Cambridge during the years following the Second World War. Ryle had spent the war years working on radar systems, and like many physicists of his generation, He brought the techniques and intuitions of that work into peacetime research. He understood that radio waves, being waves, carry information not only in their intensity but also in their phase. That subtle property describing where each wave sits in its endless cycle of peaks and troughs. If one could record the signals from two separate antennas and carefully compare not just how strong the signals were but how they aligned with one another in phase, one could extract information about the structure of the source that neither antenna could provide alone. This technique, known as interferometry, was not entirely new, but Ryle and his colleagues developed it with a patience and rigor that would transform the field. The principle underlying radio interferometry is rather beautiful in its simplicity, though the practice requires considerable care. When radio waves from a distant source arrive at two antennas separated by some distance, they reach each antenna at very slightly different times, except when the source happens to lie exactly perpendicular to the line connecting them. This tiny time difference manifests as a difference in phase, and by measuring this phase difference precisely, one can determine the direction to the source with an accuracy that depends not on the size of either individual antenna but on the distance between them, which astronomers call the baseline. Two modest antennas separated by a mile can achieve the same angular resolution as a single dish a mile across, though of course they collect far less total signal and cannot fill in all the details that such an enormous dish would reveal. What Ryle contributed was the insight that by moving the antennas to different separations over time, or by allowing the rotation of the Earth to change the effective orientation of a fixed baseline as seen from the radio source, one could gradually build up the same information that a much larger aperture would collect all at once. This technique, which Ryle called aperture synthesis, required patient observation over many hours or even days, and it required careful mathematical processing to combine all the accumulated measurements into a single coherent image. The mathematics involved, a form of Fourier transformation, was well understood but computationally demanding, and the development of aperture synthesis proceeded hand in hand with the development of electronic computers capable of performing the necessary calculations. Throughout the 1950s and 60s, Ryle and his group at Cambridge built a series of increasingly sophisticated interferometer arrays, each one probing the radio sky with greater clarity than the last. The 1 mile telescope, completed in 1964, used 3 dishes that could be moved along a railway track to provide baselines up to 1 mile in length. The 5-kilometer telescope, which became operational in 1972, extended this approach to even longer baselines. With these instruments, Cambridge astronomers compiled catalogues of radio sources, numbered according to their position in the sky and their sequence of discovery, and it was from these catalogues that some of the most important objects in 20th-century astronomy would emerge. The third Cambridge catalogue, known simply as 3C, listed several hundred radio sources, most of which were mysterious smudges of radio emission with no obvious counterpart visible through optical telescopes. Identifying what these sources actually were required knowing their positions with sufficient precision that astronomers could point an optical telescope at exactly the right patch of sky. And this was no simple matter when the radio positions were uncertain by several arc-minutes. A rather clever technique for improving these positions involved watching what happened when the moon passed in front of a radio source, an event called a lunar occultation. As the sharp edge of the moon covers the source, the radio signal cuts off abruptly, and by timing this moment precisely from multiple locations, one can triangulate the position of the source against the well-known position of the lunar limb. In August of 1962, A young astronomer named Cyril Hazard used this technique to determine the position of a radio source catalogued as 3C273, observing from the Parkes Radio Telescope in New South Wales. That great dish sitting quietly amid the sheep paddocks of the Australian countryside. The occultation measurements revealed something unexpected. The source was actually double, consisting of two components separated by about 20 arcseconds. And more importantly, the position was now known precisely enough for optical astronomers to investigate. When Martin Schmidt at Palomar examined the optical counterpart, he found what appeared to be a faint blue star, but its spectrum contained emission lines shifted to wavelengths that made no sense for any known type of star. After some puzzlement, Schmidt realized that the lines were ordinary hydrogen emission, but redshifted by an amount that implied the object was receding at roughly 15% of the speed of light, placing it at a distance of over 2 billion light-years if the redshift followed the normal expansion of the universe. This was the first identification of a quasar, a quasi-stellar radio source, and it opened an entirely new chapter in our understanding of the cosmos, revealing that the centers of some very distant galaxies harbor tremendously luminous and energetic phenomena. For our purposes in the history of astrometry, the important point is that quasars, being so extraordinarily far away, display no detectable proper motion across the sky. While nearby stars shift their positions measurably over years and decades as they orbit through the galaxy, and even the most distant stars in our own Milky Way show tiny movements that accumulate over centuries, quasars are so remote that any motion they possess is utterly imperceptible. This makes them ideal reference points, fixed markers against which all other motions can be measured, and the recognition of this fact would eventually lead to a fundamental transformation in how we define the coordinate system of the sky. The precision with which radio interferometry could measure positions continued to improve as astronomers pushed the technique to ever longer baselines. By the late 1960s, groups in Canada, the United States, and the Soviet Union were conducting experiments in which radio signals were recorded at widely separated telescopes simultaneously, with the recordings synchronized by atomic clocks of exceptional stability. These recordings were then brought together and compared, a process called correlation, to extract the phase differences that encoded positional information. This technique became known as Very Long Baseline Interferometry, or VLBI, and it allowed baselines stretching not merely across a continent but eventually across the diameter of the Earth itself. The technical challenges of VLBI were formidable. The radio signals had to be recorded with precise timestamps referenced to atomic frequency standards, initially hydrogen maser clocks that maintained their timing to within a few nanoseconds over the hours required for an observation. The recordings, initially made on magnetic tape and later on more advanced media, had to be transported physically to a central processing facility where a special-purpose computer called a correlator would compare the signals from each pair of telescopes, hunting for the pattern of matching and mismatching waves that revealed the geometry of the observation. Any error in the clocks, any uncertainty in the positions of the antennas, any unaccounted-for delay in the electronics would corrupt the result, and so the development of VLBI required painstaking attention to every link in a long chain of measurement. By the middle of the 1970s, VLBI observations were routinely achieving angular resolutions of a few milliarcseconds, 1,000 times better than the best optical observations of that era and roughly equivalent to reading a newspaper headline from 1,000 kilometers away. The radio telescopes involved in these observations spanned the globe, including the old familiar names of the early radio astronomy era such as Jodrell Bank in England and Parkes in Australia, as well as newer facilities like the 100-meter dish at Effelsberg in Germany, the antennas at Green Bank in West Virginia, and the network of stations maintained by the Jet Propulsion Laboratory's Deep Space Network, whose primary purpose was communicating with spacecraft but which contributed valuable observations to VLBI campaigns. The Deep Space Network deserves particular mention in this history, for its three major stations, located in California, Spain, and Australia and spaced roughly equally around the globe, were ideally positioned to observe any radio source in the sky and were equipped with the atomic time standards and precise tracking systems necessary for VLBI. The engineers and scientists at the Jet Propulsion Laboratory contributed not only observing time but also expertise in the analysis of VLBI data, developing techniques for modeling the tiny effects that could bias the measurements, such as the bending of radio waves as they pass through the Earth's atmosphere, the delay introduced by water vapor, and the relativistic corrections required because the clocks at each station were moving and experiencing gravity differently. As VLBI precision improved through the 1970s and 80s, a remarkable realization emerged from the data. The technique was so sensitive to the exact distances between antennas that it could detect changes in those distances at the level of a few centimeters, and when the same pairs of telescopes were observed repeatedly over years, those changes accumulated in a consistent pattern. The baselines between North America and Europe were growing longer, while the baselines across the Pacific showed different trends. What VLBI was detecting, quite incidentally to its astronomical purpose, was the motion of tectonic plates, the slow drift of the continents across the surface of the Earth. The African plate was rotating, the Australian plate was moving northward, and the Atlantic Ocean was widening at a rate of a few centimeters per year, all of which was now directly measurable through the patient comparison of quasar signals recorded at distant antennas. This geodetic application of VLBI connected the measurement of the heavens to the measurement of the Earth itself in a way that would have delighted the astronomers of earlier centuries who understood that precise astronomy was inseparable from precise knowledge of our own planet. The International Earth Rotation Service began using VLBI observations to monitor not just the positions of quasars but also the orientation and rotation of the Earth, tracking tiny wobbles and fluctuations in the length of the day that arise from the sloshing of the oceans, the movement of air masses, and the coupling between the Earth's liquid core and its solid mantle. The celestial reference frame and the terrestrial reference frame were becoming linked through a common set of observations. Through the 1980s and into the 1990s, the accumulation of VLBI data made it possible to define a new kind of celestial reference frame, one based not on the positions of nearby stars but on the positions of compact extragalactic radio sources, primarily quasars, and the nuclei of active galaxies. The effort to establish this frame was international and painstaking, involving observations from dozens of antennas on every continent, including stations in Antarctica, and requiring careful attention to systematic errors that might bias the entire framework. The positions of several hundred defining sources were measured repeatedly, and the consistency of those measurements was tested against every known source of error. In 1998, the International Astronomical Union adopted the International Celestial Reference Frame, known as the ICRF, as the fundamental reference for the positions of all celestial objects. This frame was defined by the positions of 212 compact radio sources, whose locations had been determined to within about half a milliarcsecond, and it replaced the older system based on the positions of bright stars that had served astronomy for centuries. The advantages were profound, for the extragalactic sources showed no detectable proper motion, no parallax shift with the Earth's orbit, and no aberration effects beyond those that could be precisely calculated and removed. The reference frame was, for all practical purposes, inertial, fixed with respect to the universe at large rather than drifting imperceptibly with the motions of our local stellar neighborhood. The development of the ICRF represented a philosophical as well as a practical shift in how astronomers thought about the coordinate system of the sky. For centuries, the reference frame had been tied to whatever stars were bright enough and well observed enough to serve as standards, and the frame had slowly rotated as those stars moved against the background of more distant objects. Now the frame was tied to the most distant objects observable, and any rotation of the frame could only arise from some systematic error in the observations themselves. The local motions of stars, including our own sun's journey through the galaxy, were now measured against a backdrop that did not share in those motions, a fixed stage against which the choreography of the Milky Way could be precisely mapped. The technique of VLBI that made all of this possible involves, at its heart, the correlation of signals recorded at different antennas. When radio waves from a quasar arrive at an antenna, they induce a tiny oscillating voltage that can be amplified and recorded. The recording preserves not just the strength of the signal but its rapidly varying phase, cycling millions or billions of times per second depending on the observing frequency. When recordings from two antennas are brought together and compared, the correlator searches for the time offset and rate of change of offset that makes the signals align most closely, maximizing the correlation between them. This optimal alignment encodes information about the geometry of the observation, telling us the projection of the baseline vector onto the direction to the source, and by combining many such measurements from different source directions and different baseline orientations, the complete geometry can be reconstructed. The early pioneers of VLBI worked at observatories whose names evoke the mid-century expansion of radio astronomy into new territories. Jodrell Bank, with its great Lovell telescope looming over the Cheshire Plain, had been observing the radio sky since 1957 and contributed to interferometry experiments for decades. Parkes, that patient sentinel in the Australian bush, brought the southern sky into view and provided crucial baselines to Northern Hemisphere stations. Green Bank, nestled in a radio-quiet valley of the Appalachian Mountains, offered an environment relatively free from interference and hosted some of the earliest transatlantic VLBI experiments. Each of these facilities, and dozens of others around the world, contributed their observations to the collective enterprise of mapping the radio sky and establishing the reference frame upon which all subsequent measurements would rest. The story of radio interferometry is one of patient accumulation, of observations gathered night after night and year after year, of gradual refinement as systematic errors were identified and corrected, of international collaboration in which data from antennas on opposite sides of the world were combined to achieve what no single instrument could accomplish alone. It is a story without heroes in the dramatic sense. Though Martin Ryle received the Nobel Prize in Physics in 1974 for his work on aperture synthesis, sharing the award with Anthony Hewish, and though many other individuals contributed essential insights and tireless effort. More than any single achievement, the development of radio astrometry represents the kind of progress that emerges from sustained attention to detail, from the willingness to improve measurements by small increments over long periods, and from the recognition that precision is its own reward, revealing truths about the universe that would otherwise remain hidden. As we drift gently toward sleep, we can hold in our minds the image of those great dishes turning slowly beneath the stars, listening to whispers from across the universe, whispers that carry information about positions measured to the thousandth of an arcsecond, whispers that tell us how the continents move and how the Earth turns, whispers that anchor our maps of the sky to reference points so distant that they might as well be fixed for eternity. And in that quietness between one measurement and the next, the universe reveals itself to those who have the patience to listen. When astronomers gaze upward through the Earth's atmosphere, they are looking through a restless ocean of air, a turbulent medium that never quite settles into stillness. This atmosphere, which sustains all life on our planet and scatters sunlight into the blue of day and the red of sunset, presents a persistent and fundamental obstacle to the precise measurement of stellar positions. The phenomenon that astronomers call seeing refers to the blurring and twinkling of starlight as it passes through layers of air at different temperatures and densities, each layer bending the light in slightly different directions, each moment bringing a new configuration of distortion. On the very best nights, at the most carefully chosen observatory sites, the seeing might allow a star's position to be measured to perhaps half an arcsecond or so, and with great patience and many repeated observations over many years, astronomers could reduce this uncertainty somewhat further through statistical averaging. Yet there remained a barrier, a ceiling of precision that no amount of careful technique or patient observation could penetrate, because the atmosphere itself imposed limits that were simply insurmountable from the surface of the Earth. The air above an observatory is never truly at rest. Even on what appears to be a perfectly calm and cloudless night, invisible currents of warmer and cooler air rise and fall and drift sideways, creating pockets of slightly different refractive index that act as weak and constantly shifting lenses. A beam of starlight, traveling for years or centuries or millennia across the emptiness of space in perfectly straight lines, encounters in its final fraction of a second this chaotic boundary layer of atmosphere, and emerges somewhat scrambled, its wave front distorted, its apparent direction jittering back and forth by tiny but measurable amounts. For the measurement of stellar parallax, which requires detecting the minuscule annual shift in a star's position caused by the Earth's orbital motion, this atmospheric blurring sets a practical limit of perhaps 10 to 20 milliarcseconds under ordinary circumstances, and even extraordinary efforts rarely pushed beyond a few milliarcseconds of precision. This was sufficient for nearby stars, those within perhaps 100 parsecs or so, but the vast majority of stars in our galaxy remained beyond the reach of reliable parallax measurement, their distances known only approximately from indirect methods of varying reliability. Astronomers had long understood that the ideal solution would be to place a telescope entirely above the atmosphere, in the vacuum of space, where starlight would arrive undisturbed by any intervening medium and where positions could in principle be measured with far greater precision. The idea of space-based astronomy became increasingly practical during the 1960s, as both the American and Soviet space programs demonstrated the ability to launch and operate scientific instruments in orbit. Early space telescopes focused primarily on observing wavelengths of light that the atmosphere absorbs, such as ultraviolet and X-ray radiation, but some astronomers began to consider whether a telescope designed specifically for astrometry might achieve the long-sought goal of milliarcsecond precision across the entire sky. Among the first to develop a detailed proposal for a space astrometry mission was Pierre Lacroute, a French astronomer working at the Strasbourg Observatory, who had spent many years contemplating the fundamental limitations of ground-based star catalogues. Lacroute understood that traditional astrometry suffered from two distinct problems: the atmospheric seeing that blurred individual measurements and the more subtle issue of systematic errors that accumulated when trying to connect observations made in different parts of the sky at different times. A telescope on the ground can only observe one region of sky at a time, and building a coherent all-sky reference frame requires stitching together many overlapping observations, a process that inevitably allows small errors to propagate and accumulate. Lacroute conceived of an elegant solution to both problems: a space telescope that would observe two widely separated regions of sky simultaneously, comparing the positions of stars in one field directly against stars in the other field, thereby creating a rigid geometrical framework that would tie the entire celestial sphere together in a single consistent reference system. In 1967, Lacroute presented his proposal to the French National Space Agency, known by its initials SNES, describing a satellite that would carry a telescope with two entrance apertures pointed in different directions, separated by a large fixed angle. The light from both fields of view would be combined onto a single focal plane, so that stars from opposite sides of the sky would appear side by side in the same image, their relative positions measured with a precision limited only by the optics and detectors rather than by atmospheric seeing. The specific angle between the two viewing directions, which Lacroute called the basic angle, would need to be extremely stable and precisely known, so that the comparison between the two fields would yield absolute positions on the sky rather than merely relative positions within each field. This concept of a beam-combining telescope viewing two fields separated by a large basic angle would become the defining characteristic of the mission that eventually emerged from Lacroute's original vision. The proposal was ambitious and technically demanding, and SNES, while interested, recognized that the resources required would exceed what France alone could reasonably provide. Lacroute continued to develop and refine his ideas through the late 1960s and early 1970s, presenting them at international meetings and attracting the interest of other European astronomers who saw the potential for a truly transformative advance in fundamental astronomy. The concept gradually evolved and gained support, though the path from initial proposal to approved mission would prove to be long and winding, requiring more than a decade of further study and advocacy. During this same period, American astronomers were also contemplating the possibilities of space astrometry, though their proposals took somewhat different forms. In the United States, various concepts were studied under names such as the Astrometric Telescope Facility, which envisioned a large space telescope dedicated primarily to parallax measurements of individual stars of particular scientific interest. The American approach tended to emphasize pointed observations of selected targets rather than an all-sky survey, reflecting different scientific priorities and different assumptions about what was technically achievable. Some American proposals involved very long baseline interferometry in space, using multiple separated spacecraft to achieve the extremely precise angular measurements needed for astrometry at the microarcsecond level. These competing visions represented genuine scientific alternatives, each with its own strengths and limitations, and the eventual European success with the Hipparcos mission should not be taken to mean that the American approaches were without merit. The European Space Agency, formed in 1975 from the merger of earlier European space organizations, provided a natural framework for international cooperation on large scientific projects that no single European nation could easily undertake alone. Through the late 1970s, the Lacroute concept was studied and refined by working groups of European astronomers and engineers, who addressed the many technical challenges that such a mission would face and gradually built confidence that the scientific goals were achievable with existing or foreseeable technology. In 1980, the European Space Agency formally adopted the mission, now named Hipparcos as an acronym for High-Precision Parallax Collecting Satellite, and also as a tribute to the ancient Greek astronomer Hipparcos, who had compiled one of the first known star catalogues more than 2,000 years earlier. The adoption of Hipparcos marked a commitment of substantial resources and international cooperation toward a goal that had seemed almost impossibly ambitious only a decade or two before. The measurement principle at the heart of Hipparcos was elegant in concept but demanding in execution. The satellite would carry a single telescope with two entrance apertures, separated by what was called the basic angle of 58 degrees and 2/3 of a degree, a value chosen through careful analysis of how the geometry of the observations would contribute to the precision of the final catalogue. Light entering through both apertures would be reflected by a beam-combining mirror onto a single primary mirror and thence to a shared focal plane, so that stars from two regions of sky separated by this basic angle would form images side by side. As the satellite slowly rotated, different pairs of sky regions would drift across the field of view, and over the course of the mission, every part of the sky would be observed many times in combination with many other parts of the sky, creating a dense web of angular measurements that would ultimately define the positions of all observed stars relative to one another with unprecedented precision. The choice of the basic angle was not arbitrary but reflected a careful optimization of the mission's scientific return. An angle of 90 degrees would have provided the most direct measurement of right ascension differences, but would have left some geometric ambiguities unresolved. An angle of 60 degrees would have created complications with threefold symmetry in the sky coverage. The value of 58 degrees and 2/3 represented a compromise that avoided these difficulties while still providing strong geometric constraints on the final solution. The slight oddness of this angle compared to round numbers like 60 or 90 degrees was a consequence of the mathematics of the problem rather than any particular engineering consideration. The technological challenges facing the Hipparcos mission were numerous and severe, beginning with the need for extraordinary thermal stability in the spacecraft and its optical system. The basic angle between the two viewing directions needed to remain constant to within a few milliarcseconds over the course of observations, which translated to mechanical stability at the level of nanometers over structures spanning tens of centimeters. Any change in temperature would cause the structure to expand or contract, potentially shifting the basic angle and corrupting the measurements. The solution involved careful choice of materials with very low coefficients of thermal expansion, elaborate thermal insulation and temperature control systems, and continuous monitoring of the basic angle through observations of stars themselves. The spacecraft would operate in a carefully controlled thermal environment, shielded from direct sunlight and maintained at a stable temperature throughout its mission. Attitude control presented another formidable challenge, as the satellite needed to rotate slowly and smoothly while pointing with great precision at its target fields. The rotation, or scanning motion, would cause stars to drift across the focal plane at a predictable rate, and any departure from smooth rotation would blur the measurements and reduce their precision. The Hipparcos spacecraft used a system of reaction wheels and cold gas thrusters to maintain its orientation, with the reaction wheels providing fine control of the rotation rate and the thrusters periodically removing accumulated angular momentum. The required pointing stability was at the level of a few milliarcseconds, comparable to the width of a human hair seen from a distance of 10 kilometers. And maintaining this stability over observations lasting many seconds while the spacecraft was subjected to varying gravitational and radiation forces required exquisitely precise control systems. The choice of detector for the focal plane was critical to the mission's success and represented a significant departure from conventional astronomical practice. Rather than recording images of the star field directly, Hipparcos used a system based on a modulating grid, an array of alternating transparent and opaque strips placed in the focal plane, combined with an image dissector tube that could measure the light from a small selectable region of the field. As a star's image drifted across the modulating grid due to the satellite's rotation, the light would be alternately transmitted and blocked, producing a regular pattern of intensity variations, whose phase encoded the star's position with great precision. The image dissector tube was a type of photomultiplier that could be electronically steered to select light from a particular direction, allowing the system to monitor multiple stars in sequence as they crossed the field of view. This approach of using a modulating grid and photon counting detector rather than a conventional imaging detector offered several advantages for the specific requirements of astrometry. The modulating grid provided a built-in reference scale against which stellar positions could be measured, and the photon counting capability of the image dissector tube allowed precise determination of the phase of the modulation pattern even for relatively faint stars. The periodic structure of the grid meant that positions were determined modulo the grid spacing, but this ambiguity could be resolved through careful bookkeeping and by using a second grid with a different spacing. The entire system was optimized for the precise measurement of one-dimensional positions along the direction of the satellite scan, with the full two-dimensional positions on the sky emerging from the combination of many scans at different orientations. The development of this detector system required years of careful engineering and testing. The modulating grid needed to be manufactured with extraordinary precision, its lines straight and evenly spaced to within tiny fractions of a micrometer. The image dissector tube needed to respond quickly and reliably to the electronic commands that steered its field of view from one star to another. The photon counting electronics needed to operate continuously for years without degradation, accumulating the millions of individual measurements that would ultimately yield the final catalog positions. Each component was tested extensively on the ground, but some aspects of the system's performance could only be verified in the actual space environment. Before the satellite could observe stars, those stars needed to be identified and their approximate positions catalogued with sufficient accuracy to allow the spacecraft to find and track them. This preparatory work involved an extensive program of ground-based observations, compiling what was called the input catalog from existing star catalogs supplemented by new measurements. The input catalog contained approximately 118,000 stars selected for observation by Hipparcos, chosen to include a scientifically valuable sample spanning a wide range of stellar types, distances, and locations on the sky. Each star's position needed to be known to within about 1 arcsecond so that the spacecraft's observation planning software could predict when and where each star would appear in the field of view. The preparation of the input catalog was itself a substantial undertaking, involving astronomers at many observatories who contributed their time and expertise to this essential supporting work. The construction of the Hipparcos spacecraft was entrusted to a consortium of European aerospace companies led by Maitre Marconi Space, bringing together expertise in satellite structures, thermal control, attitude determination, and scientific instrumentation from across the continent. The spacecraft was designed to operate in a geostationary transfer orbit, a highly elliptical path that would carry it from a low point near Earth out to a high point at geostationary distance, completing one orbit approximately every 10 hours. This orbit had been chosen as a compromise between the desire for a high, stable geostationary orbit and the limitations of the available launch vehicle, the European Ariane rocket. The plan called for the spacecraft's own propulsion system to circularize the orbit at geostationary altitude after launch, placing it in a stable position from which it could observe the sky continuously without interference from Earth's shadow or radiation belts. The satellite structure was built around a central optical assembly containing the beam-combining mirror, primary mirror, and focal plane instrumentation, all mounted on a framework of carbon fiber reinforced plastic chosen for its exceptional dimensional stability. The optical elements were fabricated from a ceramic material called Zerador, which has a coefficient of thermal expansion very close to zero, meaning that temperature changes cause almost no change in size. Surrounding this optical core were the support systems, including solar panels for electrical power, antennas for communication with ground stations, star trackers for course attitude determination, and the reaction wheels and thrusters for attitude control. The complete spacecraft weighed approximately 1,100 kilograms and measured roughly 3 meters across its solar panels. The software systems for Hipparcos were as complex as the hardware, involving both the onboard computers that controlled the satellite's operations and the ground-based systems that would process the raw data into scientific results. The onboard software needed to manage the scanning motion, select stars for observation, steer the image dissector tube from star to star, and record the photon counts along with precise timing information. The ground software faced the even more daunting task of combining millions of individual observations into a self-consistent catalogue of stellar positions, proper motions, and parallaxes. This data reduction problem was unprecedented in its scale and complexity, requiring new mathematical techniques and substantial computing resources that pushed the boundaries of what was available in the late 1980s. The preparations for launch extended over many years, as the spacecraft was assembled, tested, and integrated with its launch vehicle. Environmental testing subjected the satellite to the vibrations, acoustic noise, and temperature extremes it would experience during launch and operation, verifying that all systems would survive and function correctly. Functional testing confirmed that the scientific instruments performed according to specifications and that the control systems maintained the required pointing stability. The input catalog was finalized and loaded into the mission planning computers. Ground stations were prepared to receive the satellite's transmissions and send commands. The scientific community prepared for the years of data analysis that would follow the observing program. All of these preparations converged toward a launch date in the summer of 1989, when the accumulated work of more than 2 decades would finally be tested against the reality of spaceflight and observation. The morning of August 8, 1989, brought with it the particular stillness that precedes great undertakings, and at the Guiana Space Center in Kourou, along the northeastern coast of South America, the Ariane 4 rocket stood ready upon its launch pad, carrying within its payload ferrying a spacecraft that would fundamentally alter our understanding of the positions and motions of the stars. The Hipparcos satellite, named in honor of the ancient Greek astronomer Hipparcos who had catalogued the heavens more than 2,000 years earlier, represented the culmination of decades of planning and the hopes of astronomers across Europe who had long dreamed of measuring stellar positions from above the blurring veil of Earth's atmosphere. The launch proceeded smoothly, the rocket lifting away from the equatorial launch site and arcing eastward over the Atlantic Ocean, its stages separating in sequence as the spacecraft climbed toward its intended destination. A circular geostationary orbit some 36,000 kilometers above the Earth's surface, where it would appear to hang motionless relative to the ground stations below. Yet space exploration has always been an endeavor marked by the unexpected, and the Hipparcos mission would prove no exception to this gentle truth. The apogee boost motor, which was meant to circularize the orbit once the spacecraft had reached its highest point above Earth, failed to ignite, leaving Hipparcos stranded in its highly elliptical transfer orbit, swooping close to Earth at a mere 500 kilometers at perigee and then climbing out to nearly 36,000 kilometers at apogee, completing each orbit not in the planned 24 hours but in approximately 10 hours and 40 minutes. The spacecraft that had been designed to observe the sky from a serene and stable vantage point now found itself plunging repeatedly through the Van Allen radiation belts, those regions of charged particles trapped by Earth's magnetic field, which threatened to degrade its sensitive detectors far more rapidly than anticipated. For a time, it seemed possible that the mission might be lost entirely, that years of preparation and the substantial investment of the European Space Agency might yield nothing of scientific value. But the engineers and scientists who had designed Hipparcos were not easily discouraged, and in the weeks and months that followed the launch, they devised an ingenious recovery plan that would allow the mission to proceed, albeit with significant modifications to its original concept of operations. Rather than relying upon a single ground station to communicate with a satellite fixed above one point on Earth, the recovery plan utilized a network of ground stations distributed around the globe, including facilities in Germany, Australia, and elsewhere, which could maintain contact with the spacecraft as it traced its elongated path around the planet. The observation schedule was carefully redesigned to avoid the periods when the spacecraft passed through the most intense regions of radiation, and the solar panels were oriented to minimize the damage from charged particles during these passages. Through these adaptations and through the considerable skill of the operations team, Hipparcos began its scientific observations in November of 1989, just a few months after launch, and it would continue gathering data for nearly 4 years, far exceeding the initial predictions of those who had feared the mission might last only months in its hostile orbital environment. The manner in which Hipparcos observed the sky was both elegant and methodical, following what is known as a scanning law that allowed the satellite to build up measurements of stars across the entire celestial sphere through the patient accumulation of individual observations over time. The spacecraft rotated slowly about its own axis, completing one full revolution approximately every 2 hours and 8 minutes, and as it spun, its telescope swept a great circle across the sky, briefly measuring each star that passed through its field of view. But this spinning motion alone would have traced the same circle repeatedly, observing only a narrow band of stars while leaving the rest of the sky untouched. And so the spacecraft's spin axis was itself made to precess, to slowly wobble like the axis of a spinning top, completing one full precession cycle every 57 days. The combination of these two motions, the steady spin about the axis and the gradual precession of the axis itself, caused the telescope to sweep across different parts of the sky with each rotation, eventually providing coverage of the entire celestial sphere. Each star within the observing program was measured many times over the course of the mission, sometimes dozens of times, sometimes more than 100 times. And it was from these repeated measurements, gathered over the years, that the positions, proper motions, and parallaxes of the stars could be determined with such remarkable precision. At the heart of the Hipparcos telescope was a beam-combining mirror of unusual design, a mirror that brought together light from two separate fields of view pointing in directions separated by a fixed angle of 58 degrees. This arrangement, known as a basic angle, was fundamental to the mission's ability to measure absolute positions rather than merely relative ones, for by simultaneously observing stars in two widely separated regions of the sky, the spacecraft could build up a rigid framework of angular measurements that spanned the entire celestial sphere. The detectors behind this mirror were not the charge-coupled devices that have become common in modern telescopes, but rather image dissector tubes, a form of photomultiplier that could track the position of a star's image as it drifted across the field of view with each rotation of the spacecraft. A modulating grid, a precise pattern of transparent and opaque bands, was placed in front of the detector, and as a star's image moved across this grid, the light from the star was alternately transmitted and blocked, producing a signal that varied in a predictable manner and from which the exact position of the star at each moment could be calculated. The primary objective of Hipparcos was to measure with the highest possible precision a carefully selected catalogue of stars, known as the input catalogue, which had been assembled in the years before launch and contained some 118,000 objects chosen to meet a variety of scientific goals. These stars had been selected through a proposal process in which astronomers from across Europe and beyond had submitted requests for particular objects to be included, and the final catalogue represented a balance among many competing priorities, including the desire for bright nearby stars whose parallaxes could reveal their distances, more distant stars that could be used to calibrate the cosmic distance ladder, variable stars and binary stars whose properties might be better understood through precise positional measurements, and stars distributed across the sky to provide a uniform reference frame. The selection had been coordinated by a team led by Catherine Turin of the Paris Observatory, who brought to the task both scientific insight and considerable organizational skill, ensuring that the input catalogue would serve the needs of stellar astronomy for decades to come. But the designers of Hipparcos had recognized that the satellite would inevitably detect many stars beyond those in the primary observing program, fainter stars that happened to fall within the fields of view as the telescope scanned across the sky, and they had included a secondary detection system known as the Star Mapper to take advantage of this opportunity. The Star Mapper consisted of a separate set of slits and detectors positioned at the edge of the main field of view, and it recorded the transits of stars as they passed across these slits during each rotation of the spacecraft. The data from the Star Mapper were processed through what became known as the Tycho experiment, named for the Danish astronomer Tycho Brahe, whose own observations 4 centuries earlier had set new standards of precision for his time. While the Tycho measurements could not match the extraordinary accuracy of the main Hipparcos detector, they nevertheless provided positions, proper motions, and two-color photometry for a vastly larger sample of stars, ultimately yielding a catalogue of over 1 million objects, later extended to nearly 2.5 million in a revised version known as Tycho II. This secondary catalogue, though less precise than the primary Hipparcos results, proved enormously valuable for studies requiring statistical samples of stars or for providing reference stars in regions where the main catalogue was sparse. The processing of the data returned by Hipparcos was a task of staggering complexity, requiring the coordinated efforts of scientists and computing facilities across Europe over a period of many years. 2 independent consortia were established to carry out this analysis, each developing its own methods and software, so that the final results could be compared and validated through independent verification. The first of these consortia was known by the acronym FAST, standing for Fundamental Astronomy by Space Techniques, and it was led by Jean Kovalevsky of the Côte d'Azur Observatory in France, bringing together researchers from institutions in France, Italy, and the Netherlands. The second consortium was called NDAC, the Northern Data Analysis Consortium, and it was led by Lennart Lindegren of Lund Observatory in Sweden, with contributions from researchers in Denmark, Sweden, Germany, and the United Kingdom. The 2 consortia worked independently but in parallel, processing the same raw data through their separate pipelines and then comparing their results at regular intervals to identify and resolve any discrepancies. Leonard Lindegren, who had been involved with the Hipparcos concept since its earliest days, brought to the Northern Data Analysis Consortium a deep mathematical understanding of the astrometric problem and a meticulous attention to the subtle systematic errors that could corrupt the results if not properly accounted for. His work on the calibration of the instrument and the modeling of its behavior proved essential to achieving the mission's scientific goals, and his contributions would establish him as one of the leading figures in space astrometry, a role he would continue to play in the subsequent Gaia mission decades later. Erik Hogg, a Danish astronomer who had long championed the idea of astrometry from space, was responsible for the conception and development of the Tycho experiment, recognizing that the star mapper data could yield a valuable scientific product in its own right, rather than serving merely as an aid to the spacecraft's attitude determination. His vision for extracting the maximum possible science from every photon detected by the spacecraft helped to ensure that Hipparcos would exceed its original scientific goals by a considerable margin. The mission continued its observations until March of 1993, when the accumulating radiation damage to the spacecraft's systems, combined with the degradation of its gyroscopes and other components, finally brought the operational phase to a close. By that time, Hipparcos had observed for nearly 3.5 years, far longer than the pessimistic early estimates had suggested might be possible given the failed orbit insertion, and the volume of data it had returned was enormous, comprising millions of individual measurements that would occupy the processing teams for years thereafter. The raw telemetry filled magnetic tapes by the hundreds, each containing the encoded signals of stellar transits across the modulating grid, spacecraft attitude measurements from the star mappers, and housekeeping data recording the health and status of the satellite systems. Transforming this torrent of raw data into a coherent scientific catalogue required not only substantial computing resources, which by the standards of that era were considerable, but also sustained intellectual effort from the researchers who had to understand and account for every instrumental effect that might bias the final results. The two consortia continued their parallel processing efforts through the mid-1990s, gradually refining their solutions and converging toward a final catalogue that would be published in 1997. The comparison between the FAST and NDAC results provided confidence that the methods were sound, for when two independent teams using different approaches arrive at the same answers, there is good reason to trust that those answers reflect genuine properties of the stars rather than artifacts of the processing. The final merging of the two solutions into a single catalogue required careful attention to the weights assigned to each consortium's contribution, and the result was a product that represented the best possible extraction of information from the Hipparcos data stream. Jean Kovalevsky, who had led the FAST consortium, played a central role in this final synthesis, drawing upon his extensive experience in fundamental astronomy to ensure that the catalogue met the highest standards of rigor. The Hipparcos catalogue, when it was released to the astronomical community, contained precise positions, parallaxes, and proper motions for approximately 118,000 stars, matching the size of the original input catalogue. The positions were measured with a median precision of about 1 milliarcsecond, a thousandth of an arcsecond, which represented an improvement of nearly 2 orders of magnitude over the best ground-based catalogues then available. The parallaxes, those tiny angular shifts that reveal the distances to the stars, achieved a similar precision, allowing direct distance determinations for stars out to several hundred parsecs, far beyond the reach of earlier parallax surveys. The proper motions, measuring the gradual drift of each star across the sky due to its actual motion through space, were determined with sufficient accuracy that they could be reliably extrapolated backward and forward in time over intervals of centuries, revealing the past and future positions of the stars with unprecedented fidelity. Catherine Turin, who had coordinated the assembly of the input catalogue before launch, continued to play a leading role in the scientific exploitation of the results, organizing the distribution of the data to the broader community and promoting its use for a wide range of astronomical investigations. The Hipparcos results were published both in a traditional printed form, filling 17 substantial volumes, and in electronic form on compact discs and through the nascent Internet, which by the late 1990s was beginning to transform the way scientific data were shared and accessed. The catalogue quickly became an essential reference for astronomers working in many fields, from stellar structure and evolution to galactic dynamics and beyond, and its influence would continue to grow in the years that followed as researchers found new applications for its precise measurements. The Tycho catalogue, derived from the star mapper data under the leadership of Eric Hogg, complemented the main Hipparcos results by providing positions and photometry for a much larger sample of stars, albeit with somewhat lower precision. The initial Tycho catalogue contained over 1 million stars, and a subsequent reprocessing of the data, incorporating improved methods and additional calibration information, produced the Tycho II catalogue with nearly 2.5 million entries. This secondary product proved particularly valuable for studies requiring dense all-sky coverage, such as the calibration of photometric surveys or the identification of reference stars for other observations, and it filled a niche that the smaller main catalogue could not address on its own. The success of Hipparcos owed much to the institutional framework within which it operated, a framework that brought together national space agencies, universities, and research institutes from across Europe in a collaborative enterprise that spanned more than 2 decades from conception to publication. The European Space Agency provided the spacecraft and launch services, the ground station network and mission operations, while the scientific analysis was carried out by the researchers at institutions in more than a dozen countries, funded by their national agencies and coordinated through the consortium structure. This model of international collaboration, in which the technical and scientific aspects of a mission are divided among different groups with complementary expertise, would become the template for subsequent large-scale space astronomy projects, and the lessons learned from Hipparcos informed the planning for its successor missions. And so, as you settle deeper into the comfort of this moment, you might let your thoughts drift across the vast distances that Hipparcos helped to measure, those gulfs of empty space between ourselves and the nearer stars, rendered knowable through the patient accumulation of tiny angular shifts observed from a spacecraft that was never quite where it was supposed to be, yet which nevertheless achieved what it set out to do. The story of Hipparcos is in many ways a story of adaptation and perseverance, of scientists and engineers who refused to abandon their goals when circumstances turned against them and who found ways to extract valuable results from a situation that might have defeated a less determined team. The catalogue they produced remains in use to this day, more than a quarter century after its publication, a testament to the care with which it was assembled and the rigor with which its errors were characterized and documented. Let the gentle precision of those measurements, the milliarcsecond accuracy of stellar positions determined from Earth orbit, carry you now toward rest, as the slow rotation of a distant spacecraft sweeps its view across the stars, building up, one transit at a time, a map of the heavens that would have astonished Hipparchus himself, could he have lived to see it. In the year 1997, The European Space Agency released a publication that would quietly transform the foundations of stellar astronomy. This document, designated ESA SP 1200, carried the unassuming title of the Hipparcos and Tycho catalogues, and within its many volumes lay the accumulated work of more than 2 decades of planning, engineering, observation, and painstaking data reduction. The satellite itself had ceased its observations some 4 years earlier, in August of 1993, and in the intervening period a dedicated team of scientists and analysts had labored to extract from the raw measurements a coherent picture of stellar positions and motions more precise than anything previously achieved in the long history of astrometry. The publication of these catalogues marked not merely the conclusion of a successful space mission, but the beginning of a new era in our understanding of the nearby universe, an era in which distances and motions that had remained uncertain for generations could finally be known with a confidence that earlier astronomers could scarcely have imagined. The main Hipparcos catalogue, which formed the centerpiece of this publication, contained entries for 117,955 stars. Each of these entries provided not a single measurement, but a carefully determined set of fundamental quantities, the position of the star on the celestial sphere, expressed in right ascension and declination, the proper motion describing how that position changes over time due to the star's movement through space, and the trigonometric parallax from which the distance to the star could be directly calculated. The precision of these measurements represented an improvement over previous ground-based catalogues by a factor ranging from 10 to 100, depending on the particular quantity and the particular star in question. Where earlier catalogues might determine a stellar position to within a few hundredths of an arcsecond under favorable conditions, the Hipparcos catalogue routinely achieved precisions of a single milliarcsecond, which is to say 1,000th of an arcsecond, 4 stars within its observing program. This level of precision, once considered impossibly fine for practical measurement, had become not merely achievable but routine through the application of space-based techniques and sophisticated statistical analysis. The parallaxes contained within the catalogue were perhaps the most scientifically valuable of all the measurements, for they provided the only purely geometric method of determining stellar distances. The median precision of these parallax measurements was approximately 1 milliarcsecond, which meant that for stars within a few hundred parsecs of the Sun, the distances could be determined with uncertainties of only a few %. This was a remarkable achievement when one considers that even the nearest stars beyond the Sun display parallaxes of less than 1 arcsecond, and that the detection of such tiny angular shifts had challenged astronomers since the time of Bessel and Henderson in the 1830s. The Hipparcos mission extended reliable parallax measurements to distances roughly 10 times greater than had previously been possible with ground-based techniques, opening up vast new volumes of the galaxy to direct geometric distance determination. Alongside the main catalogue, the Hipparcos mission produced a second, complementary catalogue known as the Tycho catalogue. This catalogue drew its data from the satellite star mapper detectors, which had been designed primarily to support the attitude determination of the spacecraft rather than as the primary scientific instruments. Nevertheless, the star mapper observations proved sufficiently precise to yield useful astrometric data for a much larger sample of stars than could be included in the main observing program. The Tycho catalogue contained entries for 1,058,332 stars, nearly 10 times the number in the main Hipparcos catalogue, though with somewhat lower precision in the measured quantities. The positional accuracies in the Tycho catalogue ranged from approximately 7 milliarcseconds for the brighter stars to around 25 milliarcseconds for fainter entries. And while these precisions fell short of the milliarcsecond level achieved in the main catalogue, they nonetheless represented a substantial improvement over many existing ground-based compilations. The Tycho catalogue thus served as a valuable bridge between the exquisite precision of the main Hipparcos program and the broader surveys of fainter stars that remained beyond the satellite's capabilities. The scientific impact of these catalogues began to manifest almost immediately upon their publication. Among the most significant early applications was the revision of the cosmic distance scale through improved calibration of the Cepheid period luminosity relation. Cepheid variable stars, which pulsate with periods that correlate predictably with their intrinsic luminosities, had long served as standard candles for measuring distances within our galaxy and to nearby external galaxies. The accuracy of this method depended critically upon knowing the true luminosities of nearby Cepheids, which in turn required reliable parallax measurements. The Hipparcos catalogue provided parallaxes for several dozen Cepheid variables, allowing astronomers to recalibrate the period luminosity relation with unprecedented precision. The results suggested that Cepheids were somewhat more luminous than previously believed, which implied that the galaxies containing them were farther away than earlier estimates had indicated. This revision propagated through the entire extragalactic distance ladder, affecting estimates of the Hubble constant and consequently the inferred age of the universe. In the years following the catalogue release, considerable effort was devoted to understanding the implications of these new Cepheid distances and reconciling them with other methods of distance determination. The application of Hipparcos data to stellar clusters also generated immediate scientific interest, though not without controversy. Among the most discussed results was the apparent revision of the distance to the Pleiades, that familiar grouping of young stars visible to the unaided eye in the constellation of Taurus. Ground-based studies employing various techniques had converged upon a distance of approximately 132 parsecs, while the Hipparcos parallax measurements suggested a somewhat smaller value of around 118 parsecs. This discrepancy, though seemingly modest in absolute terms, carried significant implications for the calibration of stellar models and the interpretation of the cluster's Hertzsprung-Russell diagram. If the shorter distance were correct, then the main sequence stars of the Pleiades would be less luminous than previously thought, requiring adjustments to theoretical models of stellar structure and evolution. The debate over the Pleiades' distance continued for many years after the catalogue publication, with some researchers questioning whether unrecognized systematic errors in the satellite data might be responsible for the discrepancy, while others accepted the new distance and sought to modify their understanding of stellar physics accordingly. This controversy, rather than diminishing the value of the Hipparcos results, served to illustrate the profound sensitivity of astrophysical conclusions to astrometric precision and the importance of continued efforts to refine and verify the fundamental measurements. The Hertzsprung-Russell diagram, that foundational tool for understanding stellar populations, received substantial improvements through the application of Hipparcos parallaxes. With accurate distances to tens of thousands of stars, astronomers could determine absolute magnitudes with far greater confidence than before, populating the diagram with precisely located points rather than the smeared distributions that had characterized earlier compilations. The main sequence, that diagonal band occupied by hydrogen-burning dwarf stars, could now be traced with exquisite definition, revealing subtle features and allowing detailed comparison with theoretical stellar models. The giant branch, populated by evolved stars of lower surface gravity and cooler temperatures, similarly came into sharper focus. Subdwarfs, white dwarfs, and other special categories of stars could be identified and characterized with greater certainty. The net result was a significant improvement in the empirical calibration of stellar luminosities as functions of color and spectral type, which in turn supported more reliable estimates of distances to remote stellar populations where parallax measurements remained unavailable. The improved calibration of stellar luminosities naturally carried implications for estimates of the ages of the oldest stars and star clusters, which in turn constrained the minimum age of the universe. Globular clusters, those ancient spherical aggregations of stars that orbit in the halo of our galaxy, had long been used as cosmic chronometers, their ages inferred from the luminosities of stars at the main sequence turn-off point, where hydrogen exhaustion causes stars to begin their evolution toward the giant branch. A brighter calibration of the main sequence implied that globular cluster stars were more distant and more luminous than previously thought, which in turn implied younger ages than earlier estimates had suggested. The initial Hipparcos-based calibrations indicated ages for the oldest globular clusters of roughly 11 to 12 billion years, somewhat younger than previous estimates that had sometimes exceeded 15 billion years. These revised ages were more easily reconciled with the expansion age of the universe inferred from the Hubble constant, easing what had once appeared to be a troubling inconsistency between stellar ages and cosmological timescales. The details continued to be refined in subsequent years as additional data and improved theoretical models became available, but the Hipparcos contribution to this fundamental problem was widely recognized. Beyond the calibration of distance indicators and stellar luminosities, the Hipparcos catalogues enabled detailed studies of stellar kinematics in the solar neighborhood. The combination of precise proper motions with radial velocities measured from ground-based spectroscopy allowed astronomers to reconstruct the three-dimensional space velocities of thousands of nearby stars, revealing the complex patterns of stellar motion within the galactic disk. The Oort constants, those parameters that describe the local rotation and shear of the galactic disk, could be redetermined with improved precision, refining our understanding of the Sun's motion relative to the local standard of rest and the overall rotation of the Milky Way. Studies of stellar streams and moving groups, associations of stars sharing common space motions that may indicate a common origin, benefited greatly from the improved kinematic data. The structure of the galaxy in the immediate solar vicinity, once known only in broad outline, began to emerge in considerably finer detail. The detection of orbital motion in binary and multiple star systems represented another significant capability of the Hipparcos mission. For close binary systems in which the orbital period was comparable to or shorter than the mission duration, the satellite observations sampled the orbital motion directly, revealing the sinusoidal or more complex displacement patterns characteristic of gravitational interaction between two or more stellar components. Even for systems with periods longer than the observing interval, perturbations of the proper motion could sometimes reveal the presence of an unseen companion. The analysis pipeline developed for the mission incorporated sophisticated models of binary motion, attempting to distinguish genuine orbital signals from noise and systematic effects. Where sufficient evidence existed, orbital parameters were determined and catalogued alongside the standard astrometric quantities. The double and multiple systems annex accompanying the main catalogue provided detailed information on resolved and unresolved binary systems, including separation, position angle, and magnitude difference for pairs that could be distinguished as separate sources. This annex documented the resolution of close pairs that had appeared as single sources in earlier ground-based work, revealing binary companions hidden within the seeing disk of atmospheric turbulence. the study of binary stars, which provides the primary observational route to determining stellar masses, thus received a significant boost from the Hipparcos results. For some stars, the catalogue provided not merely positions and linear proper motions, but also terms describing the rate of change of proper motion, sometimes called proper motion derivatives or accelerations. These terms, where they could be measured with sufficient significance, indicated departures from uniform rectilinear motion across the sky, departures that most naturally arose from the gravitational influence of an unseen companion. The presence of significant acceleration terms in the motion of a star flagged it as a candidate binary system even when no companion could be directly resolved or detected through other means. This capability extended the reach of binary star detection to systems with orbital periods too long or separations too small for direct resolution, adding another dimension to the scientific yield of the mission. Perhaps the most fundamental transformation brought about by the Hipparcos catalogue was the replacement of the existing reference frame for fundamental astronomy. Prior to Hipparcos, the standard celestial reference frame was embodied in the fifth fundamental catalogue, known by its German abbreviation FK5, which had been compiled from ground-based observations and published in 1988. The FK5 represented the culmination of centuries of meridian circle observations, defining the positions of fundamental stars with the best precision achievable through classical techniques. However, it suffered from the inevitable limitations of ground-based astrometry, including regional systematic errors, zonal distortions, and residual uncertainties in the orientation and rotation of the reference frame. The Hipparcos catalogue, by contrast, had been constructed from observations made above the atmosphere with a rigid and well-characterized instrument, and its internal consistency and freedom from regional distortions far surpassed anything achievable from the ground. Moreover, the Hipparcos reference frame had been carefully aligned with the International Celestial Reference Frame, a quasi-inertial frame defined by extragalactic radio sources whose immense distances rendered their proper motions negligible. This alignment ensured that the Hipparcos positions referred to a coordinate system with minimal spurious rotation, a system that could serve as the fundamental basis for all positional astronomy. In 1998, the International Astronomical Union adopted the Hipparcos catalogue as the basis for a new optical realization of the celestial reference frame, effectively retiring the FK5 from its role as the primary standard. This decision marked a watershed in the history of astrometry, as the accumulated work of generations of meridian observers gave way to a new foundation built upon space-based measurements. The improvement was not merely incremental but qualitative, establishing a reference frame roughly an order of magnitude more accurate than its predecessor and tied directly to the extragalactic frame that provided the closest practical approximation to an inertial coordinate system. The scientific community rapidly adopted the new standard, and within a few years the Hipparcos reference frame had become the default foundation for positional astronomy, navigation, and the reduction of observational data from ground-based and space-based telescopes alike. The legacy of the Hipparcos mission extended far beyond the immediate scientific results obtained in the years following catalogue publication. The precision achieved by the satellite demonstrated that space astrometry could deliver transformative improvements over ground-based techniques, encouraging the development of still more ambitious missions to extend the reach of geometric distance measurement deeper into the galaxy. The statistical and computational methods developed for the Hipparcos data reduction established templates for subsequent projects, and the scientific community gained valuable experience in the analysis and interpretation of large astrometric datasets. The controversies that arose, such as the debate over the Pleiades distance, stimulated further research and ultimately contributed to a deeper understanding of both the power and the limitations of parallax measurements. In all these ways, the publication of ESA SP 1200 in 1997 represented not an ending but a beginning, a foundation upon which future generations of astronomers would continue to build as they pursued the ancient goal of mapping the positions and motions of the stars with ever greater precision. And so we come now to the quieter revolution, the one that took place not at the eyepiece of great telescopes, but in rooms filled with the hum of machinery, the soft clatter of cards, and eventually the gentle whir of magnetic tape spinning through readers. For you see, the challenge of astrometry was never simply one of observation, though observation remained essential and demanding. The greater challenge, the one that grew more pressing with each passing decade, was the challenge of calculation, of taking the countless individual measurements accumulated across years and centuries and weaving them together into a coherent picture of the sky. In the earliest days of precise stellar measurement, every calculation was performed by hand, written out in careful columns by human computers, a term that once described not a machine but a person, often a woman, employed specifically to carry out the tedious arithmetic that astronomy required. These human computers would sit at desks with pen and paper, working through logarithm tables and trigonometric functions, reducing observations one by one, a process that might take weeks or months to work through a single night's worth of telescope data. The patience required was extraordinary, the dedication remarkable, and the possibility for error ever present, no matter how careful the work might be. As the catalogues grew larger, containing not hundreds but thousands and then tens of thousands of stars, the limitations of hand calculation became increasingly apparent. A single comprehensive star catalogue might require millions of individual arithmetic operations, each one susceptible to small mistakes that could propagate through the final results. The need for mechanical assistance was clear, though the path toward such assistance would prove long and gradual, marked by incremental improvements rather than sudden breakthroughs. The earliest mechanical aids were simple devices, calculating machines that could perform addition and multiplication more quickly and reliably than human mental arithmetic alone. But the true transformation began with the development of punched card technology, pioneered by Herman Hollerith in the late 19th century for the United States Census. Hollerith's machines used cards with holes punched in specific patterns to represent numerical data, and these cards could be sorted, counted, and tabulated by machines that read the positions of the holes through electrical contacts. The system that had proven so valuable for counting populations would soon find application in counting and cataloguing stars. By the early 20th century, astronomical observatories began adopting Hollerith equipment and similar punched card machines for the compilation of their growing catalogues. Each observation could be encoded on a card, with the star's position, brightness, and various identifying information represented by the pattern of punched holes. These cards could then be sorted mechanically, grouped by region of sky or by stellar characteristics, and processed through tabulating machines that would add up values and print summaries without the need for human arithmetic at every step. The process remained painstaking by modern standards, of course. The cards had to be punched by hand, checked for errors, and fed through the machines in careful sequence. A single mispunched card could introduce errors that might not be detected until much later in the analysis. But the improvement over purely manual methods was substantial, allowing observatories to process larger quantities of data than ever before and to maintain better consistency across their catalogues. The true electronic computer arrived in the mid-20th century, emerging first from military applications during and after the Second World War. One of the earliest of these machines, the electronic numerical integrator and computer, ONIC, was developed at the University of Pennsylvania and became operational in 1945. Originally designed to calculate artillery firing tables for the United States Army. The machine was enormous by any standard, filling a large room, consuming tremendous amounts of electrical power, and requiring constant maintenance of its many thousands of vacuum tubes. At the Aberdeen Proving Ground in Maryland, where ENIAC was eventually relocated, astronomers began to recognize the potential of such machines for their own calculations. The ballistic computations for which ENIAC had been designed shared certain mathematical characteristics with the problems of celestial mechanics and positional astronomy, involving many variables, requiring high precision, and demanding the solution of systems of equations far too complex for practical hand calculation. Though ENIAC itself was not used extensively for stellar cataloging, its existence and the existence of its successors demonstrated that a new era of computational capability had dawned. Through the 1950s and into the 60s, electronic computers became progressively more powerful, more reliable, and more accessible to scientific institutions beyond military establishments. Universities and observatories began to acquire their own machines or to gain time on shared facilities, and astronomers set about adapting their traditional methods to take advantage of these new tools. One of the central techniques that benefited from this transition was the method of least squares adjustment, a mathematical approach with roots reaching back to the early 19th century and the work of Carl Friedrich Gauss and Adrien-Marie Legendre. The principle of least squares adjustment addresses a fundamental problem in observational science: the problem of combining multiple measurements of the same quantity when those measurements do not perfectly agree. If you observe a star's position on 10 different nights and obtain 10 slightly different results, how do you determine the most likely true position? The least squares method provides an answer by seeking the value that minimizes the sum of the squared differences between the observations and the estimated position. This approach gives more weight to observations that cluster close together and less weight to outliers that deviate substantially from the rest. For astrometry, where every star in a catalogue might have been observed dozens or hundreds of times from different observatories using different instruments under different atmospheric conditions, the least squares adjustment became essential for combining all this disparate information into a single coherent result. But the calculations involved were formidable. Adjusting the positions of thousands of stars simultaneously, while also solving for systematic errors in the instruments and reference frames, required the solution of systems of equations containing thousands of unknowns. Before electronic computers, such global adjustments were essentially impossible, and astronomers had to make do with more limited local solutions. The IBM 7094 computer, introduced in the early 1960s, represented the kind of machine that began to make comprehensive astrometric adjustments practical. This transistorized mainframe computer was among the most powerful of its era, capable of performing hundreds of thousands of operations per second, a figure that seems modest today but that opened entirely new possibilities for astronomical calculation. At the Smithsonian Astrophysical Observatory, researchers used the IBM 7094 to compile what became known as the Smithsonian Astrophysical Observatory Star Catalog, published in 1966. This catalog represented a milestone in computational astrometry, containing the positions and proper motions of more than 250,000 stars. derived from the combination and adjustment of earlier observations using the full power of the electronic computer. The machine could process in hours what would have taken human computers working with mechanical calculators years or decades to accomplish. The resulting catalogue became a standard reference for astronomical research, demonstrating the value of bringing modern computational methods to bear on the accumulated wealth of historical observations. As computers continued to improve through the 1970s and 80s, growing faster, acquiring larger memories, and becoming more widely available, astrometrists developed increasingly sophisticated software to support their work. One particularly influential contribution was the Starlink Positional Astronomy Library, known as SLALib, developed by Patrick Wallace at the Rutherford Appleton Laboratory in the United Kingdom. This collection of software routines provided reliable, well-documented implementations of the many mathematical transformations that astrometric work required. SLALib included functions for converting between different coordinate systems, for accounting for the effects of precession, nutation, and aberration, for transforming between apparent and mean positions, and for handling the various time systems used in astronomical calculation. By providing these tools in a standardized and carefully tested form, Wallace's library freed researchers from having to implement these complex routines themselves, reducing the likelihood of errors and ensuring consistency across different research programs. The library became widely used throughout the astronomical community and continued to be developed and maintained for many years. The culmination of computational astrometry in the 20th century came with the Hipparcos mission, which we have touched upon in discussing space-based observations. From a computational standpoint, Hipparcos presented challenges unlike anything that had come before. The satellite did not take conventional photographs of star fields but instead used a complex optical system to scan the sky continuously, measuring the angles between stars as they crossed a sensitive detector. The raw data from the mission consisted not of direct positions but of one-dimensional measurements, records of when particular stars crossed particular reference lines as the satellite slowly rotated. Reconstructing a complete picture of the sky from these one-dimensional scans required what the Hipparcos scientists called sphere reconstruction, the process of working backwards from millions of individual transit times to determine the three-dimensional arrangement of over 100,000 stars across the celestial sphere. This inverse problem was enormously complex because every measurement depended not only on the position of the star being observed but also on the precise orientation of the satellite at each moment, an orientation that was itself being determined from the same observations. The solution required iterative techniques in which an initial approximate model of the star positions and satellite attitude was progressively refined through repeated cycles of calculation. In each iteration, the predicted transit times based on the current model were compared with the actual observations, and the discrepancies were used to adjust both the stellar positions and the reconstructed satellite attitude. This process had to be repeated many times, with each cycle bringing the model closer to consistency with the observations, until the adjustments became negligibly small and a stable solution emerged. The computational demands of this iterative process were unprecedented in astrometry. The final solutions involved the simultaneous adjustment of more than 2 million unknowns, a mathematical problem far beyond anything that could have been contemplated in the era of hand calculation or even the early electronic computers. The Hipparcos data reduction teams used the most powerful computing facilities available in the late 1980s and early 1990s, and even so, the complete analysis required years of dedicated effort. Running parallel to these advances in computation was a revolution in the technology of detection itself, a shift from the photographic plates that had served astronomers for a century to electronic sensors known as charge-coupled devices, or CCDs. These devices, originally developed in the 1960s for other applications, consisted of arrays of light-sensitive elements that converted incoming photons directly into electrical signals that could be read out and stored digitally. The advantages of CCD detectors for astrometry were profound and multiple. Where photographic plates responded to light in a complex, nonlinear fashion that required careful calibration and introduced significant uncertainties, CCDs produced signals that were directly proportional to the amount of light received, making their measurements far more straightforward to interpret and combine. The quantum efficiency of CCDs, the fraction of incoming photons that were actually detected and contributed to the signal, was substantially higher than that of photographic emulsions, meaning that fainter stars could be observed in shorter exposure times. Perhaps most importantly for the computational aspects of astrometry, CCD detectors produced their data directly in digital form. There was no need for the laborious process of measuring photographic plates with mechanical scanning machines, converting the analog information on the plate into numbers that computers could process. The output of a CCD observation was already a grid of numerical values representing the brightness at each point in the image, ready for immediate analysis by software designed for the purpose. This direct digital output transformed the workflow of astrometric research. Observations could be processed and analyzed within hours or days of being obtained, rather than waiting months or years for plate measurement. Automated software could scan through CCD images, identifying stars, measuring their positions with sub-pixel precision, and comparing the results with existing catalogues without requiring constant human attention. The throughput of astrometric programs increased enormously as a result. The combination of CCD technology with modern computing also enabled sophisticated techniques for combining observations known as block adjustment methods. When a telescope equipped with a CCD camera images a region of sky, it captures not just one star but many stars simultaneously, spread across the field of view. By observing overlapping fields, so that some stars appear in multiple images, it becomes possible to tie all the observations together into a unified network. Block adjustment techniques exploit these overlaps to solve for both the positions of all observed stars and the systematic parameters describing each observation, including the precise pointing of the telescope, any distortions in the optical system, and variations in the atmospheric refraction. The mathematics involved are an extension of the least squares methods developed earlier, but applied now to much larger and more complex systems of equations made tractable by advances in computing power. Through block adjustment, surveys using CCD cameras could achieve levels of internal consistency far superior to what had been possible with photographic plates. Systematic errors that might have gone undetected in earlier work, affecting entire regions of a catalogue, could now be identified and corrected through the web of overlapping observations. The resulting catalogues achieved precisions approaching the theoretical limits set by atmospheric turbulence for ground-based observations. As the 20th century drew toward its close, the tools available to astrometrists bore little resemblance to those of even a few decades earlier. The human computers with their pen and paper had given way to electronic machines performing billions of operations per second. The photographic plates that had accumulated in observatory archives for 100 years were being supplemented and eventually replaced by CCD detectors feeding digital data directly into analysis pipelines. The mathematical techniques for combining observations had evolved from simple averaging to sophisticated global adjustments involving millions of parameters. Yet through all these changes, the fundamental goal remained the same as it had been for Edmund Halley when he first compared his observations with those of the ancient Greeks, and for Bradley when he discovered the aberration of starlight, and for Bessel when he measured the first stellar parallax. The goal was simply this: to know where the stars are, to map their positions with ever-increasing precision, and to understand the motions that carry them slowly across the celestial sphere. The computers and the software and the electronic detectors were merely tools in service of that ancient and patient endeavor, means of handling the ever-growing flood of measurements that modern instruments could provide. And now, as you rest here listening, you might let your thoughts drift along with those calculations, imagining the numbers flowing through circuits and memory, the iterative refinements bringing order to millions of observations, the gradual emergence of a picture of the sky more accurate than any that has come before. It is quiet work, in its way, the work of computers processing data in climate-controlled rooms, of software routines performing their transformations again and again, of astronomers patiently checking results and refining methods. Quiet work, but essential, building upon the centuries of observation that preceded it and preparing the foundation for the centuries yet to come. By the year 1997, astrometry had arrived at a moment of quiet consolidation, a gentle gathering together of centuries of patient observation into something approaching a unified understanding of how we might describe the positions of stars with both precision and consistency. The field had grown from Edmund Halley's modest discovery in 1718, when he first noticed that certain bright stars had shifted from their ancient recorded places, into a global enterprise spanning continents and wavelengths and even reaching beyond the atmosphere of our planet into the stillness of space. Nearly 3 centuries had passed since that initial recognition that stars were not, after all, eternally fixed in their celestial positions, and in those intervening years the work of countless astronomers had transformed a simple observation into a sophisticated science capable of measuring stellar positions to accuracies that would have seemed almost magical to earlier generations. The synthesis that had been achieved by this time was remarkable in its comprehensiveness, though it had come about gradually through the steady accumulation of techniques and technologies rather than through any single revolutionary moment. Ground-based observations continued their long tradition of careful measurement, now enhanced by electronic detectors that had largely replaced the photographic plates which had themselves replaced the visual observations of earlier centuries. From observatories scattered across both hemispheres, telescopes equipped with charge-coupled devices gathered starlight with unprecedented efficiency, recording positions with a precision and consistency that surpassed what had been possible with emulsion-coated glass. Meanwhile, the Hipparcos satellite had completed its mission and delivered its catalogue, demonstrating that space-based astrometry could achieve accuracies of approximately 1 milliarcsecond, roughly 1,000 times better than what ground-based optical telescopes could manage when atmospheric turbulence was taken into account. At the same time, radio astronomers had been contributing their own measurements to this growing body of knowledge, using techniques quite different from optical observation but ultimately serving the same fundamental purpose. Very long baseline interferometry, that patient technique of combining signals from radio telescopes separated by thousands of kilometers, had proven capable of measuring the positions of distant radio sources with extraordinary precision. These measurements, targeting quasars and other compact extragalactic objects whose immense distances rendered them essentially motionless against the celestial sphere, provided a reference frame of remarkable stability. The radio sources did not share the complications of nearby stars, which moved measurably across the sky due to their own velocities through space and their parallactic shifts as Earth orbited the Sun. Instead, they served as fixed points, anchors against which all other measurements could be referenced. The culmination of these various threads of observation was the adoption of the International Celestial Reference System, a framework that would replace the older Fifth Fundamental Catalogue, known as FK5, as the standard against which celestial positions would be reckoned. This transition, occurring officially on the 1st of January 1998 but prepared throughout the preceding year, represented a significant shift in how astronomers thought about the fundamental reference frame of the sky. Where previous systems had been defined by catalogues of stellar positions, with all the complications that arose from the proper motions and parallaxes of those defining stars, the new system took its orientation from objects so distant that their apparent motions were negligible over any humanly meaningful timescale. The origin of this new reference system was placed not at the center of the Earth or at some arbitrary point in space, but at the barycenter of the solar system, that gravitational center of mass about which the Sun and all the planets move in their intricate dance. This choice simplified the mathematical treatment of observations, removing certain complications that arose when dealing with measurements made from a planet that was itself in motion. The axes of the system, those imaginary lines extending outward to define directions in three-dimensional space, were fixed by the positions of several hundred extragalactic radio sources observed through very long baseline interferometry, their locations determined with such precision that the orientation of the reference frame could be maintained to a stability better than could be achieved by any collection of stars within our own galaxy. The practical realization of this reference system, the actual catalogue of positions against which observations could be compared, was provided by both radio and optical measurements working in coordination. The radio sources themselves were too distant and too faint in optical wavelengths to serve as convenient reference points for most astronomical observations, so the positions of nearby stars, measured both from the ground and from space, were carefully tied into the radio-defined frame. The Hipparcos catalogue, with its milliarcsecond precision for over 100,000 stars, served as the primary optical realization of the new reference system, its star positions aligned with the extragalactic frame through a careful process of comparison and adjustment. This combination of radio and optical measurements, of ground-based and space-based observations, represented a kind of harmony that earlier generations of astronomers might have found difficult to imagine. The wavelengths of light and radio were so different, the techniques of observation so distinct, and yet they could be brought together into a single coherent framework. The stars that optical telescopes observed were mostly silent in radio wavelengths, and the quasars that radio interferometers measured with such precision were often faint smudges requiring the largest optical telescopes to detect. Yet through careful calibration and cross-referencing, their positions could all be expressed in the same reference system, comparable and combinable as never before. On the ground, several programs were continuing the work of measuring stellar positions with ever-increasing precision and coverage. The United States Naval Observatory, that institution which had contributed so much to astrometry over the preceding century, had embarked upon a new program to survey the sky with modern charge-coupled device cameras, intending to create a catalogue that would cover the entire sky accessible from their observing sites with positions accurate to better than 100 milliarcseconds for millions of stars. This USNO-CCD astrograph catalogue program, known by its initials UCAC, represented a continuation of the traditional ground-based approach, adapted to take advantage of electronic detectors and improved data processing techniques. Meanwhile, other surveys undertaken primarily for different purposes were yielding astrometric information as a valuable byproduct. The Sloan Digital Sky Survey, designed primarily to map the large-scale structure of the universe through observations of distant galaxies and quasars, was also providing precise positions for the countless stars that fell within its fields of view. The careful calibration required for the survey's primary science goals meant that stellar positions could be extracted from the data with useful accuracy, adding millions more objects to the growing inventory of measured celestial coordinates. Such surveys demonstrated how astrometry had become interwoven with other branches of observational astronomy, no longer a discipline unto itself but a fundamental component of nearly every program that pointed a telescope at the sky. Perhaps most significantly for the future of the Hipparcos legacy, work was proceeding on what would become the Tycho II catalogue, a project that exemplified the value of combining observations from different eras. The Hipparcos satellite had carried, in addition to its primary instrument, a secondary star mapper that had observed a much larger number of stars, though with somewhat lower precision. These observations, processed into what became known as the Tycho catalogue, provided positions for over 1 million stars at the mean epoch of the satellite's observations in the early 1990s. But positions alone, however precise, told only part of the story. To determine how stars were moving across the sky, one needed positions from different times, separated by as long an interval as possible. The solution came from an unexpected quarter, reaching back to the very beginning of photographic astrometry. The Astrographic catalogue, that ambitious international project begun in 1887, had measured the positions of millions of stars on photographic plates taken around the turn of the 20th century. These old measurements, recorded in volumes of printed tables and stored in observatory archives, contained positional information spanning the years from roughly 1890 to 1950, depending on which participating observatory had contributed which zones of the sky. By carefully re-reducing these century-old observations, applying modern techniques to extract the maximum accuracy from the original plate measurements, and combining them with the space-age precision of the Tycho observations, it became possible to derive proper motions for over 2 million stars. The resulting Tycho II catalogue, which would be published in the year 2000, represented a beautiful example of how different generations of astronomical work could be brought together. The patient efforts of 19th-century astronomers, squinting through eyepiece micrometers at photographic plates, found new value when combined with the electronic measurements of a satellite launched a century later. The long time baseline between the observations, approximately 90 years in many cases, allowed even small proper motions to accumulate into measurable shifts, while the precision of the modern observations anchored the measurements in the contemporary reference frame. Stars that appeared to be stationary on any human timescale revealed their slow drifts across the sky when their positions from these widely separated epochs were compared. Looking toward the future, the astronomical community had already approved a successor to Hipparcos that promised to extend the achievements of that mission by remarkable factors. The Gaia mission concept, selected by the European Space Agency for development, aimed to survey the entire sky with a precision measured in microarcseconds, roughly 1,000 times better than Hipparcos had achieved. Where Hipparcos had catalogued approximately 100,000 stars with milliarcsecond precision, Gaia was designed to measure positions, parallaxes, and proper motions for as many as 1 billion stars. a number so large that it defied easy comprehension. The technical approach of Gaia drew upon lessons learned from Hipparcos while incorporating advances in detector technology and data processing that had occurred in the intervening years. Like its predecessor, Gaia would scan the sky continuously, measuring the angular separations between stars at widely different positions rather than their absolute coordinates. This relative measurement approach, when combined with sophisticated mathematical techniques for combining millions of individual observations, would yield positions of extraordinary precision. The accumulated data from years of scanning would be processed into a catalogue that would transform our understanding of the Milky Way galaxy, though that day remained years in the future and the spacecraft itself had not yet been built. The connection between astrometry and the broader field of astrophysics had grown ever stronger as the precision of measurements improved. At the most fundamental level, astrometric observations provided distances to stars through the measurement of parallax, that small apparent shift in a star's position caused by our changing viewpoint as Earth orbits the Sun. Knowing the distance to a star was essential for understanding its true nature, for only then could the apparent brightness be converted into an absolute luminosity, that measure of how much energy the star was actually radiating into space. Without distances, astronomers could not determine whether a bright star in the sky was a nearby sun of modest output or a distant beacon of tremendous power. The Hipparcos mission had transformed this aspect of stellar astrophysics by providing precise parallax measurements for a large sample of stars, including many that served as calibrators for other distance determination methods. The period luminosity relation of Cepheid variable stars, so crucial for establishing the cosmic distance scale, could be refined using Hipparcos parallaxes of the nearest Cepheids. The absolute magnitudes of stars of various spectral types, used to estimate distances through spectroscopic parallax methods, could be calibrated more accurately when true geometric distances were available for comparison. In this way, the patient work of measuring stellar positions rippled outward to affect our understanding of the scale of the universe itself. Beyond distances, the proper motions revealed by astrometric observations provided insight into how stars moved through space, and through those motions, into the structure and dynamics of our galaxy. Stars were not scattered randomly through the Milky Way but organized into populations with characteristic patterns of motion, and by measuring the velocities of large numbers of stars, astronomers could trace out the rotation of the galactic disk, the random motions of the older stellar populations, and the streams of stars torn from disrupted satellite galaxies that had fallen into our own. Each proper motion measurement, that tiny annual shift in celestial coordinates, represented a piece of evidence about the gravitational forces shaping the galaxy and the history of stellar orbits over billions of years. The year 1997 thus marked a moment of transition, when the achievements of the past had been consolidated into a unified reference frame while preparations were underway for advances that would exceed everything that had come before. The path from Halley's discovery to this point had required 279 years, spanning generations of astronomers who had devoted their careers to the careful measurement of stellar positions. Many had spent decades at the eyepiece, recording observations night after night in pursuit of ever smaller refinements in positional accuracy. Others had developed mathematical techniques for extracting order from masses of observations, for accounting for the many effects that could perturb measured positions from their true values. Still others had built instruments of increasing sophistication, from the transit circles of classical observatories to the photographic telescopes of survey programs to the satellites that observed from above the troublesome atmosphere. Throughout this long development, Certain themes had persisted even as the technologies changed beyond recognition. The importance of patient, systematic observation had been demonstrated repeatedly, for it was only through the accumulation of measurements over time that proper motions and parallaxes could be detected. The value of international cooperation had been established by projects from the Astronomische Gesellschaft catalogues to the Astrographic catalogue to the Hipparcos mission, recognizing that the sky was too vast for any single institution to survey alone. The necessity of careful attention to systematic errors had been learned through hard experience, as catalogues based on seemingly excellent observations had later been found to contain subtle biases that propagated into all results derived from them. The reference frame itself had evolved from a practical necessity to an object of profound scientific interest. The ancient astronomers had needed a way to record and communicate celestial positions, and they had done so using coordinates measured from observable references like the celestial equator and the vernal equinox. But these references were themselves in motion, precessing and nutating due to gravitational forces acting on Earth's rotating bulk, so that the coordinate system drifted slowly against the background of stars. Later generations had defined their reference frames using catalogues of stellar positions, but stars themselves moved, and so the frame drifted in different ways. Only with the adoption of the extragalactic reference frame, fixed by objects so distant that their motions were immeasurable, had astronomers finally achieved something approaching a truly inertial system, stable to the limits of measurement precision. As the 20th century drew toward its close, astrometry stood ready for a new era of discovery. The techniques developed over centuries of painstaking work had been refined to a level of precision that would have astounded the pioneers of the field. The understanding of error sources and their mitigation, accumulated through generations of experience, informed the design of new instruments and observing programs. The mathematical methods for combining observations into catalogues had become sophisticated enough to handle datasets of unprecedented size and complexity. And the motivation for continued improvement had grown stronger than ever, as astronomers recognized that precise positions, distances, and velocities were essential for answering the great questions about the structure and evolution of our galaxy and the stars within it. The stars that Halley had found to have moved from their ancient positions continued their journeys across the sky, joined now by millions of others whose motions had been measured and catalogued. Arcturus and Sirius and Aldebaran, those bright luminaries that had first revealed stellar proper motions to human understanding, traced their slow paths against the background of more distant suns, their movements now known with precision measured in thousandths of an arcsecond per year. And fainter stars, vast hosts of them too dim to have attracted the attention of ancient astronomers, were yielding their positional secrets to modern instruments, each measurement adding another thread to the tapestry of knowledge that astrometry was weaving. The night sky, so apparently changeless to casual observation, had been revealed through centuries of patient measurement to be a slowly transforming tableau, with every point of light in gradual motion relative to every other. The patterns of the constellations that had served ancient peoples as guides and calendars were temporary arrangements, destined to dissolve into unrecognizability over timescales of hundreds of thousands of years as stellar proper motions accumulated. Only through the precise work of astrometry could these changes be detected and measured, transforming what appeared to be a static backdrop into a dynamic system whose motions could be charted and understood. And so the work continued, as it had for nearly 3 centuries and as it would continue into the future that Gaia and its successors would explore. The quiet, patient labor of measuring stellar positions, so seemingly modest in its ambitions yet so profound in its implications, proceeded steadily forward, adding observation to observation and refinement to refinement, mapping the heavens with ever greater fidelity to their true arrangement. It was work well suited to those of methodical temperament and long patience, astronomers content to contribute their share to an enterprise that would outlast any individual career, finding satisfaction in the gradual improvement of human knowledge about the universe of stars that surrounded our small world.